Hi, I'm Pete Lemaster, creator of the Lemaster Tech YouTube channel, and for the last 10 years I've been working in industrial automation and controls engineering. This is a field I feel very passionately about. It's an often overlooked or seldom talked about in university field of engineering. It's adjacent to what some may call mechatronics or robotics, but in particular, it's in an industrial setting, and it's the hidden backbone driving all of manufacturing forward worldwide. The last 4 years since starting my YouTube channel, I've slowly been trickling certain videos and tutorials on this field out on the channel, but never really painted a comprehensive picture of a crash course, start here, how to become and how to learn about controls and automation engineering. Until now. In this tutorial series, we mix talking about concepts with actual practical hands-on exercises using free software and very affordable hardware so that you can learn about PLC programming, SCADA and HMI development, SQL and Historian, electrical schematics, in an approachable and affordable way. This video is a 17-chapter video, and while I do believe they play logically back to back, you do not need to watch the entire 5+ hour video in one sitting. You don't have to watch it in order if you find more value in certain concepts than others. There will be timestamps and chapters breaking up everything as you go. The 17 videos were recorded over the past 4 years since I started my YouTube channel. While I do think they play in a logical order, not be always the smoothest flow between one video and the next. By the end of this video, you should have a really great comprehensive understanding of the basic concepts of what is controls and automation engineering, feel confident that you've been exposed to the basic concepts of the field, and feel empowered to go out and further your depth of knowledge in the field. It's an incredibly important field of engineering. I feel very passionately about it, and I'm very excited to bring you this series. If you do find it useful, please consider leaving a like on the video, subscribe to Lemaster Tech on YouTube, and thank you so much for watching. Enjoy the series. By the end of this course, you should have an excellent understanding of what controls and automation is. You should also be pretty familiar with what industries and companies would be looking for these skills and trades. Be equipped to know whether getting into a career in this field or an education in this field is something that would interest you. And lastly, you should feel very equipped to know the right ways to get more information if you're curious in pursuing this field further. So for episode 1, Introduction to Controls and Automation Engineering today, what we're gonna cover is what controls and automation engineering is, key tools and technologies, as well as some lingo that you'll need to know, the biggest industries that need automation, average salary ranges you can expect. So if you're completely new to the field, in just a few sentences, what is controls and automation engineering? In my words, it's the field of engineering pertaining to improvements to a process by increasing throughput and manufacturing speed, increasing safety and system reliability, or both. And this is most commonly achieved by writing code for a dedicated industrial computer known as a programmable logic controller, or PLC, that controls input and output devices, referred to as I/O, and often interfacing with the engineers and operators through a human-machine interface, or HMI. There's a little bit of industry lingo in there, but the essence of it is we make things faster, higher quality, or safer. And ideally, we would do all three. So, bit of a funny meme here, but I think it's actually super applicable. A controls and automation engineer most commonly is not something you go to school for. At least not specifically for. You have to have enough mechanical or chemical knowledge to be able to be helpful in the process that you're automating. But you also have to have enough electrical engineering knowledge that you'll know what you're doing with a panel design schematic. But you're also gonna have to be enough of a software developer, computer science engineer to be able to write some functional, elegant, easy to read and easy to debug PLC code. And on top of all of that, you're gonna need to dip your toes in the IT field of knowing a little bit about industrial networking. And it's not that you have to enter the field with all of these skills, but you should enter the field with some of them and be ready to learn the rest of them. So some of the key technologies and tools of the trade, words that you will absolutely need to be familiar with if you have any interest in getting into this field or knowing about the field. The programmable logic controller, the PLC. There are definitely some industries moving towards an industrial PC, which is just like a really robust computer running Windows sometimes, or even some smaller automation systems systems now relying on microcontrollers like a Raspberry Pi or an Arduino if it's a really simple application. But far and away, the industry standard for years and years, and likely continuing for years and years to come, is the programmable logic controller. There are so many manufacturers of PLCs. The biggest ones, and if you're in the US, the ones you'll almost certainly get exposed to at some point: Allen Bradley, Rockwell, ABB. Those are kind of three of the giants, but there are so many companies that make PLCs as well. Mitsubishi, Panasonic, Wago, to name a few. There's more. And so a PLC is a specific type of computer optimized for high reliability, synchronous programming, meaning time-cycled code, and converting commands to electrical signals to control devices known as outputs, and read electrical signals back from devices known as inputs. Specific programming languages exist to write code for these PLCs. The most common two, and the two that you should have on your radar right off the bat, are ladder logic and structured text. Ladder logic looks a lot like relays and kind of an electrical-based programming language. It's very visual. It's like a flow chart that combines programming concepts with electrical concepts. And structured text is somewhere between like a C++, C#, Python hybrid, more of a traditional programming language, to where people with a software background often feel more comfortable writing in structured text. People with a mechanical or electrical background often pick up ladder logic. But to talk a little more about input and output devices, there are really only two types of input and output devices here, and I'm simplifying, but this is a crash course. Digital inputs and outputs are also known as discrete, Boolean, on-off, binary. Think just a simple light switch, an on-off light switch where the light bulb turns on or turns off. It's only two states, and examples of this in the field could be a start-stop pump or motor, a valve that is open or close, and information back, like a light that is either on or off, a push button that is either pressed or not pressed, discrete, digital, on-off, or analog inputs and outputs, aka variable range, 0 to 100%, position control. And for this, you can think of like a dimmer switch in your home where there's a 0 to 100% setting and the variable range is known as analog. So in process, the most common ones you might see for inputs are like temperature sensors, flow sensors, pressure sensors, and the most common outputs you might see are like pumps that can ramp up in speed, known as variable frequency drives, or motors that have adjustable speed parameters, or 0 to 100% open control valves. And a lot of devices now are smart enough to actually use an advanced communication protocol like Ethernet, EtherCAT, Profinet, Modbus, TCP/IP, just to name a few. There are a lot of others, but even when you boil it down, if they are talking over those advanced communication protocols, the end devices you're interfacing with still typically fall into either digital or analog. In determining what type of I/O you have and how many total points you have typically is one of the key drivers in a lot of the hardware decisions you'll make in a project. And one of the last huge things you need to be aware of is the human-machine interface, or HMI. Some very simple systems might be controllable just from a few push buttons or indicator lights and not actually require custom graphics to be made, but the vast majority of automation systems are going to require well-designed, simple and easy to use HMI graphics. Software developers and people with a programming background might think of these as GUIs, or graphical user interfaces, but in the industry world, because you're controlling machines, the phrase human-machine interface, or HMI, is typically used more often. And these can range from simple displays with a few buttons or device statuses to super complicated plant overviews with thousands of data points being pulled back in. A standalone HMI, a very simple display, could be used to control one piece of equipment, sometimes called a skid, but a complicated graphical display environment with embedded trending and alarms and security is typically going to fall more in the category of a SCADA, or supervisory control and data acquisition system. Which brings us to the supervisory control and data acquisition system. Plus, we're going to talk about the whole automation pyramid thing. This is kind of a very important concept that's really a lot of jargon, but it does actually hold true for the industry. Supervisory control and data acquisition system, more commonly called a SCADA, is like a blend of the HMI that allows operators to interface and control with devices, but also like a corporate software tool that can pass data up to a data aggregation system. But what you need to know about the automation pyramid is basically every control system has the lowest two levels: the field level, meaning devices that are being controlled and giving you feedback, and the control level, which is like where your PLCs and smart devices and switches and networking live. And then very often a plant or a system will stop at the supervisory level. So a SCADA might be as high as a plant goes. Not everyone has an ERP controlling production, and not everyone has an MES for data aggregation, but that is technically the automation pyramid. That's enough about that for now. Let's move on. Other things to keep on your radar, we're not going to do a deep dive in episode 1. Industrial networking standards and protocols are very important. Basics of servers, operating systems, and computer-to-computer communications are super important as well. Industrial control panel design and electrical schematics, we talked about this a little bit earlier, but that is guaranteed to come up in a career as an automation engineer. Data reporting and logging, historian, SQL database, creating Power BI reports and trends. These types of things are also super important. And there's so much more, but not for lesson 1. So now you know a little bit about what it is, but is this in demand? Where could you work if you did this? And I honestly encourage you, if you're curious about that, to spend a little time on LinkedIn or just Google poking around and seeing if your favorite companies need an automation engineer. Because if you just type in blank company, automation and controls engineer, odds are something is going to pop up. They're very in demand, and because it's a slightly more niche field of engineering, if you have some of these skills, a lot of the time you can get an interview and get your foot in the door with some pretty big companies pretty quickly. While most of the time this job is not going to be fully remote, there are definitely a lot of hybrid opportunities out there, and pretty much every city in the world and every company in the world to some extent that does manufacturing or anything industrial will need some automation and controls engineering. So if you're heading to school and you're thinking about getting in this field, or you're an undecided major of engineering and you're thinking about going to this field, should you go specifically for controls and automation engineering? I would actually say not really. It's just my advice and you do not have to take it, but I think getting a mechanical engineering degree, an electrical engineering degree, a computer science degree, a broad field of engineering degree, and focusing on electives, school projects, and internships or co-ops that help get you in this direction is actually probably going to be better for you in the long run than looking for a hyper-focused degree like controls and automation engineering. I'm not saying you won't love the field of controls and automation engineering, but I am trying to say that a mechanical engineer who wants to get into controls can usually do it. A controls engineer who wants to go be a mechanical engineer can't usually just make that switch. And most places are looking for individuals with a 4-year engineering degree for their automation and controls engineering roles, but they're usually very open as to what specific engineering discipline those people have. And they're far more focused on finding driven and motivated individuals with some practical on-hand knowledge. So if you are an automation and controls engineer, what can you kind of expect your career path to look like? And the two most common types of controls and automation engineer are either an integrator or an internal resource to a company. And an integrator is essentially an engineering contractor. There are a lot of companies that don't have the internal resources to do large-scale automation upgrades and projects on their own. So companies like Rovasys, my first job, and other similar companies will be called into a big factory to do a large automation project. Integration can be very intense. It's project-driven, so a lot of the time there will be slower periods as you develop systems in the office, and then very intense periods of travel and long hours as you commission systems on site. But these organizations are often very focused on controls and automation, and they promote from within. So if your main goal is to rise to the top of a company, you might want to look for a company that is primarily engineers doing what you're doing, because your odds of making it to manager, director, senior levels are probably better at an integrator. But on the flip side, as an internal resource, there's often a much smaller team of automation and controls engineers. A lot of the time that comes with larger responsibility or more people looking to you to take on whole system ownership. At my second company, I was one of 2 controls engineers and the only one on site, so anytime an opportunity for automation or controls arose, it was on my shoulders. This was a mix of awesome responsibility and quite a bit of stress, but these organizations could be larger and much broader than just an automation firm, and for that reason, you could get tied up in your career path in layers of bureaucracy and find yourself kind of stalled as a senior engineer, unable to move into management or break any higher because you're at a company that does a lot of different things, not just automation. So now let's take a look at salaries and typical controls and automation engineering salaries. I want to caveat this with I am talking about US based. I don't have a good understanding of the international salary ranges and how they vary. If you've had a wildly different experience, higher or lower, let me know about in the comments below. So most interns and co-ops in this position are finding paid internships. They're kind of on the low end, the Midwest, maybe the lower markets for this field might find 16, 17, the high teens per hour, but there are internships paying in the high 20s as well. So most new full-time hires right out of school with an engineering degree doing automation and controls engineering can expect to be around the $70,000 benchmark. There are definitely companies hiring higher than that, sort of right on par with the average of most engineering disciplines right now in the US. Once you're in the middle of your career and you've been technical for 5 to 10 years, you can kind of know you're at a decent spot right now if you're around the $90,000 mark. Now, as you get kind of beyond the 10 plus years, there's kind of 2 paths at this point. You've entered management and you're like an engineering manager or director, or you're still technical like as a senior or lead engineer. Technical resources typically just make less money than management resources. That's the nature of industry. But even as a technical resource, once you're in kind of deep into your career, 10 or more years, you should be finding yourself into 6 figures in 2024. I consistently found that mid-career controls and automation engineers were averaging around $110,000. And this is where the ranges start to get really wide. And of course, if you're an engineering manager or director, you can expect to be outpacing that a little bit. Again, some things like stock incentives and bonuses cannot really be captured in these numbers, but if you're in management and automation and controls engineer, you can expect that you'll be doing pretty well. But kind of a truth of engineering is that you'll do very well for yourself, and it's not a path to instant and immediate riches. So it's a great salary, it's a good field option, but it might not be the single highest earning field that you could go into. And so that pretty much wraps up episode 1, Introduction to Controls and Automation Engineering. And I want to finish some free and cheap ways to learn more about the field. I have to first plug the Real Pars YouTube channel. It's kind of funny as a YouTube channel to tell you to go watch a different YouTube channel, but they have so many short videos on just individual concepts of controls and automation engineering. Almost their entire page is dedicated to controls. They have really compelling animations. They're not sponsoring the channel. I'm not being asked to plug them or anything. They're just a really good YouTube channel. And if you search anything like what is a PLC, they're probably gonna be the top or one of the top results. I really like the Real Pars YouTube channel. We'll see you next time. Good luck with your projects. Thanks for watching. Bye. In today's video, I'm going to show you the basics of the most important components of controls and automation hardware. In this video, we're going to cover everything from main power coming into a panel to power supplies and transformers to terminal blocks. Then we'll look at the PLCs, including inputs and outputs, as well as relays and networking components. There's no way to cover all of the intricacies you could see in controls and automation hardware in one video, but this video should hopefully give you a basic understanding of most of the core components you'll find everywhere in controls and automation engineering. Without any further ado, let's dive right into looking at a lot of these core components. First thing you'll probably notice is that every component I have is mounted to this specific bent piece of metal that's called DIN rail. Okay, and DIN rail, D-I-N, rail, is a specific standardized type of metal that is bent at a specific angle for controls and automation components to be able to easily clip on and unclip from it. Anytime you're searching for a component and you want to mount it in a controls cabinet, it's a good idea to look up a DIN rail mountable power supply, DIN rail mountable PLC. And ordinarily, all of the components you see here would be inside an industrial control panel, but I want to showcase a lot of it to you, so it's easier to just have it on a backer plane. Now, let's take a look at the power into this cabinet. I have it on this specific small piece of DIN rail just so that I could zip tie it for some cable management. But basically, I take a 120 volt power into the cabinet. If you have larger components like motor starters that might require 3-phase power like 480 volts, you'd need something a little heavier duty than what I have. But since I'm just dealing with 120 voltage or household outlet voltage, it's okay to just have it come in and land on our next components. Which brings us to the next component, which is the circuit breaker. Circuit breaker, which can sometimes be replaced with a fuse, is meant to be your panel's local protection against overcurrent. There's a lot more than we can cover in this video on properly protecting all of your components from short circuits, but you should definitely be aware that basically every industrial control cabinet is either going to have circuit breakers or fuse terminal blocks for the main power coming into your enclosure. Next component you see here is the 24 volt DC power supply. This is a really critical component because in modern industrial controls and automation, you see less and less stuff getting powered off of AC voltage. Low voltage is inherently safer, so dealing with DC is safer than dealing with AC in almost every application. And since the industry is moving towards DC voltage applications, you need a power supply that can step down AC to DC. Next, hopefully you see these wires coming out of the power supply, and I have them landing on these blocks here, which are distributing the power to multiple zones. These are called terminal blocks. And I have a whole bunch of spares over here. And what you can kind of see is that there's ordinarily plain gray or white or black, like a plain color. And those are just meant to be somewhere that you can land wires on one side and a partner wire on the other side of the same terminal block. You can think of them like industrially rated wire nuts. It's a spot where two different wires, or sometimes more than two wires, meet up, and it's best used for organization and keeping your cables manageable. It also can let you land inputs and outputs from a PLC on terminal strips in your panel, and then you have somewhere to land the wires that come from the actual devices in the field. So terminal blocks are super important. Green ones ordinarily correspond with a ground wire. Some variations on these, you can find some that you lift up and they have a fuse in them. These are known as fusible terminal blocks, which offer you an additional level of built-in overcurrent protection. You can also find two-tier terminal blocks, which have two completely independent circuits that you can use. These are great for very dense panels. And a lot of the times you can find terminal blocks with 3 or 4 multi-connections. These are really great for things like power disbursement or anywhere that you need one signal in a lot of places. Okay, the next thing we're going to zero in on real quick here are relays. In a time before PLCs, most of industrial controls was done using relays. They didn't always look exactly like this, but basically what a relay is something that can take an input electrical signal and transform that to an output of either normally open or normally closed wiring. And that output signal can be completely electrically isolated from the input. So for example, the relays I have on here can be turned on and off using a 24 volt signal, but they can be used to control 120 volt outputs. Now, in modern times, it's very unusual to see more than basic logic being done with relays. And the reason for that is the PLC. Programmable logic controller is able to read statuses into the device and control the status of field devices. When it reads something into it, it's known as an input. When it controls something going out from it, it's known as an output. If you're familiar with Arduinos or hobby electronics, you're probably familiar with this terminology. So PLCs are able to be programmed, typically using the 5 IEC 61131 programming languages. That numbering and acronym and abbreviation is a little bit unnecessary. Basically, the two most prevalent PLC programming languages are ladder logic and structured text. Ladder logic looks a lot like reading an electrical electrical schematic, while structured text looks a lot like a conventional programming language. I've done entire past videos on these programming languages, and we'll be covering them more in coming videos. So for the specific example I have here, I just have one input and one output hooked up to my PLC. And so for my input, I just have a simple push button, and when I press it, my PLC receives 24 volts on that channel saying it's energized, and when I release it, my PLC receives 0 volts saying it's de-energized. For my output, I have a conventional work light, just to kind of show you that anything can be used as an output. If it's controllable in some way from electricity, it can be a PLC output. For this specific application, to show using a few different pieces of electronics, I have the output signal from my PLC coming into a relay. So the PLC is outputting 24 volts. And then on the other side of the relay, when this turns on, you can see a little green LED right here. And that's when 120 volts makes connection with the wire going to the light. So my input of a push button tells the PLC, hey, I see this input. I programmed it to turn on that output when it sees the push button. So I press the button. It turns on the output channel from the PLC because of code that I wrote, which activates this relay because now it's getting 24 volts, which connects this 120 volt signal to the light. This specific application, it's obviously unnecessary to use the relay and the PLC in this circuit because a simple push button turning on and off a light on its own is not a great use case for a PLC and industrial automation. But the purpose of this video is to show you the hardware, not necessarily build an advanced automation and controls project. The last component I think it's important to cover today, because it comes up in almost every industrial controls and automation scenario, is the switch. In this case, I have an 8-port Ethernet compatible switch, which would allow me to connect things like my PLC or smart hardware like a VFD or variable frequency drive or any other networked components back to a master controller or my main laptop, which could be reading statuses from them, storing data in SQL, displaying values on an HMI, and things like that. Now, some of the most important components that we're not covering in this video are things like motor starters, VFDs or variable frequency drives, and HMIs or human machine interfaces, which for the programmers out there can be thought of as the GUI or graphical user interface, specifically for industrial controls and automation. But to speed recap what you've seen here, we've seen the main power supply come into a panel, which passes through a circuit breaker for overload protection, then goes into a 24 volt power supply, which then goes into terminal blocks for my power distribution. And then that powers my PLC. It also powers things like my relay, my switch, and it can be spread out using terminal blocks. Everything is mounted on DIN rail. When you need to convert signals from one type of voltage to another, you need to look for relays. And when you need to network lots of components together over Ethernet or other advanced protocols, you need something like a switch. Again, it's really hard to cover a lot of these advanced concepts without being able to show you them. So let me know in the comments below if this was a useful format or if you have other suggestions for how I can make this better. As I go through this controls and automation tutorial series with you, I want to constantly be making it better. So feel free to leave any feedback in the comments below. I'll link to some of the key hardware that I used here because everything I used here can actually be found on Amazon. I'll say in terms of learning resources that can help you build some of these skills completely for free, Rockwell Allen Bradley makes a tool called Connected Components Workbench. Beckhoff has their TwinCat programming studio. Arduino now has a PLC IDE or integrated development environment. And Ignition is one of the top SCADA HMI providers, and you can get their core software for free to use on your home laptop or desktop. All right, so that is going to do it for today's video. Don't forget to leave a like if you enjoyed it. Subscribe to the channel for tons more great content. Thanks for watching. We'll see you next time. Bye. Today, I'm going to talk to you about the top 5 tools I use as a controls and automation engineer. The video is going to be a continuation on the controls and automation series that I started up in the recent months on the channel. But today's video is going to focus on the tools that you would use as a controls and automation engineer. Now, without any further ado, Let's dive in. So the first tool I'm going to talk about is the digital multimeter. And in terms of basic electrical troubleshooting, it really doesn't get any better than one of these. They start as low as like $20. You can get one from Walmart or Amazon that does the basic functionality pretty well for you. Before you start working on high voltage or dangerous electrical systems, you should be far more qualified than just saying, hey, I've got a multimeter. But these can do things like detect whether or not there's voltage at a source, tell how much voltage there is relative to ground, check for AC and DC voltage. You can even lift a wire and you can calculate amperage through current. You can detect point to point if you have continuity, which helps you when you're trying to trace wires in a jumbled old electrical panel. And you can also do resistance checks, which help you detect for like partially blown fuses and things like that. But digital multimeter is a great tool to have around, not just if you're a controls and automation engineer. If you do any sort of hobby work or tinkering or electrical work around your house, which you should also be very careful with, then a digital multimeter is a great call. This one came in a soldering kit that I bought from Amazon, and I think the whole kit was like 40 bucks, and it works great. It's very reliable. Kind of the more robust industrial version you'll probably see a lot come from the company Fluke. And the only reason I have one for personal use is because I renovated a house and I was doing a lot of home electrical. So I decided to go out and get a more industrially hardened one. It's not necessarily normal that you would have a Fluke for home use. Your company might just have 2 or 3 to loan out because they're more on the expensive side. But every engineer who is doing significant work in a control panel should have a Fluke or digital multimeter because it tells you so much about the status of your electrical signals. This isn't moving on to item 2 yet. This is item 1.5, but in the same kind of vein of testing and validating electrical signals in a panel, I think a voltage pen is something for anyone who is doing anything near any electrical circuits. It's something valuable for them to go out and get. They make these in AC and DC in one pen, so you can check if a circuit is live, whether you're working on DC or AC circuits. They make some more advanced ones that can tell you additional feedback, but the main purpose of a voltage pen is that when it's on, it will start blinking rapidly, like an LED will flash red if there's voltage present, and it'll start beeping at you if there's voltage present. So you can hold this up to a wire that you're about to take off of a terminal that you don't think should have electricity flowing through it, and if it starts beeping with a voltage pen, that's a really good first check that you were about to do something pretty unsafe. So with voltage pens and multimeters, we've covered electrical troubleshooting and the most common tool used for that. So the second tool I'm going to talk about, and this one should be kind of obvious if you're familiar with what controls and automation engineering is, but it is the wire strippers. So a pair of wire strippers are typically capable of cutting a piece of wire and removing the shielding from it so you get the bare copper on it. And it might seem really obvious that if you're doing any work in a control panel, you need a pair of these on hand, but I can't tell you the number of times I've gone to a project, I've had a young engineer with me, and they haven't had a pair of wire strippers. They didn't realize that they needed them. But it's just useful to know you will need your wire strippers pretty much constantly. There are super high-tech versions of these. There are also cable strippers, which when you have a cable that has 4 or 5 core of wire inside of it, it can grab the sleeve and pull it off of all of your 5 wires that are inside. So this can get way more complicated. And I'm kind of lumping like sets for crimping ferrules, which are nice like metal tube ends that clamp onto the copper on the end of your wire. I'm kind of roping all of the wire prep tools into you can get by with a pair of wire strippers, and sometimes you might want like a box cutter type knife. If you do have a cable, or if you're doing Profinet cable, which is really shielded and has a thicker edge to it, and you don't have the specific tools meant for crimping that style of cable, you can usually get by with cutting a slit in the edge of the shielding, peeling it back, taking the individual wires out, and then you can just strip them if need be with your wire strippers. So in my opinion, wire strippers and a box cutter can get almost any electrical work done that you have to get done, but just know the world of wire prep is actually way deeper than that, and we could go on for a very long time about the right type of ferrules, when to use splicing and heat shrink, the different types of wire nuts or terminal mounts and things like that. but we're going to keep it simple. You absolutely will want a good pair of wire strippers. Now, item number 3 is something that might catch you a little by surprise if you haven't done significant work in automation and controls engineering, but I would recommend any engineer who's spending significant time in the field or bench testing stuff in the office get themselves a 120 to 24 volt power supply. If you're in the UK or internationally, you might want to get yourself a 230 to 24 volt DC power supply. But the important point here is you're taking single phase voltage, you're taking the most common type of wall outlet voltage, and you're turning it into the most standard DC type of control voltage, which is 24 volt DC. You are going to be stunned by the number of times having one of these on hand or in your bag is super useful. Some of the most common reasons you might need one of these power supplies is there could be a lot of scenarios where a control panel was designed with high voltage, 3-phase, 480 or higher electricity in the same cabinet as switches and PLCs and HMIs. And strictly speaking, if you're going to be working on anything with that 480 voltage live, you should be in full arc flash gear every time, even if you're not touching the 480 side of your cabinet. But it's not always conducive, it's not always realistic to say that you're going to be arc flashed up, so sometimes it's better to just kill the power to the cabinet. But then you run into the problem where if you kill the power to the cabinet and you're using that in-feed power to power the lower voltage things as well with a 480 to 24 volt or 120 transformer, now you need some way of powering on the PLC, powering on the switch, powering on the HMI so that you can do troubleshooting and service with a power supply that is fed from somewhere else. So one of the more common, more scrappy things that you might do as an automation engineer is get a really long extension cord, find a nearby outlet, power up a power supply, and then you can have all of those lower voltage things like the PLC and the switch online. You can do your software-based troubleshooting. You can even do wire validation with the high voltage components powered down. Some other formats that you might see power supplies in, and again, like your company might already have one on hand, your customer might already have one on hand. These are kind of common, although not super frequently used in the US as far as I know. They're just like a metal box that has the circuitry for transforming the voltage on the inside, and then little terminals with a plastic shield. They do exactly the same, it's just a different way of looking at it, but it's nice to know what you're looking at. And it's also worth noting some of these can take multiple input voltages. So this one, for example, can work with 120 or 230, but you have to adjust a dip switch to tell it which one it's getting. And they also make these that output 5 volts DC, 12 volts DC, 24 volts DC, so make sure when you're specifying it, you get the right one. If the majority of the work that you're doing is bench testing or in like a garage environment like here, where I want to make sure something works the way I'm expecting it to work before I power it up permanently and buy a power supply just for that circuit, an adjustable DC power supply is a really tremendous tool. I don't think you would throw this in your book bag and keep it on hand as an automation engineer doing a lot of work in the field. You absolutely could. There's no reason not to. This would be able to do exactly the same thing that would be able to do, as long as you get one that's able to output 24 volt DC. Most common thing you would want is 120 volts in or single phase household voltage in, and then 24 volt DC out. That will let you do a ton of great troubleshooting and give you a lot of flexibility and the ability to make working on systems way safer. Now, item 4, I thought about roping in with item 2, which was all of the wire prep stuff, but I decided it's important enough and different enough that I'm going to make it its own topic, and that is the terminal screwdrivers. So when you're wiring up stuff in a control panel, the most common thing you'll see is a screw clamp terminal base. Some plants, some people trust the spring clamp terminal bases as well, which is basically you push down a lever, you put the wire in, and you release the lever, and now you have a spring clamp on it. But the more common one to see, honestly, especially in older plants, is screw clamp terminal bases, where you have to tighten down a screw to clamp onto the copper. This is sort of the most common way to land anything electrically. And what's surprising and annoying is just how tiny the terminals can be on those. You might think that you have a very fine screwdriver, but if all you've ever done is around the house home projects and home electricity, I promise the smallest screwdriver you have will be way too big for the terminals used in an industrial setting. So what's nice is when you can find a thin screwdriver that's rated, this one for example is up to 1,000 volts, and they're incredibly thin. They have very thin, typically flat heads. So a terminal screwdriver, it's not expensive, it's incredibly important, and you would not believe this is an example of terminal blocks. These aren't even close to as small as they come, and this terminal screwdriver is already almost too large to fit in these terminals. So having a set of very fine electronic screwdrivers is super important. And now it's time to talk about number 5, the final most common tool that you will need as a controls and automation engineer. And I saved it for last because it's a little bit of a tough one to show, a little bit of a tough one to talk about and explain, but I'm going to do my best. And I figured if you made it to this point in the video, you probably don't hate me enough to click away as I try to explain this rather complicated concept. But tool number 5 that you will absolutely need as an automation and controls engineer is an engineering laptop. And the reason I specify engineering laptop is because your work will probably give you a laptop that has a whole bunch of IT settings on it. They might not let you change your IP address. They might not let you download software from the internet. They might not let you have admin access to your laptop. That is going to be a huge deal breaker for an automation and controls engineer. So it's very important that you have a lot of RAM. 16 gigabytes is probably the bare minimum. 32 or definitely 64 would absolutely be preferable, because one of the most common things that you would do as an automation and controls engineer is you might have virtual machines, which are basically virtualized sessions of a computer that has certain engineering software loaded onto it that you open using the brains of your computer. So if you're running a laptop that has 16 gigs of RAM and you want to open a virtual machine that needs 8 gigs of RAM for it to be able to run, you've just reduced the actual memory your laptop is capable of using to do other things to 8 gigs right away, because now half of it's been dedicated to opening a virtual machine. If the virtual machine concept confuses you a little bit, don't worry about that too much for now, but just know that there are engineering softwares like TIA Portal for Siemens or Studio 5000 for Rockwell, where depending on the task that you're doing, if you're online with equipment, if you're trying to make live edits to programming, you could easily be using 8 gigs of RAM just running certain projects. TwinCat for Beckhoff will just gobble up your system resources. So if you only have a laptop that has 16 gigs of RAM or is super locked down by company permissions, you're going to have a very hard and annoying time as a controls and automation engineer. If you're at a company that only has a few automation and controls engineers, it might be hard to properly articulate to them how badly you need a really open laptop. But it's super important that you be able to put any required software to support bringing up your system on that laptop. Of course, you should still follow info security protocols. You should still have IT vet software and make sure it's not coming from malicious parties. But if you're not able to change your IP address, download bootp, which is capable of just setting IP addresses, in theory, it never works. But then if you're not able to go and grab the software you need to program a drive or a VFD or any smart component in your system where there's a little package or plugin on the vendor's machine website, and you're not able to quickly get it, it is going to slow you down. You'll have to open a ticket. You'll have to cuss out the IT department every time, and nobody wants that. So just make sure that if you're an automation and controls engineer and you are spending a lot of time in this field, you go through whatever steps are required to get yourself an engineering laptop, admin access where you can quickly change your IP address and network settings, be able to download software that you deem is necessary to do your job, and make sure that it has a lot of system RAM. So make sure it has a lot of memory. And in addition to a lot of RAM, preferably at least 500 gigabytes or maybe a terabyte of actual disk memory, because some of those software that you need to program PLCs take up a ton of install space as well. So I know it might seem silly in 2024 to say that a laptop is one of the most important tools that you'll need as an automation engineer. Like, of course you have a laptop, but this very specific type of like an automation and controls engineering laptop, to go out and get a beefy laptop and make your company pay for it. That is going to do it for the list. That is going to do it for today's video. I hope you found it useful. As always, good luck with your work, good luck with your projects, and I'll see you next time. Thanks for watching. Bye. In today's video, we're going to talk about the IEC 61131 programming languages. These are the 5 standard programming languages you're likely to see as an automation or controls engineer. So hopefully this video can answer some of the most common questions around what these are, what programming languages automation and controls engineers need to be ready to see in the field, and then also how likely you are to see them and what different applications you might use different ones for. I know just the name IEC 61131 can be a little bit confusing, but IEC is just International Electrotechnical Committee. They are sort of regulators and moderators of a lot of specifics and standards in the world of industrial electronics and controls and automation. You don't really have to worry too much about the numbers or the letters. You just need to know what these different programming languages are and when you're most likely to encounter them in the field. So let's start with my personal favorite and potentially the most common one, which is ladder. So ladder diagram, ladder logic, or just sometimes abbreviated LD, is essentially the first PLC programming language that ever came up sort of organically, because it looks a lot like electronic relay schematics. So in the old days before we had PLCs dedicated to running automation, you would read sort of primitive controls maps as schematics of different relays. So you could, for example, have a relay that would check to see if a button was pressed and if maybe something in the field like a high pressure switch was met. And if those were both true, the relay would pull in and then something else would happen downstream of it. And so a standard programmer might think of this as like a series of and or gates to do like binary logic. In ladder logic, it's almost like you could trace a flow of electricity through your program. So this is why ladder logic looks sort of like a ladder when you stare at it. It's rung after rung after rung, and the individual modules all sort of spawned from the idea that you had relays. So the two most common ones are like examine if close and examine if open, which is basically a if or an if not. So it's basically if condition is a 1 or if condition is a 0. And that's 90% of how you do Boolean checking, just series of ifs and if nots. And then to turn on Boolean conditions, you really just need to know the difference between like an OTE, which is a energize the whole time this rung is true, versus like an OTL and an OTU pair, which is latching and unlatching a binary condition when something is true. Now, obviously processes are a lot more complicated than binary logic in a lot of scenarios. So essentially what that means is you also have things like greater than, less than, limits where you check between values, and then you can also move numerical values into numerical variables. So you don't just have binary logic in ladder, you have all the sort of standard formats that you'd have in any other programming language. If you understand general programming types, you'll be able to pick up what these separate variable types mean pretty quickly and pretty easily. But ladder logic is extremely common. It's also super powerful, and it's pretty easy for people who don't have a computer science background but maybe are more familiar with the electronic side, or frankly they don't have a programming background at all. Ladder logic is super logical. I really like it. Almost every major PLC manufacturer supports some form of ladder logic using these same basic building blocks. So as a controls and automation engineer, you are super likely to need to become pretty familiar with ladder logic. Now for the one I consider second most common, some people might debate with me here, but I think the function block diagram, it's essentially more freeform than like traditional ladder logic. You just basically have a blank page of workspace and you drop blocks blocks in there that you want to do different functions, and typically you tie their inputs and outputs to different process conditions. Some of the more common ones for this would be like totalizers. A lot of the time a totalizer block that would monitor flow over a period of time and continually add to see how much total flow you had in that time. You would maybe have this floating function block diagram for a totalizer. You would tie a start command, a stop command, a reset command, as well as potentially like your input signal, so your actual raw flow meter signal. You could pass it through some sort of like time scale or multiplier, but it's just where having all of the conditions that control the totalizer and all of the outputs that you could do using the totalizer in one spot is just super powerful. I'm only using totalizer as one example. Function block diagram, its advantages are you can see all of the components that will control a block, a complicated block like a totalizer, in one location. You can also map out common programming things like AND gates, OR gates, XOR gates, NOTs, whatever, Boolean control in these as well. The disadvantages are it starts to get very hard to read a logical sequence of things happening if you get too far down and too long into one function block diagram. So you need to start partitioning it off and making a separate FBD for each major function that happens. But I have seen systems where the entire thing is done in function block. I've seen things where the entire system is done in ladder. But it's important to understand what this looks like, how you control it, what it's used for, and also it's an important one to familiarize yourself with. The next language, SFC or Sequential Function Chart, is absolutely the most common language you'll see if you run batch processes. So GE's like FT batch and Rockwell's batch, as well as I think just a lot of batch processes. The way you see a recipe is with a sequential function chart. And this one's really nice to kind of get an overarching view of your process, because typically you'll have layers where you can look at one SFC and you'll see like start phase, validate parameters phase, manual additions phase, mix phase, automated additions phase, sample phase. And so you can look at a high level SFC and you can see the overall state of your project really quickly as it relates to your whole process. And then if you have questions about what's going on in one phase of that SFC, typically most software supports you drilling in, and inside one phase at your high level model, you could have a number of phases. And inside each of those phases, you could have a number of phases in there. It's definitely most commonly used in batch. Most PLCs themselves don't support a really robust like SFC without a software that you run and configure on an actual computer. So PLCs typically host mainly like ladder and FBD, and even some of what we'll talk about next, which is structured text. But to do an SFC based control schematic, you're usually in like more of a distributed control system like DCS platform, and you usually have to put your SFC software, recipe editor, whatever, on a computer other than your PLC. Again, most common place you'll see it is batch applications. Batch just means that you separate all of your devices at the plant and your series of instructions that control devices into phases. Phases still typically have to get represented as ladder in your PLCs. So an SFC is almost always accompanied by some form of ladder logic or structured text inside of a PLC. Not always. I'm trying to generalize and give you guys a quick summary, but that's a summary of SFC. So the next one, structured text, is probably the one that would look the most familiar to someone coming in with a programming background but not a controls background. Structured text really is what all programming languages are. I mean, it's a certain syntax of words and commands that will execute certain things in your code. Structured text is typically straightforward, like saying set IO point status to digital output, set Boolean command equal to 1 when condition is met. Like the actual text, I'm not going to spend too much time digging into because it varies from manufacturer to manufacturer, controller to controller. So if I were to tell you a bunch of specific structured text, there's a solid chance it wouldn't apply to your specific manufacturer. But the documentation for what your manufacturer supports, whatever your site standard is, if you're doing a lot of structured text, then the controls at your plant probably got started by a group of people who are more comfortable with software and programming. So in general, PLC programmers, controls and automation engineers aren't going to need to see a ton of structured text, but it is supported and it is one of the IEC 61131 languages. So it's important to know what it is. If you see it in an application, don't be blindsided by it. Not super common. If it's super common at your site, you proved me wrong. Let me know I was wrong in the comments below, but most of the time, the three we talked about before are gonna show up a lot more in your applications. Okay, and the fifth one is kind of neat here. It's instruction list, typically abbreviated IL. And this one is gonna be really familiar for people who have done a lot of work with like 6-axis robots, or if you've done a lot of work with like CNC machines or 3D printers. Instruction list is not too far off from structured text in that it's really just words that kind of have some numbers mixed in to command your variables to different stuff, whereas the first three languages we talked about were a lot more visual. But instruction list is basically like machine code. So for like a robot or a CNC machine, it's often called G code, but it usually is a series of commands that run one after another. It's always gonna typically happen in sequence, but a lot of the time you can have like, oh, if this condition, then do this and jump to this rung, but if other condition, do this other thing, jump to this other rung. So it doesn't have to be linear, but typically it's in an order that makes sense that you would typically see it sequentially. And the most common applications are for things where you need position control in 3D space. So you're controlling 3 or more axes, and you would typically say, okay, go to certain position. All right, turn on your tool, whether it's cutting or drilling or welding or whatever, and then your tool's on. Okay, move from point A down to your thing that you're operating on. Okay, now move over to point B with your tool on. Okay, now turn your tool off and lift up. Okay, now go back to your home spot. A conveyor will turn on, move the next piece in. So it's pretty common on like assembly line where you have a lot of advanced like robotics or motion control. It's normal to see instruction list, but again, this is sort of more common in robotics even than you would see it in controls and automation. So it is one of the IEC 61131 languages. That's why we're talking about it. And in general, the more well-rounded you are as an engineer, the better you're gonna do in your fields. Good luck with your jobs, good luck with your projects. Thanks for watching. Bye. This is the Arduino Opta PLC. PLCs are pretty well known for being hundreds or sometimes thousands of dollars because of their industrial ratings, and often the software and the licensing accompanied with them is hundreds or thousands of dollars as well. Arduino has created a compact microcontroller that has relay outputs and digital inputs on board, as well as programmable buttons and LEDs so that you can learn the basics of controls and automation or build IoT and industrial automation solutions for just a couple $100s. And for myself as a creator and the person who runs Lemaster Tech, I'm really excited about this product because it gives me a way to teach the basics of controls and automation engineering, which is the field I work in professionally and something I feel quite passionately about, at a price point finally that's pretty accessible for anyone who's looking to break into this field. So in today's video, I'm going to walk you through downloading the PLC IDE from Arduino, getting online with it, and creating your very first project, because in the coming videos on Lemaster Tech, we're going to be doing progressively more advanced controls and automation tutorials, and being able to get started with the Arduino PLC is going to be very important if you want to follow along with all of those tutorials. So let's get right into it. All right, let's go ahead and just pop the Arduino PLC IDE into Google. And the Arduino software link to the PLC IDE, the big button that says download the PLC IDE. I'm going to download the Windows version, and I encourage you to contribute and download. Arduino's a pretty awesome company. I'm going to just download because this is like the 5th time I've done this. Arduino's pretty awesome, and they give their stuff away for free, their software stuff. But let's go ahead and install the PLC IDE together. I'm going to check yes to launch it once it's done, and I'm going to hit finish. Okay. Alrighty, so it looks, even though I just downloaded it, it can remember that I did some programs here before, which is fine. I'm just going to hit new project anyways, and I'm going to name it my first PLC. And make sure your target is the Opta unless you're using the Portenta machine control. But I'm going to use the Opta. I'll just put it in documents is fine, and I'll hit OK. It's going to take a minute to generate the project. All right, then the device shows up here. First thing you want to do with the new Arduino PLC that you have plugged in, you want to go to Device Manager on your computer. Make sure you know what port your PLC is plugged into. I'm almost sure mine's USB 13, but I'm going to go ahead and unplug it. And I see 13 goes away. Plug it back in, and 12 and 14 come back. Interesting. Okay. So this one might be in a weird state of limbo. That's like it got half booted before. So I'm going to double click the reset button that puts it in firmware reboot mode. So if your PLC is brand new out of the box, you should only have one USB serial device port here. So COM13, we're going to come in here and select that. And the first thing you want to do, regardless of the fact that you haven't written any code yet, is just on port COM port 13. You just want to hit download. It's for initial setup and reinitialization. It tells you on a new board, file system formatting can take some minutes. It takes some minutes, so just get it started. Really all you're looking for, you want this bottom left window to keep doing stuff. You don't want it to freeze and hang up, but it does take a couple minutes, so I'll probably fast forward much of this or play games on my phone. Okay, and you want file downloaded successfully, that's good. Anything that's like, hey, DFU, invalid suffix, stuff like that. Your Arduino PLC IDE might have gotten incorrectly downloaded. You might want to go to the Arduino IDE and install the Opta libraries. You might want to try double pressing reset on the Arduino Opta to get it to go back into bootloader mode and try again. Double check your COM ports are correct with Device Manager. Those are all the troubleshooting steps that I know of because I've gone through very similar things. But ideally, if that works and you go to Device Manager and ports, you now have two ports because this is a dual core PLC. So there are two USB ports in use to communicate with it. So you have 12 and 14. You want to go into online and set up communication and go to Modbus and properties. And you want to grab the higher of those two ports. The rest of the defaults should be fine. The baud rate, the frame, all that stuff. Hit OK. Hit OK. And now you want to connect to the target. So I'm actually just going to unplug and plug back in the PLC for my little, hey, I'm IT, this is how I do things. I don't think you have to do that, but go back to unload online, setup communication, Modbus, COM14, that all looks good. Okay, and now there's nothing in main except count equals count plus 1. That's the default program Arduino gives you. But when you are in resources on this header page, you want to connect to the PLC. Even before downloading anything to it, you're just connecting to make sure that all the setup stuff worked okay. It'll take a second. Okay, now I've previously licensed this, but initially yours will probably tell you that you need to disconnect it and connect it back for the permanent license to take effect. One really cool thing that Arduino does that most industrial PLC IDE providers do not do is they include a permanent license for your PLC with the purchase of the hardware. So for about $200, which is not nothing, you get a micro PLC that has relay outputs as well as programmable inputs that can be analog or digital inputs or more outputs if you need them to work that way. It can also be clipped into expansion I/O modules, which makes it a lot more useful and flexible. And then a permanent license, because Even the more affordable hardware providers, Beckhoff, Wago, Siemens, have some more affordable PLC lines. They get you with licensing their software as well. So really, for getting into the world of industrial automation and controls, this is a pretty crazy affordable option. So you should have all green. Not every Opta has Wi-Fi and Ethernet, so depending on the version you bought, these might not all be green, but mine does. So let's go to main, which is just the default program. Okay, now I'm just going to go to talk about the two tabs that they kind of give you by default. They give you project and resources. In resources, you can see the Opta that we added. And in later tutorials, I have some IO expansion modules. You'll see where we add those as well. So we have even more inputs and outputs we can play around with. But the Opta, right on the body of the main PLC, it has a channel of inputs on the top. It has relay outputs on the bottom, and then it has 4 status lights for L1, L2, L3, and L4 at the bottom. And then it has a red, green, and blue LED all here. And then it also has button inputs. So we're going to use these in future videos. For now, the only thing I'm going to do is I'm going to go to LED outputs, and I'm going to give LG, which is the green light, a variable name called green, so that then we can go over here to projects. And in my first PLC project, I'm going to add a new program. I'm going to make it structured text, and I'm just going to call it green light. Okay, and I messed up because you need to assign it to a task. So I'm going to delete that real quick and show you what I mean. Add new program. We'll just call it green light. We'll make it in structured text, and I'm going to assign it to fast. Okay, so now it doesn't have a question mark over here. And all I'm going to do is say green and then colon equals sign true all caps and then a semicolon. Okay, and you can see right now there's nothing on my PLC. I'm going to hit download and compile, and the green light turns on. Okay, so this was not a PLC programming tutorial. This was getting started with the Arduino Opta PLC tutorial, because we are about to do a whole bunch of ladder diagrams, structured text, hooking up inputs, hooking up outputs, building HMIs, all the stuff that turns you into a controls and automation engineer. We are going to do that, and we're going to use the Arduino PLC IDE and the Arduino PLC itself. So super important to go through the basics together. If you're running into problems with this, do not skip this and go forward to the next few videos. If you're trying to truly follow along with this tutorial, you really need to be able to get online with your PLC and at least make sure that you can turn that green light on and off. Otherwise, you're going to be trying to follow along with tutorials in this series that will show you useful information and useful concepts. But if you're not online with the PLC right now, the rest of the tutorials will mainly just be for your information, but they won't be practical exercises together. So thank you so much for watching. The tutorials are really going to take off from here, so I hope this basic setup was useful for you. Let me know in the comments with any questions. We'll see you next time, and thanks for watching. Bye. Okay, in this chapter, we are going to make a new project, and we're going to call it First Structured Text. Okay, so we're going to go new project. Make sure you have the Opta selected if you're using the same controller as me. And we're going to say, okay, it's going to generate a new project. Now, I have previously loaded the firmware onto my Arduino, so everything else here should be fine. We'll go to Online, Setup, Communication, Modbus, and Properties, and just make sure COM10 is still selected. That looks good. And we're going to hit Connect just to make sure that connections look good, and the all PLC Arduino Opta still looks good. All the available interfaces should show green lights. So this is all good. Hopefully, in a previous video and previous chapter, if you're watching a long form tutorial, I covered all of this stuff in some greater detail. So if you haven't gotten to this step and you're not able to get online with your Arduino Opta PLC, I suggest you go back on the channel and you watch the getting set up or getting started with your Arduino PLC video. Assuming you can get to this step and you have a new project just like I have, and if you were to go into the project tab over here on the left and hit main, you just have this default program it gives us that is count equal to count plus 1. But if you're able to get this far, then we're in the same spot, and the rest of this video is going to go so smoothly. So let's go to resources, because for today's video, I'm going to use the LEDs that are built into the Arduino Opta, and I'm going to use the user button, which is on the front of the PLC. So you could see there, actually, when I was pushing that button, it was doing stuff. That's because I have different code on there, as shown by this diff code thing in the bottom left of my window right there. So maybe I'll hang out right there so you can see my tab. But right now, I'm going to go ahead and just download this empty PLC program to it so that there's nothing on my PLC, and then we'll be in exactly the same spot. So, compiling sketch, please wait. I will wait for you, Arduino. Okay, so once you get source okay, or you might have had nothing, but in this case now we have PLC that has nothing on it. Pushing the button does nothing, the lights are not there, the green light isn't even on. You would not know anything was working on this. So let's go to the resources and click on the Opta. This should still look good, but since we're using the button and the LEDs that are on the Opta, we're going to add variables here. So the name of them is just kind of how you identify what the button is. There's one push button on the front of the Opta that is programmable. The other one is the reset button, which is used for like factory resetting. So there's only one button on the front of the Opta we can use. It's the user push button. So I'm going to assign it a variable name that is just going to be user, all caps like that. Now I'm going to go to LED outputs, and I'm going to do basically the same thing. L1, L2, L3, L4, LR, LG, LB. And so this is my exist, but it's not automatic. That's fine. LR. Okay, it's really unhappy. Oh, mercy. Okay, I'm going to call this red, green, and blue. Basically, you need to assign variable names to these hard-coded inputs and outputs so that we can use them in our program. So we have L1 through L4 refers to the 4 status lights at the bottom of the Opta, and then red and green show up in the same spot above the reset button, and blue shows up right above the user button. So we're assigning all those variable names so that when we go to write our program here in main, we have user and all 7 of those lights that we can play around with. So let's write functionally what can be considered the hello world, the intro to programming for structured text. Let's say green equals true. And a couple important syntax things here is green colon equals is how you set a value equal to true all caps, and then a semicolon. So for structured text, it's variable that you want to change the value of, and then setting a value is colon equals, and then the value you want to set it to, and then a semicolon. And this should compile and download, so I'll hit this little button for download PLC code. It'll ask me if I want to compile it, say yes, and now if I hold up the PLC, the green light is on, okay? So that's my hello world right there. That's the green light is on, I am talking to the PLC, and it is listening. Now let's go ahead and go a little bit further. Let's say that red will be equal to false. By default, it'll be off, but let's go ahead and say blue is equal to user, okay? So you'll notice the colon equal sign for all of those and the semicolon at the end for all of those. And all I'm doing is making sure the red light is off. But the blue light, I'm doing something a little more interesting here. I'm saying it's equal to the value of user. And I'm going to do something here. I'm going to add all of these values to watch. Just by right-clicking on the variables that I want to watch. I'm going to add them to watch. And I have this window over here. That's the watch window, and it shows the current value of them. The current value of green is true because my original code was just green equals true. So now if I download and compile this and then hold the PLC up, you'll see green is still true, red is still off, and that's all good. But if I go ahead and push this button, you'll see the blue light turns on. And if you're watching the watch window here, you'll see user and blue change when I push the button. Okay, so that's actually, it's pretty cool how fast we're able to advance through this PLC programming tutorial. We are now controlling the state of an output from an input. So the input being that user push button, blue being the output light. But you're not really learning too much structured text with this. We're just directly setting values based on other values. So let's go ahead and take a look at an if-else-if statement. Let's say if the user push button is pressed, so if user semicolon, actually if user then and no semicolon, I get my Python, my C++, and my structured text syntax is messed up. But here we're checking if a Boolean value is true. So it's just if user, so if the user push button is pressed, then let's go ahead and set L1 equal to true. And let's go ahead and do L2 also equal to true. And let's just make sure that L3 is off when the push button is pressed and that L4 is off when I push the push button in. Now I'm going to do else if not user. So this is about the same thing as an else statement, but I think it's important to call out that else if in structured text looks a little different than most programming languages. So it's this ELSIF and then not user. Then, and you'll notice if user then and else if user then don't have semicolons, but all these command lines do. So I'll copy these 4 instructions here and I'll shift tab, there we go. I'll change L3 and L4 to the ones that should be on and L1 and L2 to the 2 that should be off. And then super important in structured text, you need end underscore if and then a semicolon, okay? So unless I missed something important, which is perfectly possible, this should make the bottom 4 status lights flip-flop once it's downloaded, okay? So actually, good sign, you can see that 3 and 4 turn on with the button not pressed. So I'll go ahead and press the button, and there you go. You can see all 4 of the status lights on the bottom of the PLC, as well as the blue light, are changing. Okay, so that's cool. That's if, an else if, and an end if statement. But again, it's all pretty straight up Boolean binary comparisons. So let's add one more thing here for this introduction to structured text. Let's add a variable and do a little bit of sequencing, okay? So let's go into project and global variables, double click, and I'm going to insert 2 variables here. I'm going to call one last underscore user, and this is going to be a Boolean that I'm going to use to track the last state of the user push button. So similarly, if you've done anything in Arduino or other programming languages, sometimes you want a condition that only happens on the rising edge of a value. And to do that, you want some sort of variable to track the last state of it. And then at the end of your routine, you'll set last user equal to user. And then this second variable, I will just call position, and I'm actually going to make this an integer. And I'm going to say initially I want it to be 0. Initially, I'll have this be false. False. So those are just initial values. Come on. There we go. Oh, I have caps lock on. Okay. And I'm going to use position to track where in the sequence we are. And here I'm going to give it an attribute called retain, which means on downloads and power cycles, it's going to keep its value. So that's a useful thing when you have some sort of PLC program that you want to hold values even when you download new iterations of the code. You want it to be set to retain. Okay, so we made a few new global variables that we can use in our code. Let's go back to main, and we're going to scrap most of this, all of this really. And let's go ahead and start by setting L1 through L4 all equal to false here in the beginning. And a little way that structured text programming works is this code is going to go through and set all 4 of these lights equal to false at the beginning of each scan, but it's only going to matter what the value of it is at the end of the scan. So if you had code here that said green equals true, and then you added a line here that said green equals false, within your code right here, you're changing the value of green to true and then to false. But what's going to happen, the only thing that would actually happen if you ran this code, so let's just do it, is, whoops, there we go, is the green light will be false. All the lights will be false. It doesn't show green turning on and then green turning off, because the only thing that executes is the value of the variables at the end of the routine. So by setting L1 through L4 false at the beginning, we have the rest of this code to decide if we want to turn L1 through L4 off or on. So what we're going to do is we're going to say if position is equal to 1, then I want L1 equal to true, okay? And a couple things to call out here. In structured text, the comparison is just single equal sign. Most programming languages that you've probably seen before, 2 equal signs is how you check for equality. That's definitely how Python works, and that's my favorite. So then we're going to say else if position is equal to 2, L2 is equal to true, and then we'll say else if position 3, L3, else if position 4, L4, and then we'll say else if one more thing, and then I'm going to end if. Okay, so let's just get this all lined up. Position 3, 3, position 4, 4, and now let's say else if position is greater than 4, then what I want to do here, then what I want to do here is say, okay, position has exceeded my max step, so I'm going to set back to 0. I'm going to put back to the beginning. And notice that the if-thens don't have semicolons at the end, but end if does, and all of the action lines in each if condition do have semicolons. Okay, so this is great, but nothing's actually changing the state of position yet. So let's move this down a little bit, and let's say if the user button gets pressed, and it's a rising edge. So not me holding down the user button. Let me say this is just when user first gets pressed. So if user and not last user, then I want position to be equal to position plus 1, and then end my if statement. And I missed a semicolon there. Then at the very end, like we talked about, we're going to say last user set it equal to the value of user. Okay? So this should be all we need. This is setting the initial values of all of our lights. And just to make sure this new program really took, let's go ahead and say we actually want red to be on now, and we're going to turn green off. So when this boots up, if it's working properly, we'll know right away from red being on and green being off. Let's see if we made any errors. Looks good because I'm a professional. And the red light's on, nothing else is on, which makes sense based on the code that we wrote. And let me try to get this framed properly. I'm going to push the button, and the blue light turns on, and position 1 turns on. Push it again. Position 2 turns on. 3, 4, 0. 1, 2, 3, 4, 0. Okay? And you can add position to your watch window, add to watch, as well as last user if you really want to, as well as L1 through L4. And now as you're cycling through pressing the button, you can see the value of position change every time you push the button. And blue user and last user all change almost exactly together. But so that's really fun. That's basic sequencing. A very common way to write controls sequencing is in step 1, do a series of things, and then once you've checked some condition like pressure, flow, temperature, move to step 2, and then do a series of things in step 2. So this sort of sequential move through a position value is actually a really great introduction to PLC programming. So that's some basic structured text. I think up next we'll sort of recreate this program in ladder logic, so you get to see both of the main sort of 2 PLC programming languages that sort of duke it out for ultimate control. But I hope you found this introduction to structured text programming useful. The Arduino Opta is a really cool, affordable way to get into PLC programming. Thank you to Arduino for providing the hardware for this video. I hope you learned something with this structured text tutorial. Let me know what you want to see next on the channel. Thank you for watching, and we'll see you next time. Thanks. Bye. Hello and welcome back to the channel. In today's video, I'm going to show you how to make your first PLC program in ladder diagram. This is a super popular, super common PLC programming language, and to show you how ladder diagram works, I'm actually going to show you the structured text program that I built in the last tutorial, and I'm going to convert that exact program from structured text into ladder line by line with you. But I wanted to show you what the program does first, because ladder is a very visual programming language. And it's pretty different from C or Python or C#. So if you're getting into programming for the first time, that's not a big deal. But if you've been a programmer for a while and you're getting into controls, this is a more useful way to learn it, in my opinion. So the code that you can see on screen right now does the following to the PLC. The red light is always on. I have a green status light up here that is always off. And then the blue light turns on when I push the button that's under my index finger. So when I push the button, the blue light turns on with the button. Then down here, the 4 green status lights over here, I have them go in sequence from position 0 to position 1, 2, 3, and 4. Okay? So the whole routine that you see here sets the initial values of all 7 of those lights that I just mentioned. And then it says, hey, if the user button was just pressed and the last state of the user button was that it wasn't pressed, add 1 to this position variable and then end the if statement. And then it checks if we're in position 1, turn L1 on. If we're in position 2, turn L2 on. If we're in position 3, turn L3 on, 4 L4 on, and then if position exceeds 4, meaning I pushed it a 5th time, set it back equal to 0, and then lastly, set the last user variable equal to user. Okay, so if you have a PLC, an Arduino PLC, and you're programming along, make sure that from your overview screen, it kind of looks like this. I should have started, if I did this the right order, I should have started with a video on how to get set up with your Arduino Opta PLC. So make sure you watch that. If you're not at this step and you're trying to code along exactly with this tutorial, get to this step where the license looks okay and all the available interfaces look okay, and it says connected in the bottom right. Again, I should have done a tutorial on how to get here, so just check my channel, or if you're watching all these videos smashed together, check the first section of this video for that. Now, 2 other things we did in the structured text video to set ourselves up that you want to double check are in there. We went to button inputs, and the user that is on the front of the PLC, the user button, we added the variable so that we could call it user in our program. So make sure you have user or something easy to remember there. And then for LED outputs, I added the variable names L1 through L4, red, green, and blue, to all 7 of these lights so that I could call these lights from the PLC as well. So make sure you have all those variable names, or you'll be like, hey, my version that I'm trying to follow along with doesn't compile and says that like those variable names don't exist or something like that. Okay, so with that basic setup, with these variable names, with these button inputs, let's go ahead and go to project, and let's go to add and new program, and we'll call this ladder 1, because I might do more ladder. And make sure you have LD, ladder diagram, selected. Structured text was what we did in the last video. And we're going to assign it to fast. So these are different scan rates: fast, slow, background, and init. We might get more into it later, or just let me know if you have questions about when to assign what to where. But we're going to assign it to fast. No reason not to go fast. And let's just go line by line of what's happening in this main PLC and talk about how to recreate that in ladder. Okay, so the first line is green equals false. So how do we make a line of code in ladder diagram to set an output equal to false all the time? Well, we're going to use this output coil, which is what this object looks like. We're going to put the variable green in it, and currently what it reads as is actually green is always true. So I'm going to double click on that coil, and I'm going to negate it, and this strike through, this open parentheses, hash line, slash line, and then close parentheses, reads as not. So it's basically green is not on. If I copy this whole ladder 1 and I change this to normal and I change this name to red, This line of code reads as red is always on. So we have green, always false, red, always true. That's what line 1 and line 2 here are doing. And it looks like this in structured text. Green is false, red is true. Okay, so you can see right away just with this basic comparison that ladder is a super visual language. There's nothing that explicitly tells you it's true or false. It's telling you based on what sort of relays in electrical schematics look like that green will not be true and red will not be false. Green will not be true and red will always be true. So let's look at the next line of code, which if you remember was that blue, the blue light, will be exactly equal to the input of the user push button. So I click on that coil again and I say, hey, we're going to control the blue light, but we're going to control it based on an input now. So this is called a contact. These on the right that are controlling outputs are called coils. This on the left is called a contact. And we're going to say equal to the user input. So the way this line of code reads as if user push button is pressed, then blue light is on. But there's a second thing going on here, which is if user push button is not pressed, blue light is off. And that's because this output is a momentary output, which means the blue light will be on as long as the conditions on the left of this rung are true. But by default, the blue light will then go off when the conditions on the left side are false. So this sort of has if user, then blue light, and if not user, then not blue light baked into one line of code. So it really is the same way this says blue is equal to user, whether it's true, whether it's false, set blue equal to user. That is basically exactly what this line of code is doing. So far we have 3 for 3 recreated from structured text. Now, this is us setting the initial value of all 4 of those lights equal to false. So we're going to copy this green line, which is this whole rung, which is setting green equal to false. And let's see, can I move that down? I really want it in exactly the same. I really want it in exactly the same spot. There we go. So I'm going to change this to L1. And now, rather than make 4 rungs of code to do the exact same thing for these lights, I'm going to just Control C and then Control V right here. And you can see it sort of puts this branch in, which is saying, hey, the same input conditions are true for all of the outputs on this rung. So the 4 outputs are just L1 through L4, set them equal to not true. But the input is shared by all 4 of them. All right, so this is how we say L1, L2, L3, L4 equals false. That's what rung 4 through 7 here are doing. Let's just keep going. Let's take a look at saying if user and not last user, then position equals position plus 1, okay? That's the line of code that checks when the user button is first pressed and adds 1 to the position incrementer. So to do that, we'll say right-click, new network, after. And now we're going to check 2 conditions. We're going to check if user, and then I'm just going to Control-C, Control-V this, and we're going to check if not user, or last user. So last user, but this one needs to be negated. And this is saying if the user push button is pressed and the last user Boolean is not true, then, but we can't use a coil anymore. A coil is specifically just for Boolean conditions. It's for true, false things. We need to adjust an integer value, which is called position. And I forgot to say this in the setup, but if you go to global variables, these 2 were made for the structured text tutorial. The variable last user, which is a Boolean, and I have the initial value set to false, which will be how we track the last state of the user push button. And then position, which is an integer, which will start out as 0. And I have retain on, which means it will keep its value on new iterations of the code being pushed. So if position is set to 3, when I update the code, it will stay as a 3. And that will track where in the sequence we currently are. So let's go back to our ladder. Just make sure you have these global variables set if you're following along exactly. And we'll say if user and not last user. And now we need a new block. And if you don't have this toolbar in here, go to go to view toolbars, and make sure FBD is on. If you have a decent size modder, you can have all of these toolbars on. It doesn't really hurt to have SFC. It's just it's not something we need right now. But you do need FBD because new block exists in FBD. And then when you add a new block, this object browser lets you type in text and search for things, but you need to have most of the objects checked and selected. So you could have them all checked and selected. That's not going to hurt you. It's just going to give you the most options. And the first thing we want to check for is an add function. Okay, so ADD, because what we want to do is say if user and not last user, then add 1 to position and store that value in the position variable, and then we don't need a coil on this rung. Okay, so this line of code, if user and not user, add 1 to position, looks very visually different from this if user and not last user, then position equals position plus 1 and if, but those are clones. Those are functionally equivalent. Okay, and just so I don't forget, because it comes at the very end, but we might as well set it right now. We want the last network, so the bottom network in this, to be set last user equal to user, because ladder logic reads top to bottom and left to right. So every scan of the PLC will start from 1 and go down to however many rungs we have in our code. And then at the end, it will set last user equal to user. So this line of code will only ever be true once at a time per button press, and then last user will immediately get set to the same value as user. Hopefully that makes sense. Now let's add a new rung here to do these steps here, which is if position 1, then L1, if position 2, then L2, and then all the way through to if 4, then 4. And so let's just go ahead. We need a new block here. We actually don't need either of these coils, but we need a new block, which will be checking for equality. So that's EQ, and you grab the EQ block, and you say if the position value is equal to 1, then L1. And this rung of code is the exact same thing as if position 1, then L1 from structured text right here. So this is if position 1, then L1 equals true. So we just need to copy that 1, 2, 3, 4, so that we can say, okay, now if 2, then L2, if 3, L3, and I somehow got them out of order. Okay, 1, 2, 3, L3, and then if 4, L4. And now we need just one more rung of code, because if you remember from our structured text, we had if position is greater than 4, then we need to set position back equal to 4. So we'll put in a new network after this, and we need 2 new blocks. We need to check for greater than, so we'll go to block and we'll check GT is the code for greater than. If you ever can't find it, because they're not all named super intuitively, you can just put a star in there and all of them will show up. And a little bit of scrolling, you'll see GE is greater than or equal to, GT is just regular old greater than. And we'll say, okay, if the position variable is greater than 4. Now the difference here is we don't want to change a output based on this. We actually want the next block in the rung to be controlled by this, because if we just hit another block and we grab MOVE, which is how you move a value into a variable, and we say this is when we're going to want to move 0 into the position value like that. The problem is we need this tied to this. We can't use enable output. This is always going to be true. We need this output to be tied into that. So to do that, you delete this little tag, you right click on the body of the object, and you say new nope, it's set output line. There we go, set output line. Okay, so this is what you want it to look like to actually say if position greater than 4, go move 0 into position. But these 11 lines of ladder, and you can see it's quite a bit more scrolling than this little view of structured text, but functionally identical, setting these same preliminary values and then sequencing through the PLC. And just so you can see that it's functionally identical, I'm going to go ahead and delete this out of this structured text, And then I'm just going to delete, actually, I'm just going to delete main out of the routine so that the only thing on here is this ladder routine. And now I'm going to download it to my PLC. I will compile it. And I've got it up here. Make sure you got a good view. Okay, push the button, blue turns on, and we're cycling through it exactly like the structured text that we had at the start of the video. Okay, so I know it might seem a little odd to, rather than build something from scratch, compare it to structured text, but I really think if you're a PLC programmer, it's really important to understand how ladder logic correlates to structured text. Those are by far the two most common PLC programming languages that drive entire factories. So knowing both of them is a really good idea. I hope you found this introductory tutorial useful. Be sure to let me know in the comments below what you want to see next on the channel. That's going to do it for today's starter video on ladder logic. Thank you to Arduino for providing the hardware used in this video. So Arduino once again is making things more accessible for hobbyists and makers. So thank you very much to Arduino. I'll see you next time. Thank you so much for watching. Thanks. Bye. Hello and welcome back to LeMaster Tech, and today's video is going to be a continuation in the Introduction to Controls and Automation tutorial series we've been doing in the channel recently. Today's video specifically, we're going to take an introduction to the world of wiring and electrical schematics for controls and automation. So this is a super important concept and aspect of controls and automation engineering. It's also kind of a tricky one to figure out a good intro video. So I want to start by briefly telling you how we're going to attack this sort of concept. So there's way more, just like all these concepts, there's way more than you could possibly cover in just one short introduction video for the world of electrical controls and automation. And so what we're going to do is we're going to take a look at some example control schematics, not of panels that I physically have here in front of me, but then we're going to take a look at some very basic schematics, create them from scratch together, and then we'll also take a look at the hands-on what that actually means in the physical world. So how every wire that you add to a control schematic actually communicates and translates into the real world. We're going to do a few hands-on examples together. So that's sort of the format here. If you have basic understanding of hobby electronics, like you've played around with Arduinos or Raspberry Pis, then this will be a cool way to see how it translates into the world of industrial automation and controls. And then if you've been an electrician or a maintenance technician or anything like that, this will be a really good way for you to see the controls and software piece of it, but you're probably pretty familiar with the hands-on piece already. So let's just dive right in. In terms of visual aids, it's going to be a little all over the place because I have some like very high level bullet points in a PowerPoint. Then we're going to take a look super briefly at the code we write, but then we're going to cut over to physical wiring as well. And again, the reason wiring is kind of a broad topic and a hard one to cover is because in the world of industrial automation and controls, a control panel schematic and a drawing package could be things that call out your devices and your actual sensor level connections to a control panel, and then all the PLC controller level connections. So from your PLC to I/O modules, input and output blocks, relays, terminal blocks and distribution, as well as connections to the devices and the sensors. And then your power distribution, usually a high power AC power feed into a control panel, and how it translates into DC or step down transformers to be used inside the control panel, as well as power feed to motors and VFDs and things like that. And then often your networking would be encompassed in that as well. So your Profinet or EtherCAT or Ethernet connections as well. So obviously it's a super broad concept, but the drawing package for a control panel is maybe the most important thing to correlate the physical world to the software side that are both so important for controls and automation. So super quickly, in an industrial control package, a really good drawing package, you'll usually have a view that looks like both of these. So this is kind of two different views. I'll try to drop myself in the middle here. This is kind of two different views most of the time. And what you've got is a physical rendering of the panel on the left here. So this has these green covers are usually plastic wireways called Panduit, or whatever sort of wireway that you have. It's just an industrial way of keeping your wires organized. As we'll see when we get to my hands-on examples, physical wiring in the field looks really messy if you're not zip tying or using cable glands and conduit and stuff to keep your cords really clean. So most of the time, these like gray or light green rectangles will be in a material like Panduit, and it'll be a wireway. But then this physically will look almost identical to the control cabinet when you swing the door open. So you have circuit breakers and power distribution and VFDs and PLC components in a very physical, realistic rendering. And then on the right, you have what's kind of called the wireframe, which is usually a slightly less but still precise, but slightly less precise physical rendering of the panel. But everything would be labeled with however it's getting called out in the drawing. So if you see, these are basically the same control cabinet, but on the right there are a lot of blue small text that's kind of hard to read, but there's a lot of blue labels calling these VFDs out as VFD 1070, 2070, 2190. Your switch in the middle row, terminal blocks, PLC components. And so this is a labeled one that still has all of the physical components in their correct physical locations. But this one is correlating a wiring label like VFD 1070 or whatever, some way that it's going to get referred to in this control package. And it's correlating that physical component to a drawing package page that we'll find. So if we look in this next page at an example page of an industrial wiring package, this is actually a great example of the whole drawing package once you get into the line level schematics, which we'll talk more about during this video. But to highlight a few things here, it's very common to have two columns side by side that have these wire numbers that's kind of hard to see, but these line numbers from like 200 to 222, and often the wires will get physically labeled with whatever wire, with whatever row they're on in their drawing package. So it's very normal to see a wire label physically on a wire in a panel that says 205 or 225. It's also very normal to see their tag name. So if you have like a solenoid valve, it could say SV 500 whatever. But often the label will be a combination of where it physically is in the field and where it is in your drawing package. But anyways, you'll get these two columns side by side kind of drawings just because most wires don't merit a full page. Most schematics don't need a full landscape page. So they'll split into two columns. And then the footer is actually where I want to spend some time here because the footer of the drawing package contains an enormous amount of information. Usually on the left side, you have revision notes, which would be the person who approved a revision, the date it got changed, which revision number or letter it is, and then usually a brief note or comment about the revision itself, like what are you adding, what are you deleting, what are you changing. It's very normal to see the latest revision or the newest revision have all the changes in like a cloud or a bubble format on your drawing. And then there's usually some footer information about the company that the drawings are for, like, hey, this was for, this chemical plant prepared by this person, this address, whatever. So some physical information about the drawing package. And then over here is usually who prepared it. So you'll have like the engineer's name of who prepared it, who installed it, who, engineer or designer that was kind of behind that. More information about the customer. And then usually in the footer, you also have stuff on every single page that tells you the name of that page and then where within the broader drawing package you are. So on a huge control panel that has individual motor and sensor and device schematics called out, you could be on page like 12 of 158. So the numbering and the information in the footer is very important. To talk super briefly about some of the most common software out there, you have like like AutoCAD, Autodesk are some of the more common CAD software, and then ePlan is one of the more like software intensive CAD packages as well, but there's also some free ones online. You can use things like KeyCAD, which is best known as an electrical package for like designing PCBs, but you can do free schematics as well. There's a lot of online tools that are kind of free but have less powers. So I think Autodesk, AutoCAD, and basically ePlan are like probably the two biggest competitors in this space. But there's plenty of companies that do this just like any other piece of the industrial automation and controls world. Okay, where do you begin? If this is a beginner intro to control panels and schematics, knowing that the footer has great information, knowing that there's usually a title page, knowing what software to download, that's all great. But briefly, some talking points. So to remind you, this is an introduction and not a comprehensive lesson. And then if you Google just control package, like electrical panel wiring examples, there are some really good ones out there that actually show you physical ones in the field, and they talk you through what you're physically looking at and everything else like that. So if this in particular is the aspect of controls and automation that you really want to become super proficient at, I suggest you just do some Googling. This Solus PLC, another great online company, Real Pars, has some other good examples, and they actually talk about individual components and schematics that you'll see in the field. So that's not a cop-out. This is meant to get you familiar with the basics, but it's also just not a deep dive. So if you want to spend a lot more time studying on this, I absolutely recommend just spend some time Googling. Solus PLC and Real Pars have some great examples, as well as some others out there. Okay? But then I do think one thing that's really important to talk about as part of this video is who has standards in this field. So if you're a drawing designer or an electrician or an instrumentation and controls engineer, it's very important to be familiar with NFPA 70, NFPA 79, and UL 508A. Also sometimes called NEC 70, but basically these are industrial guides on power requirements, power distribution requirements, best practices for installing and creating and developing control cabinets. UL, or Underwriters Laboratory, is a listing that like panel fabrication shops and places that develop controls equipment, they want to stamp their panel with a UL listing because that means they've adhered to a certain high standard that gets validated by this company, by the UL organization. Those are like 1,000-page guidelines and books, and usually I think you have to pay for a whole copy of them. Best practices of those are found online. They talk about wire gauges, power distribution concerns, and a lot of other really great things to keep in mind while you're developing control panels, but not really what we're going for in today's video. So those three standards are great for looking into. But let's talk more practically. If you're a hobbyist or a field engineer who just needs to know when I need information, where can I go to get said information? And it's really the internet. But anytime you buy a sensor or a switch or a button or a motor, the manufacturer of that component should be providing the wiring schematic and information to you via internet manuals, downloadable manuals. Ideally, it would be included with the component when you buy it. But just a quick Google, or if you're buying components from Amazon, like I do for my garage all the time, the Amazon listing itself oftentimes has the wiring called out as well. And then control components, these are actually a lot more standard. So if you're buying Allen Bradley or Siemens or Beckhoff or even, Arduino PLC like we're using in this tutorial series, they have really good pinouts and wiring schematics. They can take a variety of forms, so they won't always look like something you can easily drop into a wiring diagram, and they won't always have a 3D model that you can include in your panel. Sometimes you just need to make a little rectangle and say, hey, this is, this device or anything like that. But the actual wiring of how to wire a component comes from the manufacturer you buy the component from. So you don't have to do any guessing of how these things work. And then why it's so important and why it's worth a whole video during this tutorial series just to talk about this component is because in the world of industrial automation and controls, and honestly in the tutorials that we're doing just in this series, control panels and control systems get very large very quickly. And so manually tracking down every wire and cable, where it came from in the field and where it landed in the panel, it's not always safe. It's not always feasible if you've tucked things into conduit runs or they're in, an explosion-proof building, but your control cabinet's on the outside, or even wireways inside of Panduit tends to get so full that you can't just trace your wire accurately. And it's also just faster. If you're the person trying to hook up a system and you're in the field and it's 2 in the morning and you've been on site for 48 hours straight, you want an accurate, well-documented control panel schematic rather than guessing, trying to find a spare channel on your PLC, trying to look into the code and see if there's a spare channel by like reverse engineering the code. So understanding the electrical schematic importance of industrial automation and controls is super pivotal. Okay, so that was a lot of Pete talking, which is my least favorite kind of video. I really like to show you guys things and do engineering together. So let's get into a practical example, and let's just start because I really want this to be a tutorial series that's low to no barrier to entry, right? I'm gonna make all of the electrical schematics today in this example for you in PowerPoint. I don't want this to be like, oh, as long as you have ePlan or as long as you have AutoCAD, you can follow along. So for an example, let's take a look at a system that has a power supply, a PLC, and one input, which is just going to be a hand switch, okay? So a, on, off hand switch, and then a PLC and a power supply. And I think I also, when I prepared these schematics, I had 12-volt power supply called out. I think I've got a 24-volt power supply on my DIN rail right now. That part doesn't matter too much because the pinout's the same, and the Arduino PLC can take between 12 and 24-volt power supply. But nobody yell at me in the comments if this schematic says 12-volt DC and the actual power supply says 24 volts. I will ignore your yelling. I want to talk about what I have on the screen right now because, like I said, I'm making this in PowerPoint. These are not, shapes that you download from the manufacturer, anything else like this. This is literally just I have a power supply that takes wall outlet voltage. And then this power supply gives me 2 plus and 2 minus. So 2 0 VDC and 2 12-volt DC channels. I need the Arduino PLC to receive power. So it has 2 positive terminals and 2 negative terminals as well. And then it has 8 input channels, and then it has 4 relay output channels. So if you've been following along with the tutorial series, you've seen the body of the Arduino already. I'll have some pictures of it on screen now as well. But this is a simple rectangular representation of the component that we're dealing with. And then my hand switch has 2 different sets of terminals on the back labeled 11, 12, 23, and 24. And it's just 2 different strips that are made when it's in the 2 different positions. So that's my hand switch. Let's take a look at what a not industrial control cabinet schematic for this system might be. Okay, so this, again, just in PowerPoint, no fancy software or anything. I'm using a solid blue line to show my DC positive power. And then I'm using kind of a white and blue. White with blue stripe is very common in the world of electrical controls for 0 volts DC. Or just solid white is also very common. But basically I have black, white, and green from the wall outlet into my power supply. And then I'm providing power and 0 volts. So these 2 wires make up a power loop to the Arduino PLC. And then I'm using another positive lead off the power supply to go into the hand switch. And then when I turn the hand switch into position 1, which is basically connecting terminal 11 and 12, then power will flow through this hand switch and go to input 8 on my Arduino PLC. Okay, so it's a very simple electrical schematic, and I'm going to tie it to this structured text program right here, which is just going to turn the blue light on when the switch is on, but then I'm going to use switching logic. So rather than just a boring like, hey, turn the green light on the body of this PLC on when the switch is on, I'm going to actually do a little bit of switching logic. So every time I turn the switch to the on position, that's going to switch my internal on-off variable, and then I'll switch an output and a little green light based on that. That was probably a poor, brief example, but the structured text tutorial was 2 videos ago. This is about wiring. So let's go ahead and take a look physically at the wiring for this system. And you can see the exact wires that are called out in our schematic show up on here. We have the black, white, and green wires coming out of the outlet. And then we have 2 blue wires going into the power feed of the Arduino PLC and onto terminal 11 of the hand switch. And then On the outlet terminal 12 of the hand switch, it goes into input 8 on the Arduino PLC, and then the last wire we need is a V- or 0 volt DC return wire to the power supply from the Arduino PLC. Every wire that we have on this schematic shows up physically in the world exactly as it's drawn here. And let's take a look at a more industrial example of this. So this kind of looks more like you should expect to see in an industrial control cabinet. Okay, I'll try to drop myself in the middle where I don't block anything. But this is sort of how you would expect to see that show up in an industrial control cabinet. You have on the left, you have your AC voltage in, you have line 1, neutral, and ground, and then they go into a power supply. And you can see here, like I put the actual part number of the power supply that I got from Amazon. That's very common too. So you'd see maybe PSU1, like power supply unit 1, and then a part number for it. And then the pinout has ground, neutral, L1, and then plus, plus, minus, minus. Typically, these are grayscale control panel drawings as well. They don't have to be, but you saw in this example a lot of color, where I was kind of color coordinating, matching what's in the field with what's on the schematic. I do actually really like doing these sorts of schematics for hobby circuits because I just think it's clear. But when you're in an industrial setting, this is what you'll be dealing with more frequently. So you have the same Arduino PLC here. Again, I dropped the power supply or the part number on it. And then you have the DC outlet power feed of 0 volts and 12 volts, kind of becomes your new power rail on the left edge of the right half of my screen. And here you can see the power coming into the PLC and then going through a hand switch, which is represented again by the part number, and into input 8. Okay, so actually what's important to know is that what you're looking at here is very industrial, and what you're looking at here is sort of hobby. But you'll see schematics that look a lot like both of these depending on your setting and the size of your application. So that's our first practical example. We have one more slightly more complicated practical example, and then we're going to wrap this video up. Okay, so we have our industrial / hobby example. Let's add an output. So we have a digital input in this previous example, and that's our hand switch. Let's go ahead and say we want to add an output, and it'll be an outlet. So we could hook any common household appliance we want up to a standard outlet. And to do that, we need L1, neutral, and ground. So we need that same 3 wires that kind of come into our power supply. We need those hooked up to an outlet, but L1 needs to pass through a relay. And a relay is a super important controls component, which allows us to switch a wire between multiple contacts. So you use low voltage DC power to change the state of a relay, and then a separate electrical connection is made on the other side of the relay. So I think we'll probably get more into relays as we continue doing the tutorials in this series, but it's arguably the most important component in the world of industrial automation and controls. So let's take a look at the hobby version of this circuit now, okay? And let's walk through all the wires that have been added. I also put in one new sort of color convention, which is a wire that ties directly into the PLC. I've changed to orange, where in the previous example I just left it as blue. So basically the final PLC signal wire is orange. L1 on this schematic is represented in black, so that's going to be your 120 volt hot. Neutral is going to be kind of this light gray because white didn't really look good on a white background. Ground is green, and then everywhere that's 0 volts DC is represented by this like light blue, white and blue striped wire. And then dark blue represents your 12 volts, which in my physical setup is actually 24 volts. But what you can see here, what's actually changed, nothing to do with the hand switch or powering up the Arduino PLC. But what we've done is we've added a hot wire, so a 12 or 24 volt DC wire from the second terminal of the Arduino PLC out feed to side 1 of the relay output on the Arduino PLC. And if it seems silly to go from a relay to control something, it is a little bit silly, but actually I wanted to show you guys a DIN rail mounted relay rather than just a relay PLC output. Technically, there's an extra component in here because I have a relay output and then I go to a relay. Let's just take a look at this practical example, okay? So when the PLC energizes that wire, this relay connects the common to the normally open channel. And then when the coil releases, the common is connected to the normally closed channel. That's a super important concept, not just for relays, but for sort of all of electronics. So if you look up relays and common, normally open, and normally closed, you'll learn a lot about sort of switching voltages. But for now, just know that to control the state of the outlet from our PLC, we bring 120 volts hot into the common channel of our relay. And then normally open means it is the one that's not going to be connected until we pull that coil in. So you could technically program the circuit to work in normally open or normally closed. We're going to use normally open, meaning the only time that outlet will be energized is when the relay is energized, which is when the PLC tells that output it's true. Okay, so that's the schematic. Let's take a look real quick at what this physically means on our bench setup. And you can see, just like I said, it's the exact same wiring as before, but now we've introduced this new relay, and we have the additional power feed from the Arduino coming into channel 0 of the output, and then we have the channel 1 of the output going to the A1 and A2 coil side of the relay. And then the other side of the relay goes back to 0 volts DC. And then we have the downstream power feed of our relay switching the common wire between normally open and normally closed, and the normally open signal goes to the outlet. So we actually didn't have to modify our PLC program at all for this one. All we did is we just said, in addition to having L1, which is the light on the body of the PLC, we now also want the outlet to turn on and off, and we just tie our outlet. If we look at relay outputs, we just tie our outlet to the first output channel in the PLC. So if you've been following along with the tutorial series, that whole PLC side of it should look pretty trivial. Don't worry too much, because this purpose is to be hands-on and physical and electrical, rather than software heavy. But feel free to ask any questions you have about it in the comments below. Now, same as before, let's take a look at how this would get represented in like a physical, in a more industrial controls package drawing. So let's take a look at what's changed. We still have the power feed on the left going through our 24 volt power supply, which I know I called out as 12 volts in here, but it's 24 volts on my bench setup, sue me. Anyways, and then I did something interesting that I think is useful to call out on this channel, or on this tutorial, is I labeled two wires with numbers, O1 and O2. And this is a massive simplification from how like a large control panel would do it, but it's not always feasible to show every physical connection in your drawing in a continuous one nice clean view sort of way. And if you look at the relay, which we've added to the top right, you can see output channel 1, wire 0 and wire 1 are pulling in the A1, A2 coil side of the relay, just like we saw before. But O1 and O2, which are linked to these, are actually being physically represented by a number that says, hey, there's this disconnect between over here and over here. And sometimes you would want to link it with some additional letters as well, or anything like that. But this is just a way of calling out that the other side of this wire shows up somewhere else in your drawing package, and it's a way for you to correlate and track down those wires. Again, this is sort of a non-sustainable way as you get into bigger and bigger and bigger systems. You can't just keep drawing this like function block diagram of all of the crazy wiring schematics, and the coloring conventions can get out of hand and they're sort of arbitrary. So you start to see, as systems get bigger and bigger and bigger, how essential having like a standard format drawing is. So this industrial example, which honestly I've already sort of deviated because I'm building it in PowerPoint, from like some common design choices. But I hope the basics are clicking for you here of what you're looking at, how the physical world maps onto this sort of electrical schematic software world, and then what you're actually looking at in the field and how that ought to be documented when you go and grab a control cabinet. Okay, so I know by far in this tutorial series, this is the most talking that I've done and the least showing you things that I've done, but it is really hard to demonstrate the world of electrical controls, drawings and schematics and control panels without like going into the field and walking through one with you. And frankly, my company would not be okay with me like walking around the plant floor showing you our control cabinets. So you're gonna have to do with what I can show you in the garage. I hope it was useful. As always, let me know with any comments or questions on this one. I also have a pretty deep library of me talking about controls and automation concepts, including wiring and hardware and things like that on the channel. So be sure to check out Lemaster Tech for more. Drop me a comment with any questions that you had, anything that I can try to clarify for you, and let me know what you want to see more of on the channel next time. Thank you so much for watching, and we'll see you next time. Thanks. Bye. Hello and welcome back to Lemaster Tech, and in today's video I'm going to show you how to get started with the SCADA software called Ignition, and we're going to show how to use it for free for hobbyists and makers. So we're going to use the Ignition Maker Edition. To get started, just go to Bing or Chrome or Google, your favorite browser, and type in Ignition for Makers. The company that makes the SCADA software called Ignition is Inductive Automation. So you'll see Inductive, you'll see Ignition, and occasionally you'll hear it referred to as a SCADA. SCADA means supervisory control and data acquisition. It's just a layer of control software, but Ignition in particular has a ton of cool applications, even for things that hobbyists and makers can get behind, which is why they have a Maker Edition. Ordinarily, this is thousands of dollars for a corporate company to get a full-blown version of a SCADA software, but Ignition has released a lightweight version of it for free, which is super exciting because a YouTube channel like mine can give a bunch of tutorials on how to do things in Ignition without needing to shell out thousands of dollars to get like a full license. So that's pretty cool of inductive automation. To get started, I'm already logged in. All you have to do is make a personal account. It'll ask you to verify an email, and then you'll be able to sign in to the link that is generated when you just click this button, Get Ignition Maker Edition. And then the first thing, I have generated a license key. I'm not going to show you guys because it's mine. But when you generate a license, there's just a big button here that says no licenses, and then you hit get license, and then it'll take like 30 seconds, generate a unique code, and you'll get two things: the license key, which is this number, and it's okay that you guys can see it, because the other thing you get is a super long string of text, which is your unique license key. And then you want to download the installer for whatever platform you're on. I'm on Windows, so I'll go ahead and download the Windows installer. This video is kind of geared at getting you started with a SCADA software. I think in the coming videos and on this series, we'll get into how to do lots of things with the SCADA, and I'll kind of talk through why you might want this. One, if you're in the world of controls and automation, and two, if you're a hobbyist or a maker, kind of show you why it's sort of cool to have access to a SCADA software, even in a home setting. So I'm looking forward to this series. I've had a lot of interest in controls and automation on the channel. And additionally, I have also had a lot of interest in Python programming on the channel, and even like Arduino and hobby builds and making things. And a SCADA software is a really interesting spot to bring SQL, Python, Java, and automation and controls, obviously, all together. So I'm looking forward to this series. I'm just going to go ahead and do typical installation, because you can do custom here and you can choose modules to install or not install. But you can also add modules at any time down the road. So you don't have to feel like if you don't customize your install in the beginning, you're stuck with features or without features that you might want later. That's no big deal. So let's just go ahead and run the installer. And something super cool about Ignition, it has two types of visuals. It has perspective, and I think the other one's called Vision. I don't use Vision really. Perspective is a web-based one. So if you had a system of networked computers, it could be your house or it could be a company. You could have hundreds of computers on the same network, and they're all able to pull up the views, the displays that you build in Ignition from anywhere. So perspective is pretty cool. Yeah, so let's go ahead and get the Maker Edition. This standard edition is pretty awesome, but you do have to pay for it. So let's just get the personal use. I do not agree. I do agree. And here's where I'm going to pause the recording because I need to put my license key and activation token in, and I don't want you guys to see my activation token. Okay, so you punch in your activation key and your license, and then it asks you to make a username and a password. I make really strong passwords, so don't even try to hack me. These we're going to leave for now. We might mess around with some gateway port HTTP and HTTPS stuff, but really leaving them as the default ports will not be a problem. So start and launch the gateway now. Sure, shoot. Who cares? The Ignition gateway is sort of a hub, so you could have multiple projects that do different things, have different views, different scripts and tags underneath them, and the gateway is what brings them all together. So there's really typically only one gateway per installation. Enable quick start for new users. No, I'm like so good at Ignition already. I'm going to start from scratch. So but when you download the designer and you put that software on your computer, that is like a desktop-based tool that you use to build HMI displays in. And I'll install for all users. Install for all users. It's just me using the computer. And you can create a desktop shortcut here. So this is nice. It lets you access the designer from your desktop. And real quick to look through the gateway. Oh, I have to log in. Okay. So if we look at the gateway real quick after logging in, just a few things to highlight here. This is just your hub to tell you how many devices you have connected, what they can do for you, and tell you some statistics about your performance. So by default, the gateway has access to 2 gigabytes of your RAM when you download it. And I have a computer running basically nothing other than Ignition and my video capture software. So the CPU is really not working particularly hard. But you can also up this number. My computer doesn't have 2 gigs of RAM. It's given Ignition 2 gigs of RAM. So we'll do how to increase RAM on Ignition in a future video. For this video, I think the most useful thing to do would be create our first view in Designer and maybe add a couple tags and just show how to display them on a view. And we'll call that for the introductory video. I do quite a bit of work with Ignition, so if you do have questions, be sure to drop them in the comments below, and I'll try to get back to you as soon as I can. When you open up the designer, there's going to be nothing configured, and initially you can just hit Add Designer. Assuming you're doing all of this on your same computer, the designer should already be discoverable. You might have to do like discover gateways on your network if you're using a different computer on the same network. But again, that's kind of like more advanced, and I start questioning, are you really doing this for makers? But I guess also these videos could be super helpful for people who do have a corporate license. So now when it shows up there and you hit Open Designer, it's going to give you a view that is a little bit daunting at first. It's hard to make anything simple. Let's go ahead and log in. So I'm going to pause again. Okay, so after logging in, if you have been working on projects in the past, they'll be here. If not, then you can just hit New Project. Let's call this one Lemaster Tech, and then we'll say underscore tutorials, okay? Project name, project title, I don't know, that seemed like a good title. I think project template, parent project, we'll get into that in the future. You really don't need one right now. Connection settings, default is fine. OPC UA module, for anyone using like PLCs, they're going to probably want the OPC module as user source, but you can also change all of this stuff later. So don't worry too much about those. Leaving them as the default is just fine. Stuff we're going to get into in future videos, tags and type of tags and how to use them, how to use SQL with Ignition, how to add PLCs and devices to Ignition, different types of displays, things like that. So if you have questions about anything specific with Ignition, be sure to drop them in the comments below. And now let's take a look at making a first view. Okay, so let's go ahead and hit the plus on this first view that pops up. We are in perspective. So again, I talked a little bit earlier. Ignition has 2 HMI tools. One is called Vision, and it's a like conventional based on a computer software. The other one is Perspective, and it looks to me like Perspective is the only one that's included with the For Makers edition, which is totally fine. But the cool thing about Perspective is it's web-based, and so that means that you can give URLs to every page. So let's just make one, and we'll call it /homepage. and it asks you what primary view you want, but because we haven't created any views yet, there's no views. So we'll expand in the project browser, we'll expand the perspective section, and you'll see there's an area for views, but it's just an empty folder right now. If you right click, then you can hit new view, and we'll call it homepage. Homepage, there we go. Root container type, column container, breakpoint container, blah, blah, blah. Coordinate is going to be your default. Go ahead and keep that. And when you make check page URL, it's doing this page for you, this part for you in the background. So we'll actually hit create view. And real quick, if you click back on views, you're going to see ones that are linked and ones that aren't. So this is the one I was working on. I'm going to delete this. Yes. What you're doing is you're telling Ignition a series of pages that can be navigated directly to from a web browser as long as you're on the gateway, which is super interesting. And we'll get into how to access it and what that actually means one video at a time right now. But so we have created a view called homepage, and it is linked to the URL /homepage. So simplest thing I can do to show you guys like what Ignition is make a tag. So I think what I want to do here is I want to make a folder, and I'll call this folder tutorial tags. And SCADAs and PLCs and basically anything automation and controls really live off of the tag structure, which is just having, in conventional programming, you'd think of it as a variable. In automation and SCADA software, it's a tag. It warehouses a tiny bit of data. It can be used for reading, writing, and logic. So let's go ahead and make a memory tag, which means it just lives on Ignition. It lives on this computer, and we will call it my first tag, okay? And let's make this a string, and let's give it an initial value of, why not, hello world, okay? And let's go ahead and drag my first tag onto the screen, and all we do is click on that tag and drag it onto the screen, and it's going to give us its top recommendations for what that data format might be. And so we'll hit label. And there you can see we have a tag that says hello world. Nothing crazy, nothing fancy going on here. And if we hit save, so Control S or the save button up here, we should now have a view called hello world. And so if we go back to, my robot heard me say hello. If we go back to the web, we can see how we can access this now. And actually, one thing we're going to do before we access it from the web is we're going to make a URL for just the home page, and we're going to address it to that same page too. So what's interesting here is I've made a second address that will access the same page. If you've done a little bit of web development, you've probably seen that sort of thing. If not, no big deal, but this basically means that this page should act as your home page as well. So let's go ahead and see how you can actually view and access this thing. If I go back to Edge and I just go to localhost 8088, so this here, localhost 8088, is going to be how you access it from the computer when you're on it. But you can also usually get to it if you just start typing in Ignition. You'll see here, it'll remember like Ignition, LeMaster Tech Engineering 1, Ignition Gateway. And anything that has this orange dot is usually going to take you to somewhere on the gateway. It might have you log in, that's okay. Anyways, when you want to view a project online, this homepage has download the designer. We've already done that. And it has view projects. And if you do that, the projects that you're making should be here. And if you hit launch project and agree that it is for hobbyists, students, and individuals, then what you can see is we have a page that says hello world. And that's super cool. And if you had a /homepage, it would still be this page because we gave it two different addresses. But we're basically building a website that is only for people who have access to your gateway. And that is something super cool and kind of unique about the Ignition SCADA software. You have here is the first tag, the first display, how to get started with Ignition for makers. What we'll be doing in this series is a lot of the basic stuff that you might need to know about to build various features in Ignition. I'll definitely focus mostly on the core functionality of how to do things with Ignition, and then I'll probably start showing how to do a lot of things for makers specifically. So I have a pretty cool garage workshop. I'll probably do a lot of automation projects in the garage, show how I use a SCADA to do that. So if you have ideas of what we should do with Ignition or things that would be useful for you to see, be sure to let me know about it in the comments below. Thank you guys so much for checking out the channel, and if you have any questions, let me know. If you have any ideas for future videos, let me know. And as always, good luck with your projects. Thanks for watching, and we'll see you next time. Thanks. Bye. Hello and welcome back to the channel. In today's video, I'm going to walk you through how to use expression tags in Ignition. All right, so this is obviously a continuation in the Ignition tutorial series we've recently started on the channel. If you do have any questions about how to download Ignition for makers, what Ignition is, why you need it, what an expression tag is, be sure to check out the playlist on the channel. I will be adding all Ignition tutorials to that playlist and hopefully building a pretty deep backlog of how to get started and how to use Ignition, and eventually doing some pretty cool and in-depth automation / makers projects with it. So as always, if you have any questions, feel free to drop them in the comments below, but I'll be assuming for this video that you at least have downloaded Ignition, know how to get into the designer, and want to know how to use expression tags. So I've already built out a little bit of a framework here that has a Boolean, meaning a bit, meaning on or off, true or false. And you can see I have a toggle checkbox for it on the screen that I've built. And you can see the tag value itself in this browser on the lower left, also changing when I change the bit. Then I built out a little just plus, minus 2 buttons on either side of a counter. And these are just letting me change the value of my integer tag. And then I have a text entry box here. Just where I can enter values and change the value of a string tag. So the reason I built out these 3 different types of tag is because I want to, obviously, new tag, new standard tag, expression tag. I want to show you how to use expression tags, and I want to show you how to interact with 3 different types of tags in your expression. So that's why I did that. And let's just call this expression tag 1. It's a nice descriptive name. We'll make it an expression, and we will make it a Boolean, because what this expression is going to be doing is evaluating multiple other tags and making a decision whether those conditions are true or whether those conditions are false. So we'll come down to expression and we'll hit the pencil. So now we are in the expression editor. If you ever get like super duper lost and confused, these fields in the top right, there's a little plus and an equal sign, and these are some of the most common fields that you'll be using in expression tags, so I find them pretty useful. If you ever forget that like or and, or less than, or equal to is this specific symbol, it's nice to have a little refresh available to you right there. But to be honest, expression tags fill a pretty tight niche in Ignition, because when things get really complicated, you don't necessarily want to be using expression tags. You want to be using like Python scripting, which we'll talk about in future videos, but the purpose of expression tags is to sort of evaluate a few things in a field. You could think of a tank, right, that could have multiple alarm issues. It could be at high level. It could be at high pressure. It could be at high temperature. And if any of those things are true, you want to turn an alarm on. Maybe it's a strobe light, maybe it's an alert, maybe it's an email that gets sent out to like maintenance or something. So that is kind of the perfect time to use an expression tag. And to use an expression tag, we're basically saying we want to look at the value of other tags and let that determine the outcome of this tag. It's basically like, let me read values about other tags and make decisions about what I should do. I said that already. All right, so let's copy the path of our Boolean tag. And I went kind of fast there, but if you want to look at the value of another tag inside of your expression, one easy way to do that is go to the tag that you want to look at the value of and right click and go down to copy path. That will give you text, which if you paste it into curly brackets, will look like this. And this is going to give you that tag, and it's telling this expression tag explicitly where to go and look at the value. So first thing, let's say we want the outcome of this tag to be determined by whether or not that Boolean tag is true. So when this thing is checked, it'll say enabled, and that means it's true, and so this will become true. Now we're going to use the expression and, which is 2 ampersands. And now we're going to look at the integer tag. So I could do it exactly the same way. I could copy the path just like I just did, and I could paste it in here. But one additional pretty cool little thing you can do inside the expression browser is this insert tag button, which is a little tag icon over on the right. You hit insert tag, and it'll open up a tag browser. So I can go to my folder for tutorial tags, my expression tag tutorial, and I can click on that integer tag and I can hit OK. And I can say, so now integer tag, and I want it greater than 2. And what you guys notice is kind of interesting is rather than all this first gobbledygook, what I get is square bracket, period, square bracket. And that is because it's telling this expression, you don't have to go look through the entire tag browser to find this tag. It's in the same host folder and location as you are. So this dot is just a way to get your expression optimized to look at a closer location. So really we could go back and we could control C this into here because the Boolean tag is obviously in the same location as well. But for now, let's do just those two things. Let's say if the Boolean tag is true and if the integer tag is greater than 2, then we want that to determine the outcome of our expression tag, okay? And I'm intentionally not using the string yet because there's one thing we're going to talk about when we get to that. But let's go ahead and make the expression tag. And just so it's a little bit more useful for us, let's go ahead and change our, yeah, I left it in run mode. Let's go ahead and change the text on this to look at the expression tag. So it's still looking at my first tag. Let's look at the expression tag, which is just going to say true or false. And let's just transform it to tell us explicitly that false will mean conditions not met. And I'm not really focusing on stuff like how to transform and what I'm doing right now. Conditions all met, okay? All I'm doing is taking the true-false outcome of the expression tag we just made and saying whether or not the conditions are met in a little label up top, okay? So if you remember, we said the integer has to be greater than 2, and we said this bit has to be enabled. So the bit is enabled, but the integer is exactly 2. Let's go ahead and add 1 to the integer. And now it says 3, and now the expression tag says conditions all met. Now, if I were to disable the bit, it says conditions not met again. And what's really interesting is we didn't set up our expression tag to be like cyclical or anything. We left it on the default, which was event driven. And event driven is really interesting because event driven means it's looking at changes of any of the tags that it is addressing in its expression. So it knows that when this bit changes, it needs to do a new evaluation because the values that it's comparing to are changing underneath it. So it's a really cool function of Ignition expression tags. If we were to take this integer back down under 2, we would get an issue. Well, it would just say conditions not met, not an issue. Now let's take a look at how to incorporate a string because it's a little bit tricky and I left one thing out of this expression on purpose to show you the difference. I think now is a perfect time to take a quick pause and talk to you about the sponsor of today's video, PCBWay. PCBWay is a long-term supporter of the Lemaster Tech channel, and I love working with them because their products and services are all about empowering makers. As their name suggests, the core of their business is manufacturing PCBs or printed circuit boards. This is such a cool way for hobbyists and makers to turn their electronic designs into super high quality and professional grade circuit boards. Beyond that, they also have the ability to support all your prototyping needs with high quality 3D printing and metal fabrication as well. Be sure to check them out at the description below this video, and thank you so much to PCBWay for sponsoring the video. Alright, now let's get right back to the tutorial. Okay, now let's take a look at how to take that expression tag one step further and incorporate our string tag here. Alright, so let's go ahead and say we also want to keep an eye on the string and make sure that it doesn't equal a certain code, right? Like you might have a status for a tank and it says like filling, heating, mixing, idle. And you want to make sure that tag is not idle. So we could say, and we want to make sure the string tag is not equal to, and not equal to is exclamation mark equal sign. And let's just pick Pete, because that's my name, and that's something that is easy for me to remember while I type it. All right, and let's go hit apply, and let's hit save. And now I'm gonna say, all right, this is greater than 3, and my string tag is not equal to Pete, which is great. But if I hit enter, you'll see conditions not met. So it's still working like that, which is really cool. But one weird nuance that you just should be aware of is if you want to do something different, like and length of the string tag is not equal to 0. So you're just basically saying, I don't want to have an empty string. If we hit apply, and we hit apply, and we hit OK, it says conditions all met right now. And when we hit delete it out, it seems to be working properly because the string goes to nothing. It might seem like an unnecessary step because everything was working fine without it, but just to show you kind of how it's interchangeable but still important to know about, I'm going to add dot value to the end of all of them. And what you'll see is they still all individually work. Like I can still turn off enabled disabled, I can still make the integer go below 3, and I can still make this go empty. I hope the outcome of this video is crystal clear. This is a really neat, powerful way that you can get one tag that tells you the status of multiple things in your process, and you can use that to do all sorts of useful stuff downstream. So it's like doing programming inside of Ignition, which is nice because a lot of old SCADA software, you mainly wanted to do as much programming as you could inside like the PLC or the devices that were coming into your SCADA, and you want to minimize developing like code and different formulas and stuff inside of the SCADA, inside of the HMI itself. But Ignition really changes that, in my opinion. Bringing raw tags in and doing math and calculations on them inside of a project absolutely makes logical sense using Ignition. So I think this is a super cool topic, and I use these tags all the time. So be sure to let me know in the comments below if you have any questions. If you have any questions about this stuff I kind of did on the side to set up this example, let me know as well. And be sure to let me know what you want to see next on the channel. I do a lot of development in Ignition, so if you have questions about how to do any sort of specifics with that, just let me know. As always, thank you so much for watching, and we'll see you next time. Hello and welcome back to the channel. In today's video, I'm going to show you how to write Python scripting inside of the SCADA platform Ignition. I'm going to show you how to do it in 3 different places, and we are going to cover a lot of material. So let's get right into it. Today, we're going to talk about one of the things that makes Ignition so incredibly powerful and super easy for traditional programmers to break into the world of industrial controls and automation, but also for controls and automation engineers to learn a little bit more of the conventional programming skills, so to speak. And part of the reason for that is you can write code in Python. And so to do this, I'm going to actually save us a little bit of trouble of watching me scrap together a piece of Python code, but I'm going to propose a scenario for you guys. And hopefully you can see in the bottom left here, I have a tag that I've created called input array, okay? And it is just an integer array. So there are 10 integers inside of this array, and that is all that's in there. And we can, you know, just manually remove rows if we want to. It's just a memory tag. It's a block of integers. But let's say I want to write a script that's going to dynamically read through that integer array, look at how many elements are inside of that integer array, and create a tag for each of those elements individually. This could be useful for trending, like creating historical graphs of temperatures and flows and things like that, or a variety of purposes. So there are a lot of reasons you might want to do this inside of Python rather than break it out when you're like reading a block of data from a PLC, for example. You might read that in as an array. So let's take a look now. I'm assuming you have a reason you want to write Python in Ignition. So let's take a look at first example of just how to test a script while writing it in Python. So your best friend as a developer, when you're inside of Ignition Designer and you want to test some Python script, is the script console. So if you go to Tools at the top and then Script Console, it's going to open a window that looks kind of like a very bare bones IDE in a conventional like programming setting, like a Jupyter Notebooks or something. None of the bells and whistles of like a PyCharm or VS Code, but the idea is you write code on the left and it gives you output on the right. So I'll talk you through the code that I've written already, and hopefully you can tell, if you're somewhat familiar with the Python syntax, that other than knowing some specific Ignition syntax in here, the code really reads like Python. It's a variable set equal to a value. It's for I in range, whatever, try except for I in range, right? Like this is Python code with some Ignition specific syntax. You'll just have to refer to Ignition forums, ask a friend, ask the internet, ask Ignition support if you don't know the specific syntax of the thing that you're trying to do. But basically, this is a script to take elements of an array and break them into child tags, okay? So there are a lot of ways to do this. This script is in no way the only way you could do this sort of functionality, but I start by reading the raw data from the input array tag, and then I define the path where I'm going to store and delete any child tags. So the first thing I do, and I'm kind of using a fudge factor here of 20, but first thing I'm going to do is clear out any tags that might already be in there. So if I've already done this script previously and there were, let's say, 6 array elements already sitting in there, this code will go through and it will delete those all out. And then what it's going to do is for I in range length of the data. So in the length of the array, it's going to define a new tag that will be called array element 0, 1, 2, 3, 4, 5 to whatever length we have. And then it's going to configure the tag, meaning create the tag, and then it will write a value to that tag of whatever's in that array. So is this a somewhat confusing example? I hope not. But remember, I have an array here that has the values in it of 10, 20, 30, 40, 50, and 60. So our goal is to create and you can see there's no drop down in the child tags folder currently. Our goal is to write a Python script that is going to read the data from that tag, and then it's going to create 6 children tags that say 10, 20, 30, 40, 50, 60. That should be what this code does. And so if I execute it, you'll see I actually get bad not found, which is completely fine because that's the delete code not finding the tags. And then all of the goods are the configuration and the right blocking working. So if we click on child tags over on the left, now you'll see we've dynamically created array element 0, 1, 2, 3, 4, 5, 6. Just 0 through 5, which is cool. And their values are 10 through 60, which makes intuitive sense. But now let's pop into our array, and let's say between 10 and between 30 and 40, we have 35, right? And after 60, we have 70. Okay, so let's say that the array has just been updated and now there's 8 values. And what you'll see is the script in the script console isn't going to automatically update it. We have to hit execute again. But when we hit execute again, the same code works and it gives us 10, 20, 30, 35, 40, 50, 60, and 70. Okay, so this is some very basic code to generate tags as you rip them out of an array dynamically, as well as clear out children tags that may have already been in there. This is pretty cool, but I think what you guys are probably noticing already, and it's no big deal if not, but it's not super convenient to have to manually execute a script every time an array updates. And so what we want to do is explore how to get that code firing on tag change. And that's what we're going to talk about now, because there are a lot of places that you can embed this script that we've just written into a different location that will do some of that functionality for you automatically. So let's take a look at the first one, and I'm not going to lie, we are pretty much immediately going to look at better places to store this scripting. But if you have simple Python functionality that you want to do, you can double click on a tag or right click and hit edit tags, and then there's an option on the left for for scripting. And for every tag, value change and quality change are going to be two of your options, as well as alarm events, but we're not going to talk about alarms in today's video. And quality change means like if you're reading values off of a PLC and the quality goes from good, healthy, I can see this tag, to oh bad, oh crap, I can't see the tag, you could do something here. But what we're going to do is value change. And when the value of an array changes, that means two things. Either we've changed one of the integers inside of the array, or we've changed something about the array itself, like the overall dimensions. So we're going to drop the code that we just wrote inside of this value change location. And what you can probably see just by looking at kind of what's available to you here, they give you some values available to you just by the nature of it being a value change script. So you could use the tag path of this tag, the tag itself, the previous value, or the current value in this tag change script. So theoretically, rather than reading the value of this tag, we could just use current value. That's a little bit of Ignition specific syntax. If you have questions about that, let me know in the comments below and we can talk about it more. But I'm actually going to leave the code exactly as is, just to illustrate that it works exactly as is. And then one thing I'm going to add here is I'm going to add a logger, and this is basically Ignition's version of like a web hosted by their gateway console window. So think of the print statement in a conventional Python script. Logger is like Ignition's way of giving you that same functionality. So if you do logger equals, and then the specific syntax is system.util.get logger, just like that. And then you get to define a name. So we will call ours Python tutorial. Okay. I love Python tutorials. All right. And then what we're going to do is logger.info. And there are a few classes of logger dot. You could do logger.warn, debug, info. There might be more, but trace, I think, is one. But basically, I'm just going to do logger.info, which is the easiest one. And we'll just say this came from a tag change script, okay, with an exclamation mark. We'll drop it right there. And all this should do is when we update this, if the script works, this should appear in the logs on the gateway. And I'll show you how to get there in just a second. But for now, let's hit OK. And let's hit save on our project. And nothing happens because the array still has the value it already had. But let's pop in here and let's add 80, 90, and just to mess with the people with OCD, let's make this one 1000. Okay, and let's hit apply and OK. And you can see the array elements are already there, and they're there in the order that we defined in the previous scripting, and they're already populated 0 to 10 with all 11 elements. So now if I pop back into the array and I delete, let's say 1000 all the way up to 30. So there's just these two rows in there, 10 and 20, and I hit apply again and I hit OK. All right, so just by putting in a value change script, this code is working. And now if I go to my gateway, right, if I go to my host here and disregard everything before like 2314, because that was me testing and setting up for this tutorial. But what you can see is Python tutorial, right? The logger name that I just gave to this logger is saying, hey, this message came from a tag script, this came from a tag script, this came from a tag script. So that represents the 3 times the script ran. It's logging it at each time, and you get a timestamp of when it happened. You get here when you're on the gateway and you're at home, you go to status and then you go to logs. And this is absolutely going to be an Ignition developer's best friend, especially if you're trying to set up Python scripting and you're getting weird errors and you're not sure how to track it down. You're going to want to rely on logging a lot of information. Okay, so I think I kind of alluded to already, not alluded to, I directly said it. We're going to move this. This is not necessarily the best spot to have this kind of scripting live. It is absolutely acceptable. And if you have smaller applications or you're the sole developer for a plant, put the code where you want to put the code. But in the instance of wanting to store the code somewhere where it's maybe easier to share, easier to immediately see all of the scripts that are executing in a project, you want to keep it elsewhere. I think now is a perfect time to take a quick quick pause and talk to you about the sponsor of today's video, PCBWay. PCBWay is a long-term supporter of the LeMaster Tech channel, and I love working with them because their products and services are all about empowering makers. As their name suggests, the core of their business is manufacturing PCBs or printed circuit boards. This is such a cool way for hobbyists and makers to turn their electronic designs into super high quality and professional grade circuit boards. Beyond that, they also have the ability to support all your prototyping needs with high quality 3D printing and metal fabrication as well. Be sure to check them out at the description below this video, and thank you so much to PCBWay for sponsoring the video. So what I'm gonna do, I'm not gonna delete this right now because you never know, maybe you want to turn it back on. I'm just gonna uncheck this enabled box. And so now what you'll see, if I update my array, okay, so let's just add 30 and 40 back in here. 30, 40, okay. And I hit apply, and I hit apply, and I hit OK, and I hit save. You'll see the array elements do not update, and that is because we disabled the script that is on there. So if you go to scripting, you go to value change, it is not enabled, okay? So let's look at the better place to put it, and I already have it highlighted actually, but in the project browser in the top left, if you go to scripting, there is gateway events as well as project library. Let's start with gateway events, okay? And you can see these ones over on the left, they all have utility. We'll probably get to a tutorial on almost all of them eventually. But for now, let's click on tag change, okay? And what we're going to do is we're gonna call this array breakout, all right? That's what we'll call this script. And change triggers, I almost always turn off quality and timestamp because I want to trigger on the value changing of this tag. So I'm gonna grab the path of this input array tag by right clicking and going down to copy path. And then in my gateway events here, I'm just gonna drop the tag path here. Now you don't need to copy path like that. You can just hit your tag, and if you have a small system, you're probably able to just go right to it and find it pretty quick, just like that. But you can see that's just the same way, a second way of getting the same data, okay? So we have the code in here, and now we need to put our script in here. So I'm gonna go in here and copy the entire script, okay? And then back to my gateway events, and I'm gonna drop that code in. It always does this funky indentation stuff, but don't worry about it. It's the exact same code. The only thing I'm gonna do is I'm gonna change from logger.info, I'm gonna change it to this came from a gateway script, okay? So a gateway event script. Now I'm gonna hit apply, and I'm gonna hit okay, and I'm gonna hit save, which sends it live. And you can see it update immediately, right? There's 10, 20, 30, 40. We'll go back in, we'll add 50 just so you guys can see I'm not crazy. Well, I'm crazy, but not that way. Okay, so we already have tag 50, which is awesome. And if we go back to the logs, you'll see this came from a gateway event script. Okay, so we had those tag change scripts. Now we have our gateway event scripts. So that is a super useful thing to know, a thing to store, and then also useful to know, excuse me, tag value change scripts are obviously living on the tag themselves. So that's on the tag provider in the tag browser. This gateway event is going to be executed at the gateway level, meaning it's using gateway resources and is not project specific. So something that we can do is we can make a project library, and this is just another place to store a script. Honestly, I'm not here to tell you which one of these is best and worst. Like if you prefer the code living on the tag that's firing it, that's honestly fine. As you get to larger systems and you maybe have hundreds of tag change scripts, it might be very useful for you to see all of those in one spot. But as long as you're documenting where everything lives, it's totally fine to just mix and match, try a little bit of everything. But let's go ahead and copy this script. And what I'm going to do is I'm going to put it in a new location. And so I'm going to go into, now I'm in scripting and I am in project library. And I'm going to create a new script and I will call this array breakout, okay? And in here, just like in a conventional Python IDE, I'm going to create a function, I'll call it run, and I'll put all of this code inside of it. But now I'm going to have in the logger, I'm going to say this came from a project stored script, okay? So I'm gonna save this file, array breakout. And first thing, easiest thing is if I go back into gateway events and I tags and I disable this one so that it's not firing for now. First thing you'll be able to see is if I go in here and I add, let's say now that this is 60, okay, then you'll see the thing doesn't update automatically, right? But if I were to go back to the script console, I actually don't know if this will work, so let's just see. If I were to import array breakout, which is the file that those work in, and let's say as AB, so I don't have to type that, and then I just do ab.run like that. And if I hit execute on this, execute, okay, it actually worked. We got 60. And so the script console is able to take that command that we just stored in a file and execute it. And I think if we go to the logs, you can see that actually that one didn't store. This came from a gateway event script. Did it? This came from a project. Yeah, which is actually a feature of the script console. If you're sort of new to scope in Ignition, just know that script console is a local thing and it's not hitting the gateway. And so when you are messing around in here, you can't use the logger, but you could use this interactive interpreter on the right side. So you could swap out logger statements for print statements and they would show up on the right, but they would not appear in your gateway logs. Okay? But let's go one step further, basically the final step, and show how you might want to use this. Rather than, as this code gets longer and longer and more convoluted, rather than having all that code live here, you could do this. You could call the script that lives in the array breakout folder, and you could just tell it to run when this tag value changes. So I'm going to enable that. I'm going to say OK and say all right. And now I'm going to save everything, and I'm going to go into the array, and I am going to add a bunch more tags. And we'll say this is 63, 66, 70, 75, 80. Okay, so I add a bunch more tags. I hit OK, and what you'll see is we get all those tags. We get 63, 66, 70, 75, 80. And what just happened is this root tag input array changed. We triggered a gateway event for tag change script that then called a script that we stored in array breakout, and it ran this file. Is that convoluted? You bet. Was that the best way I could think of showing you all the different places and ways that you could write Python? Also, yes. Okay? And so if you look at the logs after a test like that, you'll see now we have this came from a project stored script. This came from a project stored script. Because it did, because now this one is firing. And if you'd like to see evidence that both the gateway event and the stored script are firing, we can do this. We can say both a logger for this came from a gateway script, and then underneath it, this came from a stored script. And if we save it and delete one of our tags, delete, okay, apply, okay, and hit save. All right, so 80 drops off, but more importantly, both of those just ran. And so if you look at the script, you'll see this came from a project stored script, fires, this way came from a gateway script, this came from a project stored script, this came from a gateway script, okay? So you see them firing one after another. Because also every time you save in a project, your tag change gateway events are going to fire to cover their butts because they don't necessarily know if the tag changed during that saving instance. So just know that as well. If you're seeing weird behavior in logs of like multiple instances, odds are you're doing Control S a whole lot, which I do fairly frequently. But okay. Anyways, things we covered, super speed. We covered how to use the script console for basic code compilation. We covered how to put scripting directly on a tag with value changed. We even covered how to generate and delete tags a little bit using Ignition scripting in Python, which is useful. And then we covered gateway tag change events as well as storing scripting. So this is a lot to cram into one tutorial. I know this was pretty dense, and I know I moved pretty fast, but there was a lot to cover, so I hope you found it useful. I hope you've been enjoying the Ignition tutorial series. If so, please leave a like on the video, subscribe to the channel. Let me know in the comments below what you'd like to see next on the channel. Don't forget to check out the sponsor link in the description of the video as well. And if you would like to consider becoming a super supporter of the channel, my Patreon link is down there below. I appreciate the heck out of everyone who likes and supports the Master Tech YouTube in any way. So as always, thank you for watching. We'll see you next time. Thanks. Bye.
Hello and welcome back to Master Tech, and in today's video I'm going to walk you through animations in the SCADA software called Ignition. We're going to cover several types of animations you can do, including Boolean, color, and visibility transforms, text transforms including color, text strings, and integers, and then enumeration as well, where you can take integer values and do text-based transforms with it. So this is many of the most common types of animations you'd need to do in Ignition, and then more importantly, it'll show you how tag bindings and animations work so that you can go and build whatever sorts of animations you need into your projects. All right, so we're going to try to cover a lot of content in this video, so let's dive right into it. To start, let's go ahead and make a new tag called a memory tag because I don't have a PLC hooked up right now. I'm doing that just to show you that this doesn't really matter what platform you're using. As soon as you get a tag to Ignition, they're all kind of the same. So I'm just going to make a Boolean tag and call it color bool to start. All right. Now I'm going to go to the perspective components window and I'm going to grab an icon. This is just something Ignition includes. They have a number of icons that you can kind of select and play around with. And actually, I'm going to make two. One to act sort of as a button for us. So I'm going to go to the path and I'm going to type in button. And I'm just going to grab this one that looks like a button. And then the second one is what we're actually going to animate, okay? So I'm going to write a very basic script here with you that is going to... I'm going to go to the icon that's our button. I'm going to go to configure events, mouse events, on click, plus add a script. And what I'm going to do is I'm going to read the tag, system.tag.read blocking, and then I'm going to read the value of that tag, dot value, there we go. And then if my value is high, I'm going to basically write to that tag, so system.tag.write blocking, there we go. And then the same tag path, Control C. And what we're checking here is if it's high, we want to write false, and then else would be it's low. So in that case, we will write true. All right. And honestly, that tag path had to be typed out 3 times. Should probably put that in a variable, but we're not here to optimize my scripting abilities. We're here to make sure that this tag works for toggling. So I'm going to go ahead and quickly just go into this run mode, and I can see that it's toggling in the lower window. All right, now let's talk about the actual animation that is the subject of the video. I'm going to copy that tag path preemptively because I know we want it, and I'm going to go to the perspective property editor window. By default, it's usually tabbed in the right when you open up the designer. But if you go to views and panels and toolbars, you have a lot of configurability over that, and you just need the perspective property editor toolbar active, okay? So in props, you can see color is already there, but if it wasn't there, you're always able to add a property, and then you can add in color if you need to. In this case, it won't let me because it would be a duplicate. But you should have color already if you're using the icons. And then for binding type, we're going to go to tag. We're going to paste in that color Boolean. And now if we were to do just this right now, it's going to give us an error because it can't convert true and false to a different color. So what we need to do is hit this add transform button, and we're going to do a map. And it should open up this window for you, and we're just going to hit 2 pluses. The input type is going to be a value, and specifically it's going to either read true or false. And you can see in the bottom, it's also telling you what the tag is currently reading, which is nice. And then the output type we want, you can see they have a number of options, but value and color are by far the two most common ones. And so when it's true, let's go ahead and make it green. And when it's false, let's make it red. And then fallback would be like, hey, we're having error. Like this is a Boolean tag and we don't have true or false. So fallback will make this yellow just in case there's an error. Okay, and as soon as I hit apply, you can see that it goes green. Now if I hit run and I click this button, you can see it turns red. So the button is changing color bool between 0 and 1, but then the animation on the tag is reading that back and determining which color it should go to. All right, so color is one of the most common animations you're going to want to do if you're in a factory setting or in a home setting. It's a really easy way to quickly tell you the status of something as either okay or not okay. So let's go ahead and delete color and take a look at what I think is kind of the next most common one, which would be, let's take that same tag color Boolean, and we already have a button set up for it, and let's take a look at doing a visibility animation. So I'm going to use the same tag, which is color bool, copy path. I'm going to use the same tag, but what's nice is because visibility is a true or false, you don't actually need any expression or any transform here if you want it to change true and false with the tag. So if I go into run mode and I toggle the bit, you can see that second smiley face appearing and disappearing on the Boolean. Again, I know I went through that one pretty quick, but down in meta, there's this visible option. You can toggle it true or false just from the designer, but if you want it to be tied to a tag, you do it just like this. Now, I know in the beginning I had like a sun and a moon toggling back and forth, so it also kind of makes it look like it's doing a transform if you have two icons and that their visibility toggles inversely of each other. So let's do that pretty quick. I don't want to spend too much of the tutorial looking for the moon icon, but I found it quick last time. Typing in moon didn't work, so yeah, there we go. There's one. So if I have these copies and I have them both set to visible, then you do need a transform to get you the opposite. And the easiest one is just add a script transform and return not value. That way the output is going to be the opposite of whatever Boolean you're reading. So if I hit apply now and I save and I enter runtime, you can see my sun and my moon are toggling as the color here toggles. So that's a basic animation for visibility and for color based on a Boolean tag. Now let's go ahead and take a look at two cool things, which is dynamically changing color and text based on a non-Boolean condition. So an integer or a float, heck, a string if you really wanted to, but I don't. So memory tag, I'm gonna call this one color integer, and then I'll start it out as a 0 and it'll be a memory tag. Now I'm gonna go back to perspective components and I'm gonna grab a label for this one. I'm gonna just drop in a label here in the middle, and so that it's a little easier to see on the tutorial. Oh, come on. That was weird. Okay, so it's a little easier to see on the tutorial. I am going to just preemptively make the font size pretty big, and then we're actually going to mess with the font size in a second, but I'll make it, what's big, 32? Yeah, we'll start there. Okay, so it is basically just what we already saw at a very basic point. If I copy the path of my integer and I go to text now, the text property of a label, and I go to tag for binding, and then I just drop in the color integer, then I hit OK. It is that value. And if I go into this value and I write it to a 10 instead, it immediately changes to a 10. So that is actually a basic style of animation. It's animating the text, but all you're really doing is, changing the text on a label. You probably found that one out with just forums. So let's look at something a little more interesting, which would be like the color of the text changing with that value as well, right? So let's say we have the label and the color, and I don't know, we'll make it red initially. If we go into the same spot before that we had that color animation and tag, and we drop in the same tag, and we add a transform, and we go to map, Now what's going to be kind of annoying is if you go in here and you do value and you just add a bunch and you make your output color. What's annoying is if you just do mapping value to color, then you would have to go integer by integer or value by value that integer could be, and you have to choose what color you want it to be. So what's easier is this numeric range option where we say, okay, between 0 and 50, the level is good, let's say. So level's going to be green. Between 50 and 75, let's say we're talking about percentages on a tank. It's getting too high, so we maybe want to make it yellow. And then between 75 and 100, we are at high level, so we're going to make it red to warn people. And then the fallback will be like, fallback will be black to basically say like, hey, we're getting unexpected values here. Okay, so with this numeric range to color mapping, I'm going to hit OK. And what you can see is it's green right now because we're at that 0 to 50 range. If I go to 60, it turns yellow, which is actually not super easy to see because the background color is white. I spelled background wrong. Background color is white, but if we make it a dark gray, I think all of these colors will show up. So 10, it's green, it's healthy. Yellow, it's you know, hey, you're getting up there. And then 80, there's red. And let's say this went to 105, it turns black because the value is out of range. So that's kind of a cool way to take a look at doing dynamic animation. So I'm going to go back. I had pre-written a gateway script that was going to take that color integer and just keep sending it up until it hits 100 so that we can do some testing and I don't have to like manually go in and toggle come on, Pete, talking right at the same time. So I don't have to manually go in and toggle that value. I can just automate it away, but that only works if you keep consistent naming standards. So I called it color tag before. All right, so with that script, you can now see every 100 milliseconds I have the gateway going through and adding one to that value. It's just so that we can kind of see our animation working and I don't have to keep typing in a value. And just before we get to the last section, I think now is a great time to tell you about the sponsor of today's video, PCBWay. PCBWay is an incredibly cool company that manufactures printed circuit boards and printed circuit board assemblies for hobbyists and makers. On top of that, they have high quality 3D printing and metal prototyping services. They have super helpful and friendly staff, including an engineering team that reviews every order before sending it to production. Fair pricing and great turnaround times. So thank you to PCBWay for sponsoring the video. Be sure to check them out in the link in the description below. Now back to the tutorial. The next thing I want to do is show, let's say you also wanted to animate something else. Now we have two animations based on the same tag already. So if I wanted to go in and also have the font size change based on the same tag, one, that's a pretty enormous changing value and it starts pretty small. So let's also add a transform and a little script here to say let's just return the value divided by 2 plus 10. So it'll change a little bit slower like this. Now, what I wanted to show you is you can animate multiple properties by using a custom property that you pass in once. So obviously we now have 3 animations based on this one color integer tag. If I were to go into custom and add a tag property and put in the mapping of that tag, this gets way easier because I can come into each of these spots, and rather than this being directly linked to a tag, you can go to indirect tag binding and you can give it the property of this thing and then custom parameters, and then we called the tag this custom tag. So you can go and do this for all 3, and you may be saying it doesn't actually save you time because you have to go back and do this part 3 times, which is true. But what I'm going to show next is this is what you really want to do if there is any chance that you're going to use this thing again for similar animations for a different tag. So what do I mean by that? Just give me a second to finish tying all 3 of these to the tag indirect property. and let's hit OK and apply. Now, that took just as long as manually tying it in all 3 places. But let's say I have a second one of the same object, and I want to make sure that all of the animations that it was doing for this first integer, it does again for what I'll call color integer, color int 2. I'm going to call it slow because I'm going to have it changed slower than the first one. Alrighty, so what I'm going to do then is I'm going to say everywhere that I was using color int for that first one, I want to use color int slow for that second one. And initially, because we don't have the value changing, it's just looking at 29. But if I go into gateway events and I make another script, color int slow, color int slow, and this one runs once per second rather than every 100 milliseconds. Okay, apply. Okay, and then we go back to our home screen. You can see I have this on the right changing much slower than the first one, but the font size is updating, the color is updating, and the text is updating just by changing that custom tag property. So that's a cool little thing to make it replicatable. Even with buttons and things like this, if you're going to generate a lot of toggle buttons, you want to write that script to look at custom tag parameters so that all you have to do is pass in what tag you're looking at, and all of the rest of it is extrapolated away by using those shared parameters. So that's kind of one step past an animation tutorial, but I think we have the time to make this useful. So let's go ahead and do one additional thing, which is going to be transforming text based on an integer. And I think this is super useful because it's kind of the basis of like enumeration, which is why I'm going to call it an enum tag. And it's going to be an integer, and I'm going to initially set it to 0. And the thing about enumeration is it's embedding detailed text status or some meaningful thing in an integer value, because PLCs don't always want to store long strings of text when they could just store it as an integer. So the most common thing I'm thinking of is for a sequence or a vessel like a tank in a tank farm, is tank status would just tell you 0, 1, 2, 3, 4, or 5. But to make that useful to an operator, you would want to transform that to say running, idle, starting, stopped, whatever status the tank is in. So let's go ahead and go to perspective components, and let's grab a new label, and I'll show you in a little more detail what I'm talking about. I accidentally made a second label. That's okay. I'm going to grab this enum tag, and I'm going to have the tag tied to the enumeration tag. And now I'm going to add another transform just like before. And we're going to take input values and output values. You don't have to change this to string or anything like that. It'll know you want a string by default. So I'm going to say, let's say 0, 1, 2, 3, and 4 are our statuses that we could get. And let's say 0 means idle for a tank. 1 means it's starting. 2 means it's running. 3 means it's paused. And 4 means it is aborting or stopping. Let's just say stopping. Aborting always means like something's wrong. Okay. Fallback will be error bad status. Okay. That's what it'll say. Now, because the value is initially set to 0, let me make it a bigger font size too. Font size 40, heck yeah. Because it's initially 0, it says idle. Let's go ahead and make a new button, and let's change the script on this one to, I'm eating my earlier words, I should have just made it look at a tag. Let's look at the enumeration tag in this script. And let's say the tag path is equal to this. And then let's read the tag here in the beginning. And then, caps lock, it is case sensitive. And then we'll say if value is less than 4, let's just go ahead and add 1 to the tag, which will be value plus 1. And then we'll say else, let's write to the tag and have it be equal to 0. Okay, so this is just giving me a button that is going to let me increment the status. So there you go. It goes to 1, it says starting, 2, it says running, 3, it says paused, 4, it says stopping, and then 0, it says idle. And if I were to go in and manually make it a 5, you can see it says error bad status. If you don't like it on multiple lines like that, just make your object a little wider. All right, and then what's cool is you can also transform these values, and then you can add another transform if you want. And so you can give a little clarity around what this is. Like if this is tank status, you can say tank status, and then the value all in one tag in one object. And you can say, okay, the tank status is idle. Now, if you have a bunch of text strings on a screen, you're able to show a lot of information just by adding a label to this. And you could also go in that same expression. And if it was, you know, a pressure reading, let's say, you could then add units to the end. So if it wasn't tank status, if it was tank pressure, you could all in one expression, you could say tank pressure, then the value, and then the units all in one string. And you would get this object that is just one cohesive object. You don't have to deal with formatting like 3 different strings all in one. And I actually think that that's pretty darn cool and pretty darn easy. So obviously the tank status being PSI doesn't make much sense. So I'll delete that PSI part because that's my OCD acting up. Apply, okay. All right, but right there, we have covered so many of the basic animations that you can use in Ignition in a fairly short period of time. If you have specifics about how to do more advanced animations, or if I missed an obvious one, and you guys let me know about in the comments below, I will make sure to do a follow-up video to address the most sought after tutorials in Ignition that people have. So be sure to let me know in the comments below what you want to see more of. Thank you so much for checking out the channel. I appreciate your time. I hope this video was useful for you. Please consider leaving a like on the video, subscribing to the channel. It helps me out a ton. And if you want to become a super supporter of the channel, consider checking out my Patreon link at the description of this video as well. It helps me out so much, and I could not have gotten the channel to where it was without my Patreon supporters. So thank you all for watching, and we'll see you next time. Thanks. Bye.
Hello and welcome back to LeMaster Tech. In today's video, we're going to continue our introduction to the basics of controls and automation through practical tutorials. Today, we are going to take a look at tying a PLC into an HMI service and building your first HMI, or human machine interface. Our specific setup is going to be the Arduino Opta PLC using the Arduino IDE, the PLC IDE, and we're going to talk to Ignition for makers. So we've previously done a setup video on how to get started with the Opta PLC, as well as your first structured text and ladder logic languages. We'll continue building on those skills in this video. And then we've previously done how to set up Ignition for makers. So the basics, if you want to start from the same point that I'm starting this tutorial from, would be have Ignition for makers. It can run on any computer. It can run on your laptop. Ignition for makers and the Arduino PLC and PLC IDE hooked up, and we'll be in the exact same spots when we start this video. So today we're going to look at setting the IP address of the Arduino Opta PLC, setting up variables to talk over Modbus TCP, tying a Modbus TCP device into Ignition, adding tags from that device, and building an HMI, or human machine interface, a graphical screen that looks at the PLC. You don't need any project built in either of these already, so what we'll be starting from is an Ignition project that has no HMI, so we'll build a brand new project together, and an Arduino PLC that has nothing running on it other than the base code that is on there when you load a new project on there. So I have this count equals count plus 1, which if we watch it live, you can see that is the only thing running on the PLC is the default main code. So without any further ado, without me explaining to you where we're starting and what we're doing, let's just get into some of the basics together. So up to this point, we've seen a little structured text, we've seen a little ladder diagram, but we haven't tied the PLC into anything. So what we want to do is we want to give this Arduino Opta PLC an IP address, because Modbus TCP uses RJ45 connection. It uses an Ethernet connection to talk and send data over Modbus. And what's interesting is if you go to the resources tab of your Opta project and then you go to sketch, there will already be a commented out section for configure IP address, which is really nice, super useful. So all we're going to do actually is remove the comments. And this is actually just giving us what we need for it to talk over the network. The only difference is we don't want to keep this IP address. 192.168.1 is kind of fine for home use, but usually, and if you're in any kind of industrial setting, they'll have a different block of IPs they want you to adhere to. Super easy to adjust that. You just type in what you want the IP to be here. So I'll use 420.69.169. That's nice and secure. And then in the gateway, I'll say 42.0.69.1. That would be pretty normal for a gateway on any sort of like corporate network to be the same first three blocks as your device IP, but then .1 for the gateway. So that's all we're going to do to set the IP address on the machine, and that's really simple. We don't have to do anything additional beyond that. But what we do want to do so that this actually does something when we tie it into Ignition is we want to come into parameters and we want to just add a few variables here that will actually be able to monitor from Ignition. So if you go to parameters, this is going to be your Modbus addresses. So if we just add 4 things here real quick, we could add, let's say we want to add some tags for monitoring the user push button. So if you remember the Arduino Opta PLC from previous videos, we have a push button on the front, and then we have some LEDs as well. We have the red light, we'll just call it red. We have the blue light, and we have the green light. And it's important to note that we are not tying these currently to the red light, blue light, green light, or user push button. We're creating new variables, and we want to change them all to Booleans. But what we're doing is we're assigning those variables to Modbus addresses where they'll actually populate when something that can read data over Modbus TCP connects to these addresses. So this addressing is important when we get to the Ignition piece, and we'll take a look at it. But right now they're not going to do anything because we haven't tied them to anything yet. So let's take user push button, red, blue, and green, and let's tie them to the actual values that they need to be tied to. And to do that, we also want to come to LED outputs, and here we have LR, and so we'll call that LR, LG, and LB. And if you've been following along with the tutorial series, you know why we're doing this piece. And if you aren't following along with the tutorial series, maybe consider doing that. But basically, we are assigning the actual red, green, and blue lights on the front of the Arduino Opta, as well as the user push button, to variables that we can use in our main PLC program now. So if in here, we just come in and we say, like, first thing we want to do is set the red light to be equal to true, the green light to be equal to false, and then the blue light to be equal to the state of the user push button. So the blue light will change as we press and release the user push button. Then that would give us sort of those 4 variables populated. And then what we need to come down here and do is we need to say blue should be equal to LB. Whoop. So now we're taking our Modbus variables and we're setting them equal to the status of the variables we're controlling in the program. So the first lines were to actually set the state of our outputs. Oop, I'm trying to talk and type and that never goes well. And then user underscore PB is equal to user. So to recap what we're doing here, we're just telling the red light to be true, the green light to be false, the blue light to turn on and off with the user push button, and then we're telling the blue, red, green, and user push button Modbus variables that they should be equal to these variables that we're using in the code. So if we download this to the PLC and we hit yes and compile, it should compile without error. I don't always write perfect code, but I'm not that bad at it. It'll want us to restart, and that's okay. And then we'll initialize, and that's okay. Okay, so it looks like it completed. If we connect to the PLC,
We can also enter this cool mode that I don't think I explicitly called out before called live debug mode. And this actually lets us see the value of all of those variables. And what's cool is my PLC, which is on some DIN rail and connected to a power supply, so it's a little harder to show on camera than before. But what's cool is you can see the red light is on, the green light is off, and if I push the push button, the blue light turns on and off with the push button. So that's cool. That means that the PLC program took, and we should be all set now to actually tie it into Ignition. Okay, so let's go ahead now. We have an IP address set on this. We have a few variables that we can address here in our Modbus addresses. So let's jump over to the Ignition gateway. So you go to your web page. I have a lot of security on mine, very secure. All right, so for a Modbus device, it's a little different than adding most like tier 1 PLC manufacturers. Most Allen Bradley, Siemens, Beckhoff devices, like major PLC manufacturers that you'd talk to, you may go to OPC connections and create a new OPC connection. But if you have a device using a slightly older or slightly less common communication protocol, a lot of that times you're just going to go to config and then you're going to go to device connections instead. And for us, we'll create a new device. You can see a lot of their default browser default data types that they have in here, and we are just looking for Modbus TCP. Okay, and it's cool. It just needs a name and then a description. It can be first Opta PLC to Ignition for description. That part's optional. And then here you can enter your IP address. That's all you need to enter. And then port 502 is by default. You can leave that be and that should work. And just go ahead and create new device. You don't have to look at any of the advanced options or anything like that. If you hit create device and it says connected, your money. If it says failure to connect, it may give you a reason why here. It may give you information. You can try to open the command window and you can try to just ping. You can try to just ping your IP address. And you should be able to get a reply from it. If you haven't, I didn't explicitly call this out. Make sure your network adapter is on the same subnet. So make sure your laptop that is plugged into your Arduino or whatever computer is plugged into your PLC, make sure that Ethernet port is on the same 42.0.69 or whatever you're using. Make sure it's on the same subnet because Ignition can't see devices on different subnets unless you open them up and configure your network that way. The industrial networking side of controls and automation might be the least fun part of the job. But important thing while we're here on the device, it says connected and that's awesome. But if we were to, like, for example, use the OPC Quick client to try to browse the Opta for tags, we have basically nothing. We have diagnostics, which is nice, and it's proof that the device connected, but we have no useful data. We can't find those 4 tags that we added because they don't exist yet, because after you add a Modbus device, you have to hit more and you have to go to addresses, and then you need to add a row of the tags that you want to read from. So if for us specifically, let me find my notes. Good. We want to go add row. And then if we look back at the Arduino PLC, we start at 16.384, which means back in Ignition, minimize this, we can go to prefix. And here's where you just call it something you want to reference this. So we'll just call it Opta tags is fine. We'll start from 1 and we'll go to 4 because we only have 4 tags. And then you give it a unit ID. This part doesn't matter so much. I've used 255 multiple times. It really doesn't matter. You can put any unit ID number you want here. You just need to remember what that is when you're looking at the tags. This is the part that matters. 16.384 is where it starts. So now it knows to grab 16.384 and then go 4 bytes or words or addresses, registers is what they're called, from the first 16.384. So if we hit save, disconnected should turn to connected pretty quick. And now the difference is if we go to OPC Quick Client and we go to devices and the Opta, and now we have unit ID 255, which we just added, Opta tags 1 through Opta tags 4. And now if I subscribe by hitting this little S on all 4 of those, down here in the bottom window, it shows me the value of all 4 of those tags. It'll take a second to update because this is not the fastest tool. This isn't like scanning the tags live. But you can see we have 0, 1, 0, 0. If we were back in the Arduino PLC, we know that correlates to the user push button, the red light, the blue light, and the green light. So if I were to go ahead and hold down the user push button, you can see that the first tag and the third tag both turn to 1 because that's me pushing the user push button and the blue light turning on. So that's cool. Now we have tags that live in the PLC that are reading to Ignition. We haven't built an HMI yet, but we've verified that we can get tags into Ignition. So that's half the battle. It's actually over half the battle. So let's go to the designer launcher now, which is for Ignition. That's where you build your visualization. And let's go ahead to our Ignition session. Let's open the designer, and we're going to make a new project together so that we can do every step of this together. Username will be LeMasterTech because it's cool. And this is top secret and definitely totally different. Okay, so rather than open Arduino PLC tutorial, but I promise you there's nothing in there, we'll do Arduino Opta HMI. Project must start with a letter or underscore and contain only, okay, so it'll be Arduino Opta HMI all like that, smushed together. We'll copy that 3 times. I don't need to inherit anything, leave all these as defaults. Let's just create a project. Okay, so should be pretty similar to the default window you get when you open this up. Let's just go to perspective and let's go to views and let's right click and hit new view, and we will just call this homepage. Okay, so it's gonna give you a default window. I'm gonna hit save real quick, force of habit. Like every 3 seconds I impulsively do Control S and hit save. You don't have to. Perspective components. Let's go over on the right. You should have a little palette here. If you ever want to play around with the tools and toolbars in Ignition, feel free to. There's lots of panels and toolbars. Inductive automation is always adding new features to this stuff, so it's not a bad idea to comb through toolbars and check for updates and whatnot. But I use labels for a lot of stuff. So for this label, let's just call this our Arduino Opta PLC, and let's take 3 seconds real quick to make this label kind of look like our PLC, okay? I'm going to go to Style over here on the right. I'm going to hit plus, and I'm going to go to Background Color, and I'm going to make it dark gray. And I guess actually before we get too deep into this, or while I'm building this, we'll also go to Style, we'll go to Color, just color, and we'll make the text color white. And now I'm going to make it a little bit bigger because I'm going to drop a bunch of images and icons on it, and then I'm going to align vertical top. So now I have this rectangle. I'm going to drop inputs and outputs and lights and statuses on this HMI so that it looks like the PLC. I'm going to hit save, and I'm going to pause for just a second about what an HMI is meant to be and what you want to put on an HMI. So HMI, human machine interface, is what a conventional software programmer would refer to as their GUI or graphical user interface. It is where the person interacts with a virtual system so that they can control the outputs and monitor the inputs and interact with the physical system from an easy to use and easy to understand screen. So while it may look like I'm kind of rapidly building a thing and it's sort of like PowerPoint, the important extra piece to know is that you're linking tags and you're creating animations of objects based on those tags, and the animations of those objects, as well as the output actions from clicking on buttons and things like that, should go back and affect your PLC. So in addition to reading things like the statuses of lights and the status of your push button, you can also click buttons from an HMI that go and activate sequences in the PLC. So for basic first step, let's tie those three lights and the push button in so that we can get an HMI just working, and then we'll start building sequences that really show how powerful this is. So let's go into icon and let's look for a light. I went into perspective components. I know some of these tabs are a little small and I'm going kind of fast. I went to perspective components and I grabbed an icon. There's symbol factories, drawings. You can import SVGs. You can do a lot of different ways in a lot of different HMIs. There's also different syntax and all these different icons and whatever. But icons are kind of nice in Ignition because they're all simple objects, just like circles or smiley faces or light bulbs, and they're pretty easy to animate. So like if I want this to be tied to the user push button, I can grab it and I can say that I want to add a custom property that I'll call tag, and I'll put a tag path in here in just a second because I haven't added my Ignition tags yet. But what I want is the color of this button to change with the tag. And to do that, I'll go to indirect, which means I'm calling a parameter on this tag. Again, I do several Ignition tutorial introductions videos on my channel. It would take a lot of time to do all of the basics of Ignition and then a practical example together. So to keep this tutorial moving, I'm not going to deep dive every concept that we're doing, but I will try to still gear this at beginners. But basically, we're going to do an indirect tag binding, click the sort of hamburger menu over on the right, and go to View, Root, Icon 0. Icon 0 is actually what we're working on. You can see that highlighted on the left. And then custom parameters, and then tag. But what it really shakes out to is the tag path is curly brackets around tag, and then the property is this.custom.tag. All I'm saying is I'm going to grab a tag that I just want to pass in that text field, and I'm going to add one transform, which is just going to be map the true-false Boolean of whether or not the button is pressed to a color. So the output will be the color, and the input will be the value. And what I'll do is I'll say if it's true, then I want it to be, it's a push button, so color doesn't actually change. Let's say if it's true, then I want it to be black. If it's false, I want it to be light gray. And if I don't have any reading, I want it to be white. Okay? So it's white right now because there's no tag, which is a great opportunity for us to go and add our first tag. So I'm going to hit the little plus in the tag browser menu on the left side of Ignition, and I'm going to say Arduino tags, and I'm going to make a new folder. Now I'm going to browse devices. I'm going to expand out my devices, go to the Opta, go to Unit 255, and I'm going to add Opta tags 1 through 4 to my Arduino tags folder. Okay? And what you probably can see, so that a little arrow populates and all these zeros and ones populate. Modbus by default is going to call pretty much everything a short when you add it, but these are all Booleans. They're lights and push buttons, so I can select all the tags, right click, go to edit tags, and at the same time I can make them all Booleans. So I can bulk edit all of these tags. I could change them all to arrays or strings or whatever at the same time. I can make them all Booleans and hit OK or apply, and they'll all update to be Booleans. Now, Opta tags 1 through 4 isn't that useful, and if we go back to our PLC, you can see that it's user push button and then red, blue, and green. So what I'm going to do is I'm going to rename these user underscore push button as the name, and then red, and then green, and then blue. Okay, cool. So now close. Now I can right click on user push button and I can go to copy path, and I can paste that path right here, Control V, into tag. And now you can see, hopefully you can see that went from gray or that went from white to gray because now the tag exists. Now I'm going to push the button now on my HMI or on my PLC, and you can see it changes to black. That's really cool. I think it's really cool. If you don't, I don't care. Now let's get rid of this smiley face because we're not using it, and let's add in some additional stuff. So this is the push button, which is cool. Let's go ahead and just add the 3 lights as well. So the blue light on the PLC is kind of physically right above it. So let's say if that one's true, we want it to be blue. And then let's copy this over here. And the green and red lights are actually in the same spot. So I'll just put them right next to each other so that we can see 2 different lights. And let's say that this one should be green. Okay. And this one should be red. So all I'm doing is I'm changing the linking, the color animation on these circles to be different colors, but now I have to go and I have to copy that tag path. So I copy the path for blue, and I'm going to replace user push button with blue. But what's cool is the way we did that custom tag pathing, this will now update just when I click the blue button. But what you'll see is right now I've only updated the blue light and not red or green. So when I push the button, okay, all of them except blue updated. So my blue light tag is not actually working. Let's check that out in the code. A little live debugging together. Oh yeah, I called the green light blue and the blue light green. That can get you in trouble if you're not very careful about the order that you do things in. So we'll correct this to blue. We'll move this to green. So basically what happened there is because the Opta tags got added as Opta tags 1 through 3, I misnamed, I got blue and green backwards. So now if we go in here and we correct this tag path to be just tied to red, okay, and then this tag path to be just tied to green. Okay. We have, now if I push the button, you can see the black button getting pushed in and the blue light turning on at the same time. If we were to go back in the Arduino PLC, let's say, and just change from LR being equal to true to setting LR equal to, we gotta go offline. Let's say we want LR to be false now, and we want LG to be true, and we want to compile that and say yes, and send the new code. Now we should be able to go to, yep, we can go to our PLC, I can push the button in, and I can have blue, and the blue light turns on, and then the green light turns on, and red never turns on because of the code that we have running on it. So this is really cool. We have an Arduino PLC connected to Ignition, and we built our first HMI actually looking at tags off of the Ignition PLC. So in the next video, I think what we'll do is we'll build multiple sequences in ladder logic and structured text that actually interact back and forth with the HMI. So we'll take a look at controlling sequences from the HMI, reporting statuses, doing enumeration, and a lot more interesting SCADA, HMI, plus PLC development together. So today's video was a great way to get you connected, get tags reading back and forth. If you're a somewhat competent programmer, this can be a fun spot to play around and explore with animations and things like that. But this is really also the legwork so that the next chunk of this tutorial series can move along really well, and we can focus on programming, and we can focus on HMI development, and we don't have to get all of the basic interconnections done. So I hope you found this video useful. I hope you've been finding this tutorial series useful. I have really been enjoying using Ignition for Makers and the Arduino Opta PLC. All right, so I'll leave you with that. I'm looking forward to the next video. Please leave comments with any questions on what you saw here today or things you want to make sure we cover on future videos on the channel. I appreciate all the support, and as always, good luck with your projects, and thanks for watching. We'll see you next time. Thanks. Bye. Hello and welcome back to Master Tech, and today's video is going to be a continuation in our Introduction to Controls and Automation tutorial series. And in today's video we're going to write some pretty specific form of PLC logic called sequences. So one of the most common ways that long complicated routines get controlled to do things in order in factories is with sequential programming. And sequences often involve interaction from the operators at specific points in the sequence. So we're going to take a look at how to create a step and then a function where you step through it in order. And then we'll also add some features to the HMI so that you can see how the HMI could interplay with the sequence. And most important thing is, because this is kind of a continuation in a tutorial series, the concepts in this video stand alone, so if you just want to see an example of sequential logic being programmed in ladder logic on a PLC, you're in the right place, keep watching. But if you want to follow along line by line and build the same sort of things as we go, make sure that you have Ignition connected to an Arduino Opta PLC. You've already set up the Modbus connections, so I have it so that the red, green, and blue buttons, as well as the user push button, are already tied to my PLC. And then I have a PLC program where I've already set the IP address, set it up with Modbus connections, and created some very basic logic, including adding my first 4 Modbus tags. So if you haven't been following along with the tutorial series, but you really want to do this piece together, all you really need to do is watch the previous video on the channel. I'll try to remember to leave a link to it below, a card to it somewhere in the top of the screen now. But I don't want a ton of comments on this video that are like, oh, you jumped right into it with no context or background. So please get yourself in the same spot as me if you would like to follow along exactly. Otherwise, let's dive into the tutorial and the concepts in this video. Okay, now I've prepared a pretty simple prompt that is going to step out a 5-step sequence, and it's basically going to tell us what we should be trying to program. Because a really important thing about controls and automation is if you just sit down to write PLC code and you have no idea what you're trying to code, it gets really hard in terms of inputs, outputs, variables, what you need to put on an HMI. So anytime in controls and automation when you go to write new PLC code, you should have a basic vision of what you are trying to accomplish. Bit of a tangent, but basically step 0 of our sequence will be considered idle, and it'll just be waiting for an operator to press the start button on the screen. Then step 1, we're going to be activated, and then I still have the hand switch connected to my PLC from the wiring examples that we did a few videos back. But instead of the hand switch, you could use the user push button on the front of the Opta like we've been doing lately. It's up to you. But in sequence step 2, we're going to wait for a timer to complete so I can show you guys the timer function block. And then in sequence step 3, we're going to click a button on the HMI until we get up to a set point. So I'm going to show you how to create a set point on the HMI screen that operators can change and interact with, and then we will use that in our sequence. And then step 4 will be sequence completed, and it'll be sitting there waiting for us to send it to idle by pressing a stop button. Let's dive right back in. Let's dive into the programming. I'll probably pull up this notepad if we forget what the next step is supposed to be. I'll try to go slow. I'll try to explain everything as I do it. Hopefully a lot of this is familiar if you've been following the series along. So let's go ahead and go to our program. Let's go to project, and then we're going to right click and we're going to add a new program in LD, ladder diagram, and we will call this ladder underscore sequence, and let's assign it to fast task and hit OK. All right, so sequence step 0 equals idle, and we're going to wait for the HMI start button to be pressed. So the first thing we need to do is we need to check with an equals block. So EQ, we need to check if sequence step is equal to 0. So we're going to need a variable that we'll call sequence underscore step. And if it does equal 0, then we just want to tie this into the output line. So this should look familiar from the first ladder tutorial that we did. Okay, now we're also not going to worry about making all of these variables right now. I'm going to write the sequence, and then I'm going to go and look at what variables I used and kind of add them all at once. If that feels a little backwards, if you're more of a person who wants to define all of your variables and then use them, or define them as you go, you know, dealer's choice. But basically we have sequence step equals 0. We're going to listen then for a push button from a tag that we'll just call HMI start. Okay, and when the HMI start button gets pressed, that'll be something that we click on the ignition screen. So then we'll go ahead and start by resetting the HMI start push button. Okay, so you're going to turn it on from the HMI screen, and then the code will turn it off. But when it turns it off, we will also add 1 to the sequence. You could add 1 to sequence step at this step, or you could say move 1 to sequence step. It doesn't really matter. Just like any form of programming, there's a few different ways that you could write it. What's nice about this rung that we've built is it's sort of good for reusability. So we can copy it, and now we can say, all right, now sequence step equals 1. And I'm not looking for HMI start anymore. Now I'm probably looking for input 8, right? So I have the hand switch. If you don't have the hand switch still hooked up from a few tutorials ago, you could put the user push button right here. But instead, I'm going to put an HMI tag in that is monitoring input 8. Actually, yeah, that's fine. And then when it's made, we'll go to step 2. And then we could do the same reset, but that doesn't make a lot of sense because this is actually going to be looking at the hand switch. Now, the hand switch has on position and off position. And I specifically want to listen for the rising edge of the hand switch. So let's say you had left this on. I don't want it to automatically blast through this step. I want it to listen for a person to intentionally turn the hand switch on. So to do that, I'm not just going to use a regular examine if closed block, this regular normal contact. I'm going to use positive edge of the contact. So this is rising edge. This is as you detect that that Boolean variable transitions to a 1, pulse. So it's basically a 1 shot on transition high. So this step is just going to listen when we're in sequence step 1 and only when we're in sequence step 1 for the hand switch to turn on, and then it'll move a 2 into sequence step. So if we're tracking our little notepad of instructions, we have step 0, we're in idle and we're waiting for the HMI start button to be pressed. And then we have step 1, we've activated the sequence and we're waiting for the hand switch to move us to step 2. Now in step 2, we're going to wait for a timer to complete. So we haven't talked about timers yet. There's a timer on delay where when the conditions that make the timer start begin, the output is false until a set point is met. Then there's a timer off delay, which is kind of the opposite, which is where when the conditions to start the timer begin, the output is immediately true, but then when the conditions that make the timer true go away, the timer will then start counting and stay true for a period of time after that. That's a lot of gobbledygook and stuff to try to explain what ought to be a simple concept, but with PLC programming, there is just a little game within the game of knowing the nuances going on here. So let's go ahead and drop a new block that we haven't seen before, but it's TON, timer on delay. And just to show you real quick, there's timer off delay. So when you make function blocks like timers that have a few parameters to them, you have to give them an instance name. So for this one, we can just call it the step 2 TON, the step 2 TON. But the reason you need to do that is because there's an output tag, an input tag, a set time, and then an elapsed time, all of these 4 parameters, and they need to be stored in a variable or instance. Okay, so for this timer, we're going to go down to PT, and you can add constants. So if you know you always want it to be 5 seconds or something like that, you can put a constant in here. I'm going to want to tie it to a variable, which I will call, just call step 2 time. That's what I'll call the variable. And that'll be my my time that is set for the timer. So that's how long I want the timer to count up for, which will be something we'll let the user set from the HMI screen we're about to build. And then we will make, on the output of this timer completing, we will make it move to sequence step 3. Okay, now there's a few things. Oh, I have two moves here. Okay. There's a few things we're going to change now. We don't want the input of 8 anymore. We don't need that. But there is one thing about PLC timers that we haven't included yet, and that's that the default time for almost every PLC is in milliseconds. I don't want the operator, I don't want the user on the HMI entering a time in milliseconds. It's not that intuitive. It's not how people think. So I'm going to add a multiply block in here, MUL, and I'm going to drag it before the timer, if it'll let me. There we go. And I'm going to take the HMI time SP, so set point, HMI time set point. If you don't like my tag naming conventions, I don't know what to tell you. You know, that's okay. And then I'm going to multiply it by 1,000, and I'm going to store that in step 2 time, which is the name of the variable that we just defined. Okay, so what this line is doing now is saying when I get to this step, I'm going to take the set point that's on the HMI, and I'm going to multiply it by 1,000, and then we're going to use that value in the timer. So we'll enter a time in seconds on the HMI. This will convert it to milliseconds for us, and then once the timer finishes, it'll move us to step 3. Okay, and then if we remember step 3, we're going to have a counter. So we're going to have a target number of times a button has to get clicked, and we're going to keep track of how many times it's been clicked, and then once we hit our set point, we'll move to step 4. So this one's a little bit different, and it'll probably make more sense once we get to the HMI where you can see the interaction part. But I'm just choosing to sort of start in the PLC code, and then we'll move into the HMI all at once. So it's still not too bad. We're going to say now if we equal 3, and then we want to move to 4 when this step finishes. In the middle, what we're actually checking for, because we'll do most of the hard work on the HMI for this step. So what we're going to check for here is that we're greater than or equals. So GE, a new block. And we can delete the multiplication that was for the previous step. And we're going to want to check that HMI counter. So let's go ahead and make a new tag called HMI counter in here. And we want to check that the live counter gets greater than the HMI count, and we'll say set point, SP, right there, okay? And now we need to delete this block because what we want the output to be is just set the output line. Okay, so very simply, this line means when we get to step 3, wait until the HMI counter gets above the HMI count set point, and then move to step 4 after that. But one thing that we want to keep in mind is that if you were to restart the PLC or you didn't properly clear the sequence or anything like that, how do we guarantee that the HMI counter has been reset to 0 by the time we get to this step? One of the easiest ways is actually just go to the step before it and add some branching logic. Add some branching logic around your output conditions. Okay, and we're going to come down here and we're going to add a new block to just move a 0. So come over here. And here we're going to move a 0 into HMI counter. So this is just my way of saying I really don't care what's happened to that variable up until now. I haven't needed it in my sequence up until now, but I'm about to enter step 3, and I know I want that to be a 0 when I get there. So I'm going to set it equal to 0 before I get into step 3. So that's all we're doing there. And then that's really it for our sequence. So step 4 is sequence completed, press HMI stop to send to idle. That is basically exactly what we did with line 1. Since that's exactly like the first line, we have a really good thing to reference here already, and we'll just go ahead and say, okay, that was a coil, and we're going to say, all right, when I get to step 4, then I want to move to step 0 when HMI stop gets pressed, HMI stop. And if you remember from that first line, we also went ahead and we reset the output as part of that. So if we go over here, we also want to put HMI stop in a reset. That's going to say you wrote a 1 to it from the HMI. We're going to write a 0 to it from the PLC. All right, we did a lot of ladder here without looking at the HMI. We need to add a lot of variables, so let's try to do this carefully and methodically now. If we go into the resources tab and then parameters, I'm basically going to default to wanting every one of these tags in parameters because I want to give the HMI as much information as we can. So we're going to have sequence step, that's going to be an integer. We're going to have HMI start, that's going to be a Boolean. We're going to have HMI input 8, that'll be a Boolean and we'll tie it to my hand switch. We're going to have HMI, I spelled HMI wrong. We're going to have HMI time set point. Boy, I'm struggling to type today. Time set point. That'll be an integer where the operator enters something in seconds. We'll have step 2 time. That'll also be an integer. It'll just be multiplied by 1,000. And then we're going to have HMI counter. That's going to be an integer as well. And then we'll have, we could also put the elapsed time from that timer in a variable. So we could call that HMI elapsed. And we could make, that could be an integer as well. That's fine. So we can put how much time has progressed in another variable. So on the HMI, we could also show how far the timer has progressed. I just decided that was a good idea right now. Then we're also going to have the HMI count set point. So that'll be what you need to press the button up to. And then we want HMI stop. And I may have missed some things, but that's what we're going to start by making. So let's go into parameters. And we have the user push button, red, blue, and green from before. No reason to delete those. Let's just go ahead and add. And we'll add sequence step, and that can be an integer. And then we'll add HMI start. Careful on spelling. That'll be a Boolean. And then we'll add HMI I8, and that'll be a Boolean. Now we will add HMI time set point, integer. Add step 2 time. That'll be an integer. We'll add HMI counter, also an integer. We have HMI elapsed. You guessed it, that's an integer. We have HMI count set point, integer. And then we have HMI stop, and that's a Boolean. Okay. One thing that we need to do, because it's the thing that interacts with the physical world, is we need to go in here and we need to set HMI I8, here being, sorry, I should have clarified, here being the main routine that we set up in the previous video where we just mapped our lights and push button to we mapped our Modbus tags to the physical tags that actually represent them. So here we want to set HMI I8 equal to input 8, and we want to go to our programmable inputs and make sure that I8 or whatever. I have my hand switch wired up to I8 on my Arduino. So I'm just going to make a variable called I8 that physically represents the state of the hand switch. And then in main, I am mapping the HMI tag that we just made to share with ignition, and I am mapping that to the physical hand switch. All right, so I am naively optimistic that this is going to compile. Let's just go ahead and compile and see what we missed. And it appears that it worked, so let's go ahead and try to download it. A warm restart's required, that's fine. Initialize the database with default values, that's fine. Warm reboot, it says source code okay, so if you were to throw on the little live debug mode, which is a cool feature of Ladder and most PLC IDEs, you can see the live value of all of these tags come in. And so sequence step 0 is active right now. And if I were to click the HMI start button, or just within the code by double clicking, I can set it equal to true. What you can't see is that the HMI start went true and it immediately reset itself, but what you can see is that the sequence step is now 1. So now we're waiting for HMI I8 to go true. If I set equal to a 1, that one actually won't let me force it through because it's being overwritten in the main PLC routine. But what I can do is boot up my 24-volt power supply real quick, and I can actually trigger the hand switch. And if I go in here and I watch HMI I8, if I make the hand switch, it goes true. Okay, and actually, predictably, it went straight to sequence step 4 because our time set point is equal to 0. So the timer finished immediately and went to step 3. And then our counter is equal to 0. So it went immediately to 4. It's waiting for someone to press HMI stop. So if I go ahead and I write a true to that Boolean, it'll go back to step 0. So that's kind of as fast as you can walk through it just on the PLC to make sure it's working. So we added a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 new tags. We need to go into Ignition. And first thing from the gateway, if you were following along last tutorial, we need to expand our addresses to include those new 9 tags. So before we went from 1 to 4, this is super easy. Now we just go from 1 to 13 and hit save. The status is connected, which is great. The live screen won't change, so we open up Designer, Launcher, and we open our Gateway Designer. Open the Designer. All right, so we've got our home page. I'm gonna leave the Opta up there exactly like it was from last time. I don't have a problem with that. But I'm going to add to my tags. I'm gonna add a new folder and call these sequence tags. And then I'm going to browse devices and go to my Opta, and I'm going to go to my unit ID, and I just added tags 1, 2, 3, 4. I just added tags 5 through 13, so I'm going to store those in sequence tags. Okay, so I am adding all of the new tags that we just added in the PLC to the HMI. They're all zeros. They also all came in as shorts. But if we look back at our PLC real quick, we have sequence step, HMI start. We have the exact order we actually wrote on this notepad for easy reference. We have 1, 2, 3 bools, and so we need to change those tag types to bools. Modbus holding registers always look like 16-bit signed ints to Ignition if you don't tell it otherwise. So Opta tag 5 was the sequence step. Okay. Opta tag 6 was the HMI start. And you don't actually have to call them exact, and this one was a Boolean. You don't have to call them exactly what they're called in the PLC. It's just an easier way to keep them straight. HMI input 8 was also a Boolean and was the next tag. And then HMI time set point was an integer. And the next tag was step 2 time integer. Okay. The next tag, HMI counter, and that's an integer. Okay. Step 11, the next one, HMI elapsed, and that is how much time has passed. That can be an integer. The next tag is HMI count set point, integer. Okay. And the last tag will be HMI stop, and that's a Boolean. Go to the PLC. Okay, HMI start needs to be, oh, well, it is case sensitive, so this needs to be a capital S for HMI start. Do you want to reassign this variable and use it as parameter? Yes. Okay, so that should be a Boolean. That should work. This should also be a Boolean. And then this should also be a Boolean. That should work. All right, I'll the addressing should still be fine. And then I guess since we have to download anyways, we can go back to our ladder sequence really quickly, and we can add that elapsed time that I forgot to put in here. So if we go back to resources, we just called it HMI_elapsed. Let's go to our timer block and let's add a variable to the ET, and we called it HMI_elapsed. Okay. And one thing to call out here that you could kind of see, which is also kind of nice, and maybe I did this in a bad order. If you define all your variables that you're going to need for your routine before writing your program, then they're available when you go to add variables, and you can see that they exist and what data type they are. So maybe I did a little bit backwards. I'm not perfect. Let's compile and download and restart the PLC. Initialize the database again. Okay, so with all of our tags added, we can finally do the fun part. Depends who you are. I enjoy the graphical user interface, the HMI development portion of the job. Let's go ahead and add that sequence step, right? So to the visuals, and Ignition's kind of nice. You can just grab a device or a tag and drag it onto the screen. And based on what type of tag it is, it'll show you all the recommendations for it. So like an integer, by default, they have gauges, one-shot buttons, cylindrical tanks, labels, things like that. So we'll just do a label for the sequence step, and then we'll build some more cool features into it. But let's go ahead and do little checkbox buttons for start and stop. And the text, we'll say start for the start button. That seems like a good thing to say. And then we'll say stop for the stop button. So the text stop. Cool. And then we'll throw, what do we want to throw? We want to throw our set points on the screen as numerical entries. So if we click the little palette over on the right, perspective components toolbar, we'll type in numeric entry field and drag it onto the screen. And the value will be what it's asking for. It'll be asking for a tag. So let's make this one our count set point. And we'll say value tag path count set point, and make sure to click bidirectional so that people can write to it. Okay, so this is our count set point. So why don't we go back to perspective components and add another label that just says count set point. So count set point, and that doesn't have to be linked to anything. It's just telling us what this numeric entry field is. And then we had one other thing that people could edit willy-nilly, and that was time set point in seconds, right? And that has to go to a different tag. That one needs to go to HMI time SP. So time SP. And I know some people are going to be furious at my lack of consistency with capitalization and camel case, snake case, made up case, you pick it. Okay, but so that'll let us enter a time set point. That'll let us enter a number of times to be counted. So then the only other thing I want to add real quick is I want to add a button, perspective components button, that is going to add one to the counter. So if you remember, we get to a step where, I also want to add indication. Let's finish that counter first. Press to count up, okay? So we're gonna make a little button, and when you press it, the count goes up, and then we will show the counter right next to it in a label. So this is the HMI counter tag, and then on click, so button, right click, configure events, we're going to do a little script here, a little ignition script to add one to the value when the button is pressed. So we go to mouse events in configuration events, on click, press the plus button, and we're going to do a quick little script that is going to be val equal to, so the current value of the counter is equal to system.tag.read blocking, and that's a little bit of just ignition syntax for you. The tag path is going to be that counter variable. So we're going to say read the value that the counter currently has, and then little Python syntax fun that we get to play here is if we actually want the value, we say square brackets 0 dot value. So this is how you get the actual value that is in the counter tag already. And then what we're going to say is value equals val plus 1. Okay, so we're just saying, you could just say val again is equal to val plus 1. But now we're going to do system.tag.write blocking. And in that same tag path, we're going to write value. So we're just adding 1 to the value of the counter when that button gets pressed. And what's cool is it'll let you click the button at any time, but what you'll see is when we get to step 3, which is where it's actually checking it, you'll see it get reset to 0 because we only care about it when we get there. So you're starting to see how the HMI and the PLC work together to create a system that the operator has some control over, but the PLC can also be programmed intelligently to protect it. So this is how we just make a button in Ignition to increment a value. And let's see, what am I missing? When we're in step 0, we're idle. We press start. We should go to step 1. Yeah, we want to monitor input 8. And actually, to do that, I'll grab one of these buttons that we made in the previous step. This was the blue button. And I'll just drag it up here. This is input 8 up here because that's kind of physically where it is on the Arduino. And we'll have it, when it's true, we'll have it go pink. I don't care. Pick a color. All right, so then all I have to do is copy the path for that tag, and I have to say, hey, here's the tag that you're animating off of. Again, I'm assuming you watched the previous video and you know that we set this tag parameter to tie into that color animation. Okay, so real quick, we can check that color animation because I have the hand switch right here with me, and we can see whether the hand switch is on or off. Okay, very cool. So obviously it looks like crap because we haven't formatted it. We haven't made it stylistically pleasant. We don't animate things whenever. But let's go into read-write mode real quick for the gateway. So that's what these two little arrows are. And right here in the designer, we can toggle into preview mode. So now we can interact with the things. Let's say when we get to the countdown step, we want 5-second countdown. And when we get to the count up step, we want to have to click the button 3 times. Okay, I'm going to enter those. You can see right here, I can start counting up just by clicking it, and the counter is at 8. What's cool is when we get to the count up step, that should go back to 0, and we should have to start over again. One thing we didn't add, but I want to put here, is the elapsed time, and I'm going to put it in a label. But where did it go? Oh, there it is. But you guys are going to see something cool. Let me go up here. You guys are going to see that this value is going to come in milliseconds. So I'm going to let it do that this first test through, and then I'm going to show you how you can scale it in the HMI. You could scale it in the PLC. You can scale it in the HMI. Just kind of pick something and try to be consistent on your project. So we're in step 0. I hit the start button. Now we're in step 1. And we're waiting for HMI, we're waiting for input 8. So I'm going to turn the hand switch. And now we're in step 2, and you can see the counter counting up. And when it hits 5,000, we go to step 3. Okay, pretty cool. And now it's waiting for us to count up to 3. So you see this was 8. Now it's just waiting at 0. So we click once, twice, a third time. Now we're in step 4, and we press stop, and it goes back to 0. Okay, so the sequence step is working, and that's really cool. What's not great is it doesn't tell you anything useful. So what we're going to do is we're going to add a transform, and we're going to map it. Okay, so this is very common when you have a numerical value that tells you something that you would prefer to explain with text. A common way to refer to this is enumeration. Enumeration just refers to taking a integer value or a numerical value and it telling you more than just a number. It's telling you a string of text, but it's easier for PLCs to pass a simple integer back and forth than long strings. So in 0, we're in idle, waiting to press start button on HMI. That's the text that we want to display in step 0. Oh, there we go. In step 1, we're active waiting to see input 8 transition high. In step 2, we're active, waiting for timer to complete based on time set point. Step 3, we're active and we want to wait for pushes to reach push count up set point. You can call it whatever you want if you don't like my step names. And then step 4, we can say complete. Press stop button on HMI to idle sequence. And what's nice about Ignition too is they have a feature called fallback, which is, I don't know how I got here. And we can just basically say sequence step somehow out of normal boundaries. And that's just basically saying you should not have been able to get here. Here's an error message telling you that something bad is happening. That can come in handy a lot. So we're going to make that label a lot wider because that text is a lot longer. And then other than that, I think the only other thing I want to do right off the bat is I want to take this thing on the screen and I want to make it in seconds. So what we're going to do is we're actually going to make this scale mode linear, and I'm going to say, okay, well, it's showing me milliseconds, but I want seconds. So if the raw high is 1000, that means the scaled high is 1. And as long as you don't do clamp mode, then it will automatically say, okay, even if I'm more than 0 or more than 1, that's okay. And then we'll make the value a float. Since now we're dividing it by 1000, we'd like to see decimal precision. Okay, so this should be a little bit better now when we test through it because it's giving us instructions. And we'll actually open the web page now. And we'll actually open the web page now and we'll run it from here. So I'm going to go ahead and hit start. I'm waiting to see input 8 transition high. And you can see it's already high, but we put in that positive transition bit. So it needs to see it high again. And here you can see fractional seconds counting up, which is nice because we set the set point in seconds. Now we need to count up to 3, 2, 3. And now we need to press stop on the HMI. Okay, we can pretty easily say, let's make the count set point 11. Let's make this time set point 7. And let's do it again. Let's press start here. Let's flip the hand switch. We're going to get to 7 seconds. We're going to count up to 11 clicks. And now we've finished the sequence. We can hit stop and we're back to idle. Overall, this was a challenging tutorial to put together because where to start, how to make it useful, how to explain the concepts but not get bogged down in the details was all a little bit daunting. I do hope you found it useful. I think we're getting to the point where all of the basics have been covered, and I think we want to build one complete automation and controls project together. So I am looking forward to doing that. I am already sort of fleshing out what that's going to look like and entail. So as always, be sure to ask any questions that you may have in the description below. Thank you so much for watching. Let me know what you want to see next time on the channel, and keep an eye out for more controls and automation tutorials. Thanks. We'll see you next time. Bye. Hello and welcome back to Master Tech, and in today's video we're going to continue our controls and automation tutorial series by introducing the concept of a historian or a continuous trending tool, as well as SQL, which is kind of a more conventional database tool. So by far these are the two most common ways that data gets represented in the world of industrial automation and controls. SQL stands for Structured Query Language. There are ample tutorials on the internet on how to get started with SQL, but specifically how to embed it within like a controls and automation project. is very much like an automation concept. And then historians are sort of the standard for continuous trending of automation data. So if you are just watching this video on its own, it will stand alone as a tutorial on how to use both the historian tool and create a SQL query from Ignition, which I think is useful on its own. But if you've been following along with the tutorial series, you know that we physically have this Arduino Opta PLC. We have the button and the blue light and the green light and the red light all tied to the HMI on Ignition, and then as well as input 8 there in the top right corner, which I have a physical hand switch for. So when I make the hand switch, we can see that input 8 goes on. So in the last video, we kind of introduced sequential programming, and we made this sequence where we could start, we could wait to see that hand switch go high, and then we start a timer that's going to count to a set point that we can adjust, and then we need to click this button until we get to a target value, and then we press stop. Okay, so I have a sequence. If you don't want to follow along exactly with my example, that's okay, but you should have something sequential that you want to track if you want this to be like a practical hands-on example for you. So we're using Ignition for Makers, which is a very popular SCADA supervisory control and data acquisition software. We're using Ignition Maker Edition, which is an awesome free tool that Inductive Automation put out. We have a basic HMI project that shows some of our tags, and then we have the Arduino Opta PLC sharing data with Modbus TCP data. So we're going to go into the designer of Ignition, and we're going to take a look first at a very simple continuous trend. So one thing to note is when you start storing data, when you start looking at data history over time, you need some version of a database to store that in. One really nice feature of Ignition for Makers and the industrial version of it is it'll by default have a sample SQLite database enabled, and it'll use some of the storage of your computer by default because SQLite is just a file. So it's a way of storing data that looks like, you know, Microsoft SQL or any other sort of like table and columns and rows version of SQL. But SQLite is just a file. So by default, we don't have to do anything special in Ignition. We have one connection to a database, and it's a sample SQLite database. That's really important because anytime you want to store data, you have to store it somewhere. Okay, now let's go ahead and just pull up the HMI that we were developing before. It's kind of just a little square here, and I had it mode fixed. So what I'm going to do is zoom out a little bit and widen it to be a little closer to the width of the screen. I'm going to hit save, and then I'm going to do one thing here. I'm going to change mode from fixed to %. So now it should scale with the screen. Before we did that, if we were zooming in and zooming out, all those objects would also be zooming in and out, but now it's scaled to always be full screen. So it's just a little feature of Ignition in particular. But that also means if we want to add a trend over here, we can. So if we hit the perspective components palette over on the right, I'm just going to grab a power chart, and I'm going to drag it onto the screen. And what's really cool is you don't have to tell it what tag to look at or anything. You just drag this power chart onto the screen, and Ignition has a pre-built object that will let you browse tags within that. So just by hitting save and going back to the web page, you can see this chart is on screen. The only problem is there's only example data in here. So I have tags that I added before for testing, and then they give you these sample tags of realistic values to show you what navigating it looks like. But since in the designer we haven't added historical data to any tags, we're not seeing anything, okay? So if you've been following along with the tutorials, you should have the same tags, but if you don't, that's okay. I don't have data trending enabled on any of these tags, so let's grab a few that we might want to historize. So sequence step is a good one to start with as an example. If I want to see the sequence step over time, that would tell me where in the sequence it was over time. And all I have to do when I open the tag editor is go to history, and then true, and then I need to give it a storage provider, which in this case will make that sample SQLite database. And then there's a few important things here. There's deadbands, there's deadband styles. You can leave most of these on the default and it'll just start working if all you do is enable history and give it a storage provider and hit apply. It's important, I think, to call out onChange versus periodic, because onChange by default will only store new values when the value changes. That's kind of like a memory optimization, but you can tell it no matter what, I want it to store at a certain periodic interval as well. So we'll leave it as onChange, and I'm going to hit apply and OK. And so now it should have history enabled. And let's go to that web page and let's open the tag browser. And let's browse through this to default, and then sequence tags, and then sequence step, and let's add that selected tag here. So if I collapse the tag browser, what you can hopefully see, although it might be hard on the recording, and we can click this xtrace tool which tells us the value, we can see that sequence step is a constant 0. And if I change my real-time value to show the last 5 minutes and hit apply, and you can always edit that here in the set date range. But if I show the last 5 minutes, now let's go ahead and start that sequence, and I hit start, and it should go to step 1. And you can see this trend jumped right to 1 in real time. Now it's waiting to see input 8 transition high, so I'll go ahead and turn that hand switch, and you can see the value jumps up to 2 right away. Now it hits our 5-second timer, and it jumps up to 3. Now it's waiting for the pushes to reach the set point. 1, 2, 3. Should jump up to 5. And then if I hit the stop button, the sequence step goes back to 0. So it's really cool. You can see just right there us stepping through the sequence. So if I were to go to time set point 10 now, and we did it one more time, kind of as fast as we can here, hit start, turn the set point on, and then it's going to take 10 seconds. And then we count up to 3. And then we hit stop. But what's cool is you can see between those 2 runs, step 2, which is the time-based step, was 5 seconds here and was 10 seconds here. And we can narrow that window as well. We can say last 2 minutes, and you get a more precise graph going. Okay, so that's going to do it for our very basic introduction to the historian, because that is objectively the simpler of the data tracking tools that we're trying to cover today. Kind of like I said in the outset, when you just want to see process data continuously over time, a historian tool is great for that and is plenty to do that. But when you want to create a more, I guess, logical data story over time, and you want to tie what time I started, what time I stopped with, what were these settings at that time, who was doing that work, that's usually when you want to go to something like a SQL database. And like I said, we have a SQLite already here in Ignition. Again, if you're not using the Ignition platform, I guarantee your SCADA supports some way of interfacing with a database like a SQL tool. You just have to do a little reading on how to connect insert name of your SCADA or HMI platform to SQL, and I guarantee someone's done it. All right, so from the Ignition Designer, I'm going to go ahead and go to the database query browser. And I previously had a sequence data table while I was testing. I'm going to go ahead and delete that real quick with this drop table command so that we can rebuild it from scratch. So I had sequence data, I just deleted it there, so you guys can follow the exact steps that I do. So I'm going to kind of think about our sequence real quick and the things that I would want to add to capture how the sequence was running. So I would want to capture the time it started. I'll call that start time. I would want to capture end time. I want to capture what the time delay set point was and the count set point were. And then potentially a username if someone was logged in. And then maybe like a run count, an ID that says, hey, this was run 1, 2, 3, 4, 5, 6, and it just keeps incrementing up, okay? So I don't have all of those variables defined yet, but I have many of them. We're not gonna worry about the tags existing yet. We're gonna make that table first. So let's go back into our tools, and let's go into our database query browser, and let's create a table in the query browser that's going to have that data that we want. So to do this, we're going to say create table. And at this point, you guys have probably seen Ignition can use Python in some places. It has specific Ignition syntax for certain things. This is SQL syntax, and in particular SQLite, but all SQL is pretty similar if you know what you're looking at. So we're going to create a table. We'll call it sequence data, and we'll expand these parentheses out. And we'll have a field called run count, and we'll make that an integer. And we'll make this the primary key. So you don't have to know about keys and primary keys and stuff to build a simple table. You don't have to include that primary key bit. But if you want something that is like unique for a table, which would be a primary key, you're saying, hey, run can never repeat itself. If I already did run 1 or run 2 or run 3, I can't have another run 1 or run 2 or run 3. That's going to corrupt my data. So you can make that a primary key. And then we'll have a username, which will make a varchar 50. If you haven't seen that format before, that's SQL's way of saying it could be a string. Varchar means variable character, and you can basically pass anything in there. Okay, and then we'll say start, date, time. And the reason I'm putting null at the end is kind of SQL's format for saying, do you want that field to be able to be left empty or not? And in my case, I'm actually okay if any of these fields get left empty except for the run count, because I'm sort of just trying to prove out the function. But a lot of the times you might say, hey, a row of data is going to be useless if I don't have start time or end time or a username. And in that case, you would say not null. Click count, int, null. Okay, so what I am doing right here with this command is creating a table that has an integer for run count, a string variable character for username, a date time parameter for start time and end time, and then I'm going to store the set points for time delay and click count. And if I hit execute on this, and then I refresh my little browser over here in the right, you can see sequence data has those 6 columns. And a statement that we'll use a few times is I'm going to select all by using the star from sequence data. Okay, and if I hit execute, you can see nothing exists in there. And that's actually what we expect. We expect nothing because we just made that table. So we're going to go ahead and close this. And what we're going to do next is take a look at from Ignition, from our sequence, how to store that data, how to trigger events in our Ignition sequence that are going to write data to SQL, and that'll give you an example of how to store batch data out of a sequence that you might have written in the PLC and are monitoring from an HMI. So very cool interconnected automation and controls concepts going on here. And to do this, we're going to add a few new tags. So we had our original Arduino tags from our first example of tying Arduino into Ignition. We had our sequence tags from our additional sequence. We're going to make a few new tags just so we can keep track of when we added what. So we're going to make a new folder called SQL tags, and I accidentally added it inside that folder. Let's go ahead and liberate it. And we need to add a few new tags. One of the first tags is going to be a new standard tag. I'm going to make it a memory tag, and I'm just going to call it run count. Okay, and we're going to leave it in the default tag group. It's going to be memory, it's going to be integer, and to start, it'll be a 0. Okay, so the run count is going to be that primary key that tells us how many times we've run through this sequence. And we're going to make another new tag, standard tag, memory tag, and this one we'll call username. Okay, so if you were going to log in, you could store that info in a string tag. Initially, we'll say it's Pete. That sounds like a cool guy. And then the last new tags that we have to create are start time and end time. So I'm going to do new standard tag, memory tag. This format is going to be date time, and we'll call this start time. And actually, getting a little bit ahead of ourselves here, but I'm going to only make start time, and we're not going to need a tag for end time because we're going to use the trigger event that finishes the sequence as the time to go do end time. All right, so there's just me adding the tags that round out what we're going to write to SQL because everything else already existed. Let's capture the start time of our sequence. So when we click this button for start and we're in step 0, that's when we go from step 0 to step 1. So I'm going to click on the sequence step tag and I'm going to go to scripting, and I'm going to go to value change, and I'm going to add a little if current value dot value is equal to 1 and previous value dot value was equal to 0. So here I'm taking advantage of the tag change event, which has current value and previous value as parameters of the event. And technically this sequence only ever goes to step 1 from step 0. So this is kind of an over-engineered statement, but we're going to leave it. And I'm going to say, okay, that means someone just started up the sequence. So I'm going to system.tag.write blocking, which is the ignition syntax for writing a value to a table. And I'm going to copy the path for that start time tag that I just made, copy path. And I'm going to paste that path in here. And then I'm just going to say use system.date.now. Okay, so this is Ignition's like system formatted. Go grab a timestamp of what my computer says it currently is and store that in a tag. And I'm gonna hit apply, and I'm gonna hit OK, and I'm going to hit save. And now we're going to go back here and we're gonna hit start real quick. And now we're in step 1. And if we go back into the designer, now we can see we have, August 12th at 10:17 p.m. stored in start time. So that's cool. That tells us that our script worked. Now we've got the time capturing into start time, which is very cool. But to actually write to SQL, we need to hit a database, which is technically a gateway scoped thing. So we're going to go to gateway tag change events, and we're going to go to tag change, and we're going to create a new event, and we're going to call it write to SQL. But basically we're going to say when that sequence step tag changes, when the value specifically changes, so not the quality, not the timestamp, but the value of that tag changes, we're going to trigger this write to SQL script. But we don't want to trigger that script every time the value changes, only when it resets. So we're going to start by doing system.tag.read blocking on that sequence step, and then square bracket 0.value. That's just a little Ignition specific syntax for how to read the value out of a tag. And we're specifically going to say if value equals 0. Because value equaling 0 means that the sequence has just reset. This is an on tag change event script. So the tag is only changing to 0 when someone hits stop because it was in sequence step 5. So that's when we're actually going to trigger write data to SQL. Now, all we really need to do is we need to go out and read all tags that have SQL data. And then we're going to do a section of define the SQL query and arguments. And then we're going to call the SQL query and increment the counter. So if you remember, we have like a counter variable. It's currently at 0, and we're going to increment that every time we do a new run. Okay, so these are kind of the 3 sections we have to create in this script, and it's immediately, hopefully, sort of apparent why you don't want to do this just on a tag change script. It's a little bit easier with gateway events to keep revision control and sight on things like that. So we're going to read all the tags that have SQL data. And if we remember our table, we want to start with start time. And I'm going to try to keep the convention, of first letter lowercase and then all following words. What is that called? Snake case, I think, or camel case. I get the 2 backwards. Okay, in any case, we need start time, we need end time, we need the username, we need the count set point, we need the time delay set point, and we need the run count, that unique parameter. So we need to read all these tags. I'm going to steal this system.tag.read blocking command here, and I'm going to just replace the tags. So start time is going to be that start time tag, copy path, and paste it in here instead. And then actually that isn't what we want it to be for end time. We want system.time.now. No, system.date.now. Come on, Pete. Getting tired. So we want system.date.now for end time. And then for the username, that's going to be, we're going to copy this line and look at username instead of start time. So we're just going to update this bit to username. And to write basically all we're trying to do, just to be super clear, is that when we write a SQL query, we need to pass in all of the data we want stored in SQL. So within our script, we have to go out and grab the data that we want it to read. You can read all of these tags in one line of code. I think it's a little easier for beginners to see it broken out this way. So let's go ahead and say run count is this, just run count like that. And then time delay set point is actually copy path in a little bit of a different location. So we'll copy that one. And then count set point is right next to time delay set point, but it's called HMI underscore count SP. Okay. So that should give us the 6 fields that we want to write into SQL. One thing that is worth calling out, so we've got start time. We're actually going to format start time here. We're going to use a command called system.date.format because the ignition date and what MySQL or SQLite uses are slightly different. So we're going to take that start time and we're going to explicitly tell it to be 4-digit year with YYYY, 2-digit month, 2-digit day, and then 2-digit hour, 2-digit minute, and then 2-digit second. So we're explicitly defining a date format because SQL will throw an alarm, throw an error if it uses the exact ignition format. So we're going to make this new variable start and end instead of start time and end time. And they're just going to have the transform data. You can do system.date format and system.tag reblocking on the same line. I think it's easier to split it out this way, especially for beginners. But if you look at this tag, and if you were to see that printed, it's got PM on it, and it can also, depending on the ignition statement, it can sometimes have the date too, like it'll say Monday, the whatever. So this is just us explicitly calling out a format that we know SQL will support. Okay, so we've got all of the raw data we need. Now we're going to define a query. And this is a cool thing about Ignition. You can just write simple queries in a string of text. This is true of Python as well. If you're a bit of a Python programmer, we can just type in insert into sequence data, and we can say username. Let's go real quick to the database browser, query browser, and make sure I get all these column names right. Whoops, where'd they go? Yeah, so we've got run count. I'm just going to take a snip of this real quick. Run count. No, I'm going to leave it up the whole time, even better. Gateway events. Okay, so we want username like that. So this is case sensitive, which is the main reason I'm being extra careful about this. Oh, where'd my gateway event go? And we're going to insert using. Now the order also doesn't really matter. It's okay that we grabbed the order in a different, grab these raw tags in a different order that I'm defining them right here. Click count. What else did we have? Let's just finish typing these in so that then I can talk. Time delay, start time, and end time. Okay, what I was trying to say is it's okay that these are in different orders because then we say the values are going to be parameters that we pass in. So we do that with these question marks. So there should be 6 parameters that we're passing in. So our SQL statement is just saying we're going to insert values into those 6 columns. And the values are things we're going to pass in. They're going to be arguments. So args is equal to, and then a square bracket. And here I'm going to do a little typecasting. I'm going to say, okay, string username. It's never a bad idea, even if you're pretty sure it's already the right format, to explicitly make sure that it gets defined as the right format. So like run count needs to be an integer for it to work. Click count, same deal, which what do we call click count? Count set point. Count set point And then we have the time delay set point, same thing, that needs to be an integer, time delay SP. And then we have our start time and our end time. And actually for another just my SQLite thing that I'm sharing with you all is that casting it to a string in the correct format is the best way to ensure that it gets stored in SQLite appropriately. So there's a little bit of just knowing how to play the game here. But basically what we've done is we've said username, run count, click count, time delay, start time, end time are going to be passed in as 6 parameters. That's what the question marks mean. And then this order is very important. These need to correlate to the column order that you just did. So it needs to be username, run count, click count, time delay, start time, end time. Now there's only 2 lines of code left and then we're done. We want to do system.db.run prep update, and we're going to pass in the query and we're going to pass in the arguments, and then I'm going to delete out all the other auto-generated stuff. System.db.run prep update, query in the arguments. And then the last thing I want to do, which will also show us when we run it that it's working, is I want to do system.tag.write blocking, and I want to write to the count set point, no, run count. I want to write to this tag, a value of run count plus 1. Okay, so this is me saying, hey, at the very end of logging data to SQL, I want to increment the run count parameter by 1. Okay, so we're going to go ahead and hit save, and to see if it's working, we're going to go ahead and run through the sequence. So, all right, let's count up 1, 2, 3. Now it's in step 4. Let's go ahead and hit stop. Okay, now it's idle, it's ready to go again. Let's go ahead and go back to the designer, and you can see run count is 1. So if you weren't looking before, it was 0. To make sure that it actually got to SQL, we'll go to tools, we'll go to query browser, and again, we'll go ahead and select all from sequence data like we did before, hit execute, and that's pretty cool. Now we have run count, username Pete, start time, end time look accurate. I had a pretty big break between when we started and now. The time delay set point and the click count. Okay, so let's go ahead and go back there one more time. Let's say now the count set point is only going to be 2, but our time delay is going to be 5 seconds. And in the designer, you could make it a label on the field, but in the designer, I'm just going to change the username from Pete to Peter. And let's go ahead and start this thing again. So start, and waiting to see input 8. There we go. Time set point, count up to 5. Count set point, count up to 2. And press stop. Okay, so back to designer we go. And now we can see run count is up to 2. We go ahead and we go to the query browser and we search again. We have 2 entries. So one last thing, because it's nice to tie it back into a visualization. In SQL tags, we're going to add a new tag and a new standard tag and a query tag. And we're just going to say SQL results. I'm trying to go pretty fast now because I know how long this tutorial's gotten. And we're going to make this a query tag. We're going to make it a data set. Data set, I know you're in here. There it is. And we're going to just make it every, let's say 10 seconds. No, 5 seconds. What the heck? It's not doing much. We're going to make a query that is just going to be select all from sequence data, just like we've been running. And the data source is going to be our SQLite database. I'm going to hit apply. And now I'm going to drag that SQL results onto the screen, and I'm going to make it a table. And one Ignition thing, I've seen a lot of forums, a lot of people are like, why do my dates look jacked up? This is just a little bonus lesson for you. When you have a table, you need to explicitly define the columns are date time to get the date and time to look correct. So if we go to columns in the table and we add array elements and we say 1, 2, 3, 4, 5, and 6, we can go to 2 and 3, which in this case are start time and end time, and we can say start time, and then you come down to date format, date time, and there you go. Start time looks good. We can do the same thing, go to 3, end time. This very much is a tidbit of useful if you're working in Ignition. No other SCADA that I've seen has this like explicitly needing to define dates and times. But we're not going to worry about that. We have a table on the screen. Let's go ahead and run it one more time so you guys can see this power of live updating. So we're going to start it again. Let's change this to 6 and this to 4 and transition the hand switch. We've got to wait 6 seconds. So we should have one now that shows starting after this 2303. 1, 2, 3, 4, and push stop. And within 5 seconds, this table here should update. There you go. It's way less than 5 seconds. New start time, new end time, new time delay, new click count. Okay, so we've seen just in a couple minutes, we've seen how quick and easy it is with a good SCADA software to be able to monitor live data. This same tool can go back in history pretty far, so you can look at days or weeks past as long as your computer's retaining it. And you can look at continuous trending data like that. You can look at SQL data like that. Far and away, Historian and SQL are the two most powerful data analysis tools for automation and controls engineers to get familiar with. So I hope you found this to be a useful introduction. I hope you have found the introduction to the automation and controls tutorial series, if you've been following the whole series, to be super useful. We've covered the majority of the basics to the point where you should at least understand the major fields that we're addressing. So as always, if you have any questions about what you saw in this video today or things you'd like to see in the future on the channel, be sure to let me know about them in the comments below. Thank you so much for watching, and we'll see you next time. Thanks. Bye.
Welcome back to Master Tech, and in today's video we are going to continue our series on industrial automation and controls tutorials with a quick but super important and useful concept, which is adding I/O expansion modules. So with pretty much any PLC manufacturer, Allen Bradley, Rockwell, Siemens, Arduino, you're going to run out of input and output channels with whatever came on board the PLC module itself. In fact, some of the high-end Siemens and Allen Bradley PLCs are just CPU modules. They're just brains, and they don't have any I/O on board. So you design a project, an automation system for a certain number of inputs and outputs, and you need to be able to add I/O modules to those PLCs. So the Arduino Opta line is a pretty new line. They only have 3 expansion modules that they offer right now, but it covers all of the basics. They have 2 different versions of input and output, digital input and output cards, one that has electromagnetic relays and one that has solid state relays. And then they have a little bit of a grab bag card that has pulse width modulation outputs, analog inputs, analog outputs, as well as a few conventional input and output channels as well. But the important thing is you design an overall system, you make like an I/O list of the total inputs and outputs that you're going to have, and you need to be able to add these modules to your PLC. So we've been doing this tutorial series with the Arduino Opta PLC, so we're going to continue using that in today's video. Whatever PLC and system you have, just know that your manufacturer should provide all sorts of recommendations for cards that support digital inputs, digital outputs, analog in, analog out, I/O link, Profinet, high-speed counter. There's so many different variations on inputs and outputs, RTDs and thermocouples. You just need to look up the card that's compatible with your PLC, or you're following along with this Arduino Opta series, and I'll leave all of the cards that I'm using linked in the description below this video if you want to follow along exactly. So that we start from exactly the same spot, I'm going to just make a new project for this tutorial, and I'll call it I/O add-ons, and I'll just make a brand new project. And then in terms of my physical setup right now, all I have is the Arduino Opta PLC plugged in via USB-C cable to my laptop, and then plugged in to a 12-volt power supply for DC power. So that is the total physical wiring. There's no cards clamped on there yet. I have them just sitting here waiting to be hooked up. But so we have a brand new project, nothing going on. I'm going to go ahead and onboard the file system just like you do first time with any PLC, so we can really start from scratch together. And that takes a little time, but it looks like it works. So if we just go into our LED outputs real quick, and we just give ourselves like L1, L2, L3, and L4 variables real quick, as well as, let's just say, you know, red,
green, and blue. And then let's grab that user button input and let's call it user so we can program with those variables now. Hopefully you've been following this series and that's all pretty familiar to you. And we have this count program. Let's just go ahead and say that we want green to be on and we want blue to be equal to the user. This is just kind of like a great 1-2 line to make sure the PLC is actually working when you connect to it and then download to it. So we connect. It says no code. That's good because it's the first boot up, so there is no code running on there. And we're going to go ahead and just send this, and hopefully it compiles okay, downloads okay, and then we'll get the green light turning on, and then the blue light will turn on and off as we push the user push button in. That means our PLC is all rocked and rolling and ready to go. It'll ask you to restart. Go ahead and hit yes. Target reboot. Shouldn't take too long. Okay, and it does look like it worked. The bottom right says source okay and connected. If I come in here and turn on live debug mode, I can see the count counting up, which is good. I'll grab a video real quick here of the front of the Opta. So the green light's on, and as I push the user push button in, I get the blue light. So that's great. It's online and we're communicating with it. We've been in this point a few times before. That's not really the new content for the video, but this is where we're going to start from because now it's time to add those I/O expansion modules. And the wiring and the IDE, the PLC software side of things are both really simple, but it's easiest to just do them one at a time. So let's go ahead and take a look at the wiring really quickly, and then we'll look at the IDE side really quickly. Now the wiring required to get one of these expansion modules, again, there are 3 and they all look very similar to the body of the PLC because they all clip into the same chassis. It's very simple for wiring. They just need their own power feed, which you can daisy chain off of the PLC or the card right next to it, or you can give it dedicated 12 to 24 volt power. But then they have these little slots in the side. The PLC has that same slot right there, and they need these little 10-prong I2C communicators. Oh, I dropped that one. Okay, well, there's one right here. They need these little communicators, and they just clip in right next to each other, and that's how they communicate card to card. And we'll see in the IDE once we get these clipped in that the PLC actually knows what cards it's plugged into because of those little communication tabs. So that's all we have to do is get the power hooked up and then get these clipped in together. So I'll go ahead and do that now, and we'll go back to the software side. Okay, so I've got them powered up. I've got them hooked up to power, and I've got them communicating down the line, which is great, but you can see the lights are kind of doing their own thing. Green for power is good, definitely means they're connected, but the PLC is throwing an error because it doesn't know what to do with these cards because we haven't told it what to do from the software yet. So the physical wiring, very simple to connect them. Now we have to look at what to do in the PLC IDE to connect them. So if we come back into the PLC IDE and we try to connect to it, well, we'll see that because I unplugged it. Now that we're plugged in, if I just try to connect to it again, I'm going to get errors because it's not in a running state because the I/O configuration has changed. So the PLC has thrown an error. If I go to I/O expansions and I hit scan, this is really cool. It's going to say, hey, the configuration's not matching. And it's going to say, hey, I have these cards here. Do you want to add them? And I can just hit apply detect config. If you hit scan and they're not detected, you should double check your wiring because something is probably wrong with the physical wiring. But if you're sure the wiring is correct, or if you're trying to set one of these up ahead of time, you can always add a card just by right-clicking on I/O expansions and hit add. And you can select the cards and you can add them to your project manually. But it's a lot easier to scan and then say, okay, apply the detected config. And then it adds the cards as well as all the programmable inputs and outputs that you can use for those cards. So if we take 2 of the LED channels on the first card and we just say that'll be light 1, 1, that'll be light 1, 2. And then I take the relay outputs on the second card and I say that'll be output 2, 1 and that'll be output 2, 2. We'll use those 2 lights on those 2 cards to do a little bit of programming with. Okay, so I'm going to go ahead and hit save, and then I'm going to try to download this now that it has these cards on it. Well, first let's go to the program and let's do something. Let's say that we just want light 1, 1 to be on all the time, and we want light 1, 2 to be on when the user push button is pressed as well. And then let's say the opposite for the second card. Let's say we want output 2 on all the time, and then the light for 1 to come on when the user push button is pressed. Okay, so this should compile unless I missed something, which is possible. Build looks fine. Now let's go ahead and download. Download. Yes, it's okay that it's going to want to restart. Restarted pretty quick, but there's no lights on because the PLC is not running. That's an important clue. You can go ahead and hit cold restart here, the blue circle there, and hit yes. And that's cool. That's best case scenario for sure. It's normal to need to power cycle at this point. Stuff goes goofy sometimes. But I have now one LED on both of the expansion modules, and if I push the push button in, you can see the other LED on both cards turns on with the blue LED on the Opta itself. So that is proof that the cards are talking to each other and that I can program any input or output channels for any of these cards from the PLC now, and I've got all the communication. Okay, so at this point, you should understand how to get expansion modules added to your PLC. Like I said in the beginning, they're not all this straightforward for all PLC manufacturers out there, but Arduino has made it really easy to add their expansion modules, and it is generally the same steps of set the network parameters, connect them to your network, and then discover them in your PLC IDE or related software. Like with Siemens, they have TIA Portal, but they also have a software called Proneto where you can discover and set up network parameters for Profinet devices. RS Logix, they have Studio 5000, which is this integrated software, but they've always had this RS Links software where you can see network devices and you can see remote I/O and things like that. So there's definitely some industry knowledge. It's hard to become an expert in every type of remote I/O, but now you understand the basics of adding I/O expansion modules to your projects, especially for the Arduino Opta PLC. I'll have all the hardware I used in this tutorial linked in the description below this video. Let me know with any questions or snags that you ran into on this video, and let me know what you want to see more of next on the channel. Thanks so much for watching, and see you next time. Thanks. Bye. Welcome back to LeMaster Tech, and in today's video I'm going to show you how to use push buttons and switches for industrial controls and automation. I will probably skew the topics in this video towards applications that might involve controls and automation, but this also is applicable for anyone who wants to use push buttons or switches for hobby applications. And far and away, the most common example of a digital on-off input that is used in controls and automation and hobby circuitry and electronics are the push button and the switch. With a push button, it's either pushed or it's not pushed. With a switch, it's either in position 1 or position 2. So today we'll be looking at the most common wiring and talking about some of the uses and applications of push buttons and switches for controls, automation, and electronics. And a huge thank you to APL who provided the hardware we use in this video. More about them later in the video. Now let's start with the most common type of push button you will see anywhere and everywhere. A momentary push button. This is a type of device that is only going to read a 1 or high or energized when it is actively being pushed in. At an absolute minimum, these buttons may only have 2 wires because that's all you need to get the effects of a push button. It's basically the power feed in, and then it's broken by a strip of metal that is not made until you push the button in. When you push the button in, power flows into the second wire and goes downstream. When you have a slightly more advanced button that has things like a built-in LED or a normally opened and normally closed wire, you can do a lot more functionality with it. To understand the concept of normally open and normally closed, it's useful to start from the concept of common. On this momentary push button in particular, there are 5 wires total. Now 2 of them are just the power circuit for the LED, so to discuss the controls concept going on here, we actually just want to focus on the other 3 wires first. And those 3 wires are common, normally open, and normally closed. In our case, we'll put our positive power from the 9-volt battery on the common wire, which is green for these buttons. When I'm not pushing in my momentary push button, one of the wires will read 9 volts and the other wire will read 0 volts. The wire that's going to read 9 volts when it's not being acted upon is the normally closed wire, which in this case is yellow. The wire that is going to only read 9 volts when we're pushing the button in is the normally open wire, or blue in this case. So when you have a device that offers you both normally open and normally closed feedback, what you're saying is there's a wire there that will be connected to common until you push the button in, and then there's another wire there that won't be connected to common until you push the button in. So for my application, I have the ground of the LED pin connected to the negative terminal of the battery, and then I have the positive terminal of the battery connected currently to my normally open contact, meaning the light will not turn on until I close this button. Then I have the positive power from the battery coming into the COM terminal, and currently I don't need any purpose for my normally closed contact, so I'm just going to cap that off. It's not a good idea to leave live copper wires around even when you're only working with low volt DC. Now what we'll see when I push the button in is I'm actually powering the normally open wire, which now becomes closed, and because it's connected to the power of the LED, it turns the LED on. To understand the difference between the normally open wire and the normally closed wire, we can just flip which one our power LED is connected to. So the red wire, which determines whether or not we have the LED powered on, is now going to get connected to my yellow wire, which correlates to normally closed on the button. Because it's normally closed, we can see that the LED turns on right away, and it doesn't turn off until I push the button in. In my handy dandy box where I have a whole bunch of these hooked up, that's how I have both of my momentary push buttons hooked up. Now that's not just a deep dive into how momentary push buttons work. We also covered the fundamentals of how normally open and normally closed terminals work. For that reason, we'll really be able to fly as we talk through the next one, which is a latched push button. So the biggest difference between a latching push button and a momentary push button is right there in the name. With a momentary push button, you have to be actively holding and affecting the button for it to change from a 1 to a 0. With a latching push button, there's an internal and rather interesting ratcheting mechanism which will hold it in place until you press it again to release it. So effectively, you're getting the switching between a 1 and a 0 effect that you get with a momentary push button when you press it in and release it, but it holds its state. So you can put it in 1 and leave it and come back later and put it to a 0. So using the exact same wiring configuration that we just had with the momentary push button, where the LED was connected to the normally closed contact, and when we push the button in, the LED goes off, you can now see that I get the same functionality that I was getting before by having to hold it, but now I can release it and leave it in place. So now with the exact same normally open, normally closed configuration, now I have the LED connected to the normally open terminal. So once I push the button in, the light comes on. When I push it again, the light turns off. Now, in my opinion, because we're looking at a latching push button, that's a good chance for us to take a look at pivoting into the latching switch. Now, I have a couple different types of latching switches here on my handy dandy box. One that has no visual indication of whether or not it's passing power onward, but has 2 positions, and one that does have an LED to show you whether or not it's feeding power out of the load line. The limitation of these switches, as we'll see in a second, is there's only one way for you to feed power out. So you don't have the normally open, normally closed connections that you do actually have with a 2-position switch like this. So it's important before selecting your hardware for any application to think through the use case. If you have a switch that is as simple as it needs to pass power on, so you just want to be able to flick a switch and feed power to a bunch of devices, flick it back the other way, and kill power to those devices, something that only has one signal wire coming off of it is probably perfectly fine. In the case of my switch here, I can turn it on and I get the visual indication that the LED is on. And in this case, I'm actually triggering another LED on this push button just as an example of how to use the switch. So when I sit here flicking my switch, I'm turning not just the LED on this, but also the LED on this light on. However, a limitation is when I turn it off, the light has to turn off. There's no way for me to use this light to turn on this light in an inverse manner, where if I wanted the green light to be on while the switch was in a de-energized way, because the switch only has one load wire and the other two are the power feed, there's no way for me to effectively do that. So if I had an application where I needed a switch to do one thing in one position and a different thing in another position, this would not be the right switch to select. But it does give me visual indication of whether or not it's feeding power down the line. So we move on to the selector switch that has 4 terminals on the back. And when it has 4 terminals, what it actually has is 2 sets of electrically independent contacts. So when I am in position 1 on this switch, 2 terminals are being connected in the back and the other 2 terminals are not connected to each other. Then when I flip the switch into its other position, the opposite 2 terminals get connected and the original 2 terminals that were connected are now broken. You can see that here by my blue and green LEDs that change, hopefully you can see that change state every time I actuate the switch. So here again, I have not so much normally open, normally closed configuration, but position 1, position 2. These are very often used not just for on-off like I have here, where I use my switch to kill power to the entire enclosure. I could use it where when it's in position 1, it powers only this half of the box, and in position 2, it powers only this half of the box. That would be a normal application for it. They do make a 3-position selector switch as well that has the same 4 terminals on the back, but it also has an off position where no terminals are being connected. The most common use for that would be like on a pump. You might see a hand off auto. In hand, the left 2 terminals might be made. In off, no terminals might be connected. And then in auto, it might be the right 2 terminals. There are definitely more selector switch options out there, some of which have 8 terminals on the back, some have 6 terminals on the back, but far and away a 2-position selector switch with 2 sets of isolated terminals is the most common type that you'll run into and the most common type you would need. So just to show one cool variation on the 2-position selector switch, I also wanted to talk about this cool keyed selector switch. It's effectively exactly the same device as this 2-position selector switch, but rather than being able to be turned by a human hand, you have to turn it using the key that matches it. And this way, you're able to control access to who can power up a piece of equipment or machinery using a set of keys. In this case too, the key is actually locked in the device while it's on, so you can't turn something on and walk away with the keys. Anyone has the ability to turn it back off, and then you can take the keys away. This is a safety measure to make sure that anybody is able to deactivate a piece of equipment if they feel it's unsafe. It's not incredibly common to see these, but it is an interesting and useful to know about variation on the selector switch. The last and most important maybe piece of equipment in industrial controls and automation that I want to talk about that is really just another form of a latching push button is the e-stop. And the purpose of an e-stop is really to kill power to an application. Some e-stops do have terminals and feedback to a PLC or a controller or a stack light to let you know that they have been pressed, but typically the main reason you hit an e-stop is something is wrong and you want to kill power to a device or at a minimum put it in a safe state. Wiring and functionality wise, everything we discussed about momentary push buttons still applies here, but typically there's an extra motion like a twisting motion or a hard pull to release an e-stop. When it gets pressed, it's supposed to be easy to press in to put things back into a safe state and require effort and intentionality to release and put back into an operational state. But it's a super useful piece of equipment to know about, especially if you're in the world of automation or controls. I know at first glance how to use push buttons and switches can seem really intuitive or like a basic concept, but it's actually one of the most important fundamental things to get down if you want to be doing industrial controls and automation or hobby electronics and building with robotics at home. The topics and concepts covered here will serve you great not just as you build physical things, but it also helps you think through logic and how programming using normally open and normally closed conditions work as well. As always, good luck with your projects. Thank you for watching, and we'll see you next time. Thanks. Bye.